Hi, welcome to the Kotlin for Java Developers course. My name is Svetlana Isakova and I'll be your instructor for this course. I'm a developer advocate at JetBrains and a co-author of two books about Kotlin, Kotlin in Action and Atomic Kotlin. This course is for you if you are an experienced developer who knows Java and wants to learn Kotlin. I won't explain programming fundamentals or Java basics. I will only highlight what is new and different. After this course, you'll be able to use Kotlin for your daily tasks. If you are a developer who learned Java many years ago and now uses some other languages, you may still decide to watch this course. However, note that you may need to check some Java concepts on your own in order to better understand what's going on. This course will consist of 4 modules, which basically you can watch on your own pace. If you have a full-time job, you may decide to watch each module in 2 weeks or more. That's fine. If you, for instance, need to prepare to the interview, then you may decide to watch everything in a week. That's totally up to you. We'll have many in-video questions. Note that sometimes these questions will introduce a new idea, not just ask you about something that I've already explained. And in this case, even if you don't know the answer, just make a pause, think, and you may guess. And just afterwards, you will see the solution. Each question will followed by the explanation directly in the video. We'll have many small tasks which you can do directly in the browser. Note that these tasks are ungraded. You may just check yourself by ensuring that all the output is as expected. And this task will be accompanied by the solution video. And I would recommend to watch these videos after doing the task. Sometimes these videos may highlight different options, compare different options, or introduce some new details. At the end of each module, we'll have one full assignment. And note that you may implement, read the task, do the solution, and check the solution from IntelliJ IDEA directly using the EduTools plugin. You'll find all the necessary installation instructions and the accompanying materials to this course. In this video, I will introduce the Kotlin programming language, highlight some basic facts about it, and mention what we will and will not cover in this course. Kotlin is a general-purpose language which supports both functional programming and object-oriented programming paradigms. It's an open-source project developed mainly by JetBrains with the help of the community. Like Java, Kotlin is a statically typed language. However, in Kotlin you can omit the types, and it often looks as concise as some other dynamically typed languages. Kotlin is safe. It's even safer than Java in terms that Kotlin compiler can help to prevent even more possible types of errors. One of the main characteristics of Kotlin is its good interoperability with Java. It's hard now to call Java a modern language. However, it has so huge ecosystem that it would be really difficult to create it from scratch if you use a new language. And that's not our goal. We really want to be able to reuse every Java library, every Java framework from Kotlin. And it really works like that. You often can improve your experience with working with some library, but you can use any library from Kotlin. JetBrains is a tooling company, and you may expect a really good tooling support for Kotlin, and you'll be right. In Kotlin, you can use all the same IDE support, like completion, navigation, refactoring, all the same features that you used to have for Java, and that will work. Kotlin is a pragmatic language for industry. It's not a research project that just tries some ideas. No, it is based on many existing languages, and it tries to reuse what works there, and you often can find what language was the source of inspiration for some Kotlin feature. Kotlin project started at 2010, and it took it 6 years to achieve its mature state and first release. Afterwards, it was acknowledged as a first-class citizen on Android, which really boosted the adoption. You can see the trend here. You can notice that peak. In this graph, you find the number of GitHub lines, and the Stack Overflow question, which just show you the overall trend, which is quite optimistic right now. Android is an important platform for Kotlin. Note that this course won't cover specifically Android. It will cover Kotlin in general, but that will help you to better understand how it works and to use it successfully on Android. Many people now think that Kotlin is the language only for Android, and that's not true. Actually, there are many server-side developers which already successfully use Kotlin for their projects, and you can use Kotlin whenever you used Java before. But that's not only that. Kotlin is not only JVM or Android. We have other target platforms as well. So, of course, JVM is the first one, but also you can compile Kotlin code to JavaScript or even now into native code. For this course, the main target platform, the only one that we'll cover is Kotlin JVM, because it's the most mature one and the most used. But if you want to switch later, it will be quite easy because it's the same language. And the main ultimate goal for this, for having the several different target platforms, is being able to write the full stack application entirely in Kotlin. So you can write the Kotlin code on the server side and the front end, and you can write application code in Kotlin. And what's even more important is, the more important goal is to be able to share some business logic, some common code, to be able to share it between different platforms. You can check what's going on there. There are several online resources and videos with explanation of how that works. For now, this course we won't cover it. I just mentioned this picture, kind of the future, to share it with you, to share the whole picture. Right now, in this course, we'll focus on Kotlin JVM, and let's start our Kotlin journey, and I will explain you how Kotlin makes JVM a better place. It's really easy to start using Kotlin, especially if you're a Java developer. You can use all the existing Java frameworks and libraries from Kotlin. You can even mix Kotlin and Java code in one project. Kotlin is a JVM language, so you can easily call Java code from Kotlin, but that also works in the other direction. Kotlin is designed in a way so that using its all features from Java was straightforward. That means that you can make the transition from Java to Kotlin very slow by adding new features to your existing Java application written in Kotlin. What do you think? Is the Kotlin code compiled to Java source code or Java bytecode? Of course, it's compiled to Java bytecode. Compiling it to Java source code first would be really ineffective. There is a powerful tool that helps to speed up the process of learning language based on your Java experience. This tool is Automatic Java to Kotlin Converter. The converter has two main use cases: learning the language and incorporating it into an existing Java application. When you know how to write something in Java, but don't yet know or remember the exact construct in Kotlin, you can write it in Java first and then convert it. It's also extremely useful to use the converter when you start adding Kotlin into existing Java application. When you have a Java class and you need to modify it, you may prefer using Kotlin. In this case, you can convert this Java class to Kotlin first, and then you'll be able to write new code in Kotlin. Now let's look at Java to Kotlin converter in action. This typical example of a Java class is often demonstrated to show differences between Java and modern languages like Kotlin. This Java class does nothing meaningful, it just stores the data. The person class contains two fields, constructor and two getters. We can convert this code automatically into Kotlin using Java to Kotlin converter. You can call an action convert Java file to Kotlin file in IntelliJ IDEA or in Android Studio. As a result, it gives us the same code written in Kotlin. You can see the difference. It's much more simple and concise. Under the hood, at the bytecode level, the same constructor and two getters are generated. So from Java point of view, that's the same class. What's more, you can add a data modifier to this class. That will automatically generate several additional methods for it. Note that we'll discuss the syntax for property declaration in detail later. In this example, it's val name and val age, as well as the full syntax for variable and function declarations. For now, I want to illustrate how the automatic converter works and highlight some differences with Java. That's how we can use the person class. We create an instance of person and then we print its name. At first you see the code written in Java, then the analogous code in Kotlin. The main point to note here is that there is no new keyword in Kotlin. You simply call the constructor as a regular function without new keyword. Let's now look at another example of Java to Kotlin converter in action. We'll see that the converter doesn't always produce the best result. The converter will produce the Kotlin code that is very similar to its Java counterpart. Then we'll try to simplify it. So let's start. The update weather function in Java does a very simple thing. It assigns two different values to two variables depending on the temperature. The enum class color contains the colors used to describe the weather. We assign the description and the color values depending on the degrees. Probably here it's more European way of perceiving the weather. For some people, less than 20 Celsius or 70 Fahrenheit will be already cold. It's a very straightforward code in Java, and we can convert it to Kotlin automatically. There are two main ways to use the converter from IDE. You can either convert the whole file from Java to Kotlin as we saw before, or you can copy the Java code and paste it into the Kotlin file. In this case, IDE will suggest converting it automatically. You can copy the Java code from any place, for instance from a browser, Google the Java code, copy it, paste it into a Kotlin file and see the analogous result. Here is the update weather function code converted to Kotlin. It looks very similar to its Java version. You see new fun and val keywords for function and variable declaration, but overall you understand what's going on. This function initializes two variables using a slightly different syntax. However, we can improve this code, make it more Kotlinish. What can be done? At first, we have to repeat the variable name several times. We say description equals, but in Kotlin we can avoid it. We can initialize two variables at once by a pair of values. The first value in each pair is used to initialize the first variable description, the second value initializes the second variable color. Now we don't have to repeat the description variable name. The next improvement. When you define a variable in Java, you have to specify its type. In Kotlin, you can prefer to omit the type if it's clear from the context. When you omit the type specification, the Kotlin compiler infers the type automatically, based on the initializer expression. IDE can do automatically the next simplification. We want to replace if with when expression. When expression in Kotlin is similar to switch in Java. It allows you to enumerate several options. It's especially useful when you have more than two if-else options. When often looks nicer for this use case. We are almost done. We now have only one last change. To be more Kotlinish, we can replace the constructing of pair with to. There is an alternative way to create a pair in Kotlin. We'll discuss later in this module the details of what exactly it is and where to comes from. That's the result. That's how we converted the Java function into a Kotlin function. You can compare the initial code written in Java and the improved Kotlin version. The question to check yourself. Does the automatic Java to Kotlin converter always produce the idiomatic Kotlin code? The answers are yes or no. Automatic Java to Kotlin converter is very useful. It's very helpful in many situations, however, often it just converts the code automatically. To get the best results and to get idiomatic Kotlin code, you have to manually improve it, replace some constructs, rewrite some code, and so on. You've seen the examples of using Java to Kotlin converter. That already allows you to start experimenting with Kotlin if you want. Next, you'll learn the basics of the language. In this video, you'll see how the classical first Hello World program can be written in Kotlin. We'll discuss how it's different from Java, and you'll also learn about Kotlin language features that can improve this already simple piece of code, such as top-level functions and string templates. Let's look at our Hello World example. In our case, it will be Hello Kotlin example. This simple program prints Hello Kotlin. Let's try to compare it with a similar code written in Java. The first thing that comes to mind, apart from these new keywords for function variable declaration, is that there is no class here. This function is defined at the top level, and it is the only contents of the file. Our file hello.kt is the whole program. It contains the package declaration and the function at the top level. In Kotlin, you can define the function at the package level. You no longer need to put everything inside a class to define a lot of static utility functions inside a special util class. If you need general functions without binding to the specific class, you can define them at the package level. In Java, the main function always requires the program argument list. But for simple use cases, these program arguments are often unused. Starting from Kotlin 1.3, you can omit main program arguments and define args parameter only if needed. To make our first program a little bit less trivial, let's print Kotlin if no program arguments are passed, or hello and the value of the program argument if there are some arguments. There is no special built-in syntax for arrays. Under the hood, at the bytecode level, it's the same array as in Java. However, in the code, array looks like a regular class with generic arguments. Note that in Kotlin, if is an expression. You can assign the result of if into a variable or return it from a function. If returns you the result value. Here we use if to check whether there are any arguments passed to this function. In Kotlin, you can use this nice syntax for string templates. You can insert a value inside a string literal by using a $sign and a variable name. If you need to print out a more complicated expression like a function call, if expression or some arithmetic expression, you can insert the value of this expression, but you have to surround it with curly braces. For example, we can print the value of the first argument if some arguments are passed. What do you think is printed if there are no arguments? There are three answer options. Hello null will be printed, hello and exclamation mark, or null pointer exception will be thrown. What's your choice? Under the hood, Kotlin uses Java lang string, and that means that such things work directly as in Java. The question might be then reworded as how the same logic would work in Java. In Java, if you try to print the value of null or to add null to a string, you will see hello null as a result. In Kotlin, it's absolutely the same. Under the hood, Java lang strings methods are called. Java lang string transforms null constant into a string null. If you want an empty string instead of null, as in Java, you have to process that explicitly. So the right answer is hello null. One more question. Here we call the foo function twice inside a string template. And the question is, how many times the result of this foo function will be computed? The first option is that it will be computed twice, and calculating foo will be printed twice. The second option is that it will be somehow cached, and the function foo will be called only once. What do you think? The answer is the first one. We simply call a function twice inside a string template. There is no magic here, no unexpected optimizations. Your function can return a different value on each access. If you want to store this value and compute it once, you have to do that manually. If you call the function twice, it will be computed twice. In this video, you've learned that functions might be declared at the top level, if is an expression in Kotlin, and you can insert any expression inside a string using string templates. Next, we'll focus on variables in Kotlin. In this video, you'll learn how to define and use variables in Kotlin. There are two main keywords to define variables, val and var. Val comes from value and denotes a read-only or assign once variable, while var comes from variable and denotes mutable variable, the one that can be modified. Read-only variable can't be reassigned. If you try to assign a new value to it, you'll get the compiler error. In essence, val in Kotlin corresponds to a final variable in Java. If you need to reassign a variable, you declare it as var. Then you can easily assign a new value to it. In Kotlin, you can emit the types of variables and the compiler will infer the types for you. Here we emitted the types of these two variables and they are inferred automatically by the compiler. Kotlin is a statically typed language, which means that every variable, every expression has a type. Even if you emit the type, the compiler just infers it for you. It doesn't mean that this variable doesn't have a type or it's unknown. It means that the type specification is verbose, it's clear from the context, and you trust the compiler to infer the type. The question to you, why doesn't the following code compile? Because you can't reassign a var variable, because you can't assign an integer value to a variable of string type, or assign a string literal to a variable of int type. The third option is correct. Because of the local type inference here, int type of the variable is inferred. It's called string, but it was done on purpose only to confuse you. The type of this string variable is int. And the Kotlin compiler complains that you try to assign a string literal to a variable of an int type, but int is expected. That's the compiler error. Another question for you. Is it possible to modify an object stored in val? What do you think? There are options yes and no. If we are talking about reference types in Kotlin as in Java, variables just refer to some objects stored in memory. And this question can be reworded as, does val put any additional constraints on the stored object? Of course, there are no additional constraints. You can easily modify an object stored in val as in Java. Val, like a final variable, is mutable reference which doesn't say anything about the content that is stored. For example, here we have a reference to a mutable list. Languages refers to an object in memory. We can modify this object by accessing the modification method. We can't assign another reference to the language's variable, but we can easily modify this exact object. Another question. What do you think? Why doesn't the following code compile? That might be a source of confusion for people who are new to Kotlin. The declared variable has the type list, but when you try to modify it, you see an error. What do you think? That's because you can't modify a read-only list or modify an object stored in val. You can't modify a read-only list. We've already discussed that val doesn't give you any guarantees about the content stored in an object. The content can be easily modified, so the second option is wrong. In Kotlin, we have a distinction between mutable and read-only lists. Note that we use the same keywords mutable and read-only as for variables. In this case, read-only list just lacks mutating methods. If we try to call add on a Kotlin list, which is a read-only list, the compiler will complain that there is no such method available. By default, strive to declare all your new variables with val keyword, not var. Using immutable references, immutable objects, and functions without side effects makes your code closer to the functional style, which is easier to understand and support in the end. When type specifications are clear from the context, it's safe to omit them. For instance, if it's variable of a primitive type or string, or the type is clear from the variable name, that's rather straightforward. However, if any confusion of what's going on is possible, it's better just to have this type specification explicitly, to keep it, to avoid this confusion. In this video, you've learned about two different keywords to define variables in Kotlin. Val for read-only variables and var for a variable that you may need to modify later. Next, we are going to discuss functions. In this video, you'll learn the different syntax of how to define a function in Kotlin. Also, we'll touch the question of Java interoperability and discuss how to call a top-level function from Java. Here you can see the syntax for function in Kotlin. This function returns a maximum of 2 values. Note that the parameter type specification is put after the parameter name, like for variables. In a similar manner, function return type specification follows the argument list. If your function simply returns one expression, you can use an alternative syntax, so-called function with expression body. IDE like IntelliJ IDEA or Android Studio can automatically convert from one form to another. The expression that the function returns goes after the equals sign. IntelliJ IDEA nicely highlights the type specification for us, and by pressing only one key, you can either remove it or leave it. It makes sense to specify types explicitly for public API for library functions. If it's a regular application, you have a function, especially a private one, and its type is clear, for instance from its name, you can safely omit it. Note that if you try to omit the type for a function with expression body, it will mean that this function returns unit. You can think of unit as an analog of void. The displayMax function returns no meaningful value. It's written for its side effects, and the compiler considers its type as unit. You can use an alternative syntactic form by specifying unit explicitly, but I think no one does that. In Kotlin, you can define functions everywhere. You saw that you can define a function at the top level or make it a member of a class. You can even define a function inside another function. Then it's called a local function. Sometimes it's really convenient. What do you think? Is it possible to call a top-level function from Java? If that's possible, then how to access it from Java? And there are options: you can't do it, or you can call it as a static or member function of the class which name corresponds to the file name containing this function. From Java, you call a top-level function as a static function. All top-level functions under the hood are implemented as static functions. Here is the example. We define a top-level function foo in Kotlin, and from Java you call it as a static function. The top-level function is defined in the file called myfile.kt. At the bytecode, the underlying static function belongs to a class myfile.kt. From Java, you can import a class by its name or use import static. This last syntax gives you the same foo invocation as in Kotlin. If you want, you can change the name of the class that contains all the top-level functions as static functions. For that, you use a JVM name annotation. You annotate the file contents and put the annotation right before the package name. Now you call foo as a member of a class which name you specified, in this example of the class util. Now you know the difference between function with a black body in Kotlin and function with expression body. You've also learned about JVM name annotation that can change the name of the class containing top-level functions. Next, we'll see how Kotlin can improve a function invocation. In this video, you'll learn how to provide default values for arguments or specify their names in a function call. Let's start with the question: what will be printed here? The join-to-string function joins the content of a string in the desired way. You can specify separator, prefix, and postfix. The output should be quite straightforward. We simply join the content of the list by using an empty string as a separator and surrounding it by the specified prefix and postfix, the parentheses. You can specify the names of the arguments directly in the code. That often makes the invocation more readable. It's easier to understand what the arguments are supposed to do, especially for arguments of basic types such as int, boolean, or string. Named arguments are often used together with default arguments. For join-to-string, you can provide only the value for one of the arguments, for instance, postfix. Looking at the output, we can understand that the default separator is comma and an empty string is used by default as prefix. You don't have to specify the values for all arguments each time. You can change the defaults only if needed. Let's see how you can declare a function with default values for arguments. Here, the function displaySeparator prints a character by a given number of times. We use star as character by default and 10 as the default number of times. Afterward, you can call this function with different argument values. For each argument with the default value, you can either provide another value or use a default one. However, note that if you need to provide only the value for the second argument, then you'll have to use named argument syntax. By default, there is the direct correspondence between unnamed arguments and parameters according to their order. The next question to you is, what is printed in this case? The options are 5 threes, 3 fives, or the code won't compile. What do you think? The right answer is the code won't compile. As I've told you, there is the direct correspondence between unnamed arguments and parameters. This code doesn't compile because you can't pass int constant whenever char is expected. And similarly, you can't use character argument as int parameter. In Kotlin, there are no implicit conversions. You can't implicitly convert an integer to a character or vice versa. You have to explicitly call toInt or to char functions for such conversions. If you pass the arguments by name, you can change their order easily. In this case, we get what we expect. It prints character 5 by 3 times. In Java, if you want to achieve the same behavior, you will use the overloaded functions. To provide the functionality of default arguments, you will define several different overloads and call one inside another by specifying default values. In Kotlin, you use the default arguments feature directly. You no longer need to provide several overloads. But there is an interesting question: how to call a function with default arguments from Java? When you call a Kotlin function with default arguments from Java, you have to specify the values for all the arguments. That happens to minimize the number of functions which are generated under the hood. By default, Kotlin generates the function with all the arguments and only one additional auxiliary function containing information about all the default values which you can't call from Java. If you want to call the Kotlin function with default arguments from Java in a convenient way, then you can add JVM overloads annotation. After you annotate the function with default argument with JVM overloads, you can specify only some of the arguments when you call it from Java. The next question is not about JVM overloads annotation, but it will help later to understand how exactly it works. The sum function has 3 arguments here. You can either specify each argument value or omit it and use the default value. How many argument combinations are possible when you call this function from Kotlin? The first combination is specifying only the first argument, the second one is specifying only the second argument, the third one is specifying both the first and the second argument, and so on. The answer is 8, which is 2 to the power of 3. In a general case, if we try to cover all the argument combinations, it will be too many functions. 2 to the power of the number of arguments with default values might be too many. Let's note how JVM overload annotation works. JVM overloads annotation generates in this case only 4 functions, the one for each new argument with the default value. Note that if you don't use the function with default arguments from Java, there is no need to add the JVM overloads annotation. Even if you use it occasionally from Java but you want to have only one function for performance reasons, you might want to leave it without annotation and to specify the argument values explicitly in Java. That's your choice. We've discussed the syntax for named and default arguments in Kotlin. You saw a useful join-to-string function that allows you to print list contents in a desired way. Also, we've discussed how to make usage of a function with default arguments convenient from Java. That completes our discussion about functions and variables. Next, we are going to focus on control structures. In this video, we are going to discuss the basic control structures in Kotlin. We'll start with if and when. You will learn how when expression in Kotlin is different from switch in Java, which expressions can be used as when conditions, and what are smart casts in Kotlin. As we've already discussed, if is an expression in Kotlin. That means if returns a value which you can assign to a variable like here. In Kotlin, there is no ternary operator like in Java. If you need the logic if a condition is satisfied, return one value, otherwise return another value, you use if expression. We've already seen when. At first, it might be considered as an analog of Java switch. When you have a enum class with some values, you can perform actions or return a specific expression depending on the enum constant. When then takes enum value as an argument and checks all the enum constants. There is the similar code written in Java and in Kotlin. In Java, you have to use break or return if you want to stop operating inside the switch branch. Otherwise, you'll get the unexpected results, like all the colors will be printed as blue. Note that this small example might be improved in Java by extracting a function returning color, but it nevertheless illustrates the difference. In Kotlin, you no longer need to use break to say that the operation should stop here. If the when condition is satisfied, the result of the corresponding branch is returned. Note that you have to specify the paths to the enum constants explicitly unless you import them. By default, you say color blue, color orange. But you can import enum constants, and in this case, you no longer need the explicit class specification. You use enum constants simply by names. You can check whether when argument equals to one of the values. You list several values separated by comma. You can use any expressions, not only constants, as branch conditions. Here, we create a set of two colors and compare it with three predefined sets. When Kotlin compares sets by quality, under the hood it calls set equals, which compares the content. We use sets here to ignore the order of the colors. If one of the branch conditions is satisfied, we return the corresponding result, the color after mix. Sometimes you have a type hierarchy and need to check whether it's this subtype or that subtype and do actions accordingly. In Kotlin, you can use when for this. Is checks whether an argument is of a specific type. Is cat is analogous to Java's instance of cat. Note that you don't have to cast explicitly the variable after you checked its type. It's automatically smart cast to the right type. In Java, you cast the variable to the type after checking instance of. In Kotlin, you simply access its members as it was of the right type. For convenience, the smart cast expressions are highlighted by the colored background in ID. Note also how in Kotlin we use when rather than the cascade of if-else. Starting from Kotlin 1.3, you have the opportunity to introduce a new variable for when subject directly inside when expression. You often want to use the whole expression as the when subject. You can easily do it, however, the complicated expression can't then be accessed as one variable inside when. And since there is no variable, nothing will be smart cast, even if you check its type. You need to explicitly introduce a new variable name like pet in this example. Then this variable is accessible also after when expression, and it makes it possible to return when directly from a function since it's two statements. Now it's improved, and you can introduce a new variable name right inside the parentheses by using val keyword. Then this variable name is visible only inside when, and also it's possible to use such when as the only function body. This when comes from our previous Java to Kotlin conversion example. Note that there is no when argument here. It's when expression without an argument. You can put any Boolean expression as a branch condition. If it's satisfied, then the corresponding branch code is executed, or the corresponding expression is returned as a result. That's the analogous code written in Java, as we've already seen before. What do you think? Is it true that you should always prefer when to if? No, you don't have to do that. When expression is especially useful for more than two branches. You can use it for two branches if you prefer, but you don't have to. If is still useful. You've learned how to use if and when expressions. Next, let's discuss loops. Kotlin has the same basic loops as in Java: for, while, and do while. In this video, you'll learn about them and also learn about some niceties like iterating over a map using a for loop. In Kotlin, we have the same while and do while loops as in Java. Nothing more to say here. For loop looks a bit different. First, a different keyword is used to express iteration over something, in. Second, we omit the element type. Probably is the case when the types are omitted most often. If you want, you can specify the element type explicitly. Another difference is that in Kotlin you can iterate over the contents of a map. Here we assign key and value separately at each iteration loop, then print the result. This syntax works not only for maps, it can be used to iterate over collection with index. After we say with index, we can assign both index and element on each iteration turn. If you need to work with indexes directly, you can use ranges. There is no full form of for loop as in Java. You use ranges instead. Here we iterate over a range of numbers from 1 to 9. That's the result. You can also build a range using until function. The last number then will be excluded. The first range includes the upper bound and using until function excludes the upper bound. If you want, you can build more complicated ranges like with iterating backwards or over a step. You can even iterate over a string. What do you think? What is printed here? When we add a number to a character, it returns the character with increased code. The letters go one after another. So if we say character plus 1, for A, it will return the next letter in the alphabet, B. Another question for you. Which is the right way to write the following Java code in Kotlin? We have three options, using to, using regular range, or using until. In Java, this code prints numbers from 0 to 8. It's the same as using until in Kotlin. Note that the first line doesn't compile. To creates a pair in Kotlin, not a range, and you can't iterate over a pair. We've discussed loops in Kotlin. When you need to iterate via indexes, you use ranges in Kotlin. In the next video, we are going to discuss ranges in more details. In this video, we'll discuss ranges. It is a very convenient feature that has no direct analogous in Java. You'll see how to check for belonging to range and what you can do with the range of strings. In is used for two different use cases in Kotlin. We discussed the first one in the previous video about iteration. In can be also used to check for belonging. Here, we check whether a character is a lowercase or uppercase letter by checking if it belongs to either the range of lowercase letters or the range of uppercase letters. The range check can be replaced with the explicit comparison with its bounds. Under the hood, the compiler generates exactly this code for in check. You can use not in, which checks whether an element is not in a range. You can use in as when condition, like in this example. Here we check whether a character is in a range of character numbers or is a letter. You can create ranges of different elements. It's clear what a range of integer number or a range of character means, but what about a range of strings? In fact, you can create a range of any comparable elements, like a range of your custom myDate class. You can store a range in a variable of the corresponding range type. Such range is a regular object. Note that under the hood, the int check for primitive types is optimized. No extra int range or char range objects are created. The similar optimization works for iteration over a range of primitives. Now let's talk about a range of strings. To better understand how it works, there is a question for you. What do you think is printed here? The result here is true for the first line and first for the second one. The second one is easy. We just check whether the string belongs to a set of strings and Kotlin string is not present in this set. That's false. To answer the first question, let's discuss how we compare strings. InCheck is compiled to the code simply checking its bounds. In Kotlin, we can compare strings like numbers via this nice syntax. Under the hood, the compare_to function is called. Like in Java, strings are compared lexicographically by default, or in other words, by the alphabetical order. That means we compare the first letters B goes after A, and only if they are the same, we compare the rest letters, first the second ones, then the third ones, etc. Thus, ball goes after A but before K. When we check whether ball is in this range, we compare ball with its bounds and get the corresponding result. In our task, we also compare the strings by their alphabetical order and get true as a result. K goes between J and S in the alphabet. You can define a range of any comparable elements. Let's say you have your custom_my_date class which implements comparable interface. In Java, to compare dates, you need to call compare_to function explicitly. It's not really readable, especially these comparisons to 0. In Kotlin, you can do better. You can replace compare_to call with direct date comparison. Note that this syntax is available for all the types implementing comparable. That means if Java class implements comparable, in Kotlin you can compare its instances using this nice syntax. Ranges help to improve this even more. You can replace the comparison within bounds with a range check. Again, the range check works with every comparable type. You can check whether an element belongs to a collection also using in keyword. Then is the same as calling contains on a list. In this video, we've discussed ranges. Our next topic is exceptions. In this video, we'll discuss exceptions. They are very similar to Java, with one important difference. Kotlin doesn't differentiate checked and unchecked exceptions. In Kotlin, you may or may not handle any exception, and your function doesn't need to specify which exception it can throw. The experience shown us that in Java rules for checked exceptions often require you to write a lot of meaningless code to rethrow or ignore exceptions, and these rules doesn't really help you to prevent possible errors. That's why in Kotlin this design decision was made, which is actually shared among many other modern Java languages. Throw is an expression in Kotlin. You can assign its result to a variable. In this case, if the number belongs to the range from 0 to 100, this number becomes the result of if expression. Otherwise, we throw an exception. You can assign throw to a variable of any type, which is very convenient, especially to use that in if or when branches. In Java, throw is a special construct which you can't assign to a variable. Try can catch an exception if it was thrown inside, check it for being of a specific type, and perform the corresponding actions. Like in Java, try simply rethrows an exception if its type wasn't listed. Unlike Java, in Kotlin, try is an expression. That means you can assign the result of try to a variable. Here we assign the result of parseInt function to a number variable if everything is okay. We return from the outer function if the exception was thrown. Instead of completing the function entirely from the catch block, we can assign null to a number variable as a result. There are no checked exceptions in Kotlin, so there is no need to specify this function throws at this exception. However, we have the throws annotation in Kotlin, and the question is, why do we need it? To better understand it, try to answer the following question. Is there a difference between calling the following foo and bar functions from Java? Foo and bar simply throw IO exception, which is a checked exception in Java. The only difference is the throws annotation for the bar function. Java code tries to call these functions inside a try block and catch IO exception. The possible options are: there is no difference, the Java code calling an annotated function foo compiles, but the code calling an annotated bar doesn't compile, and vice versa. The right answer is that the code calling the annotated function compiles, but the code calling the function without annotation doesn't compile. Let's look at the first Java example. Here we try to call foo from Java and catch our exception, but the Java compiler complains that exception is never thrown in the corresponding try block. In Java, you cannot catch a checked exception if it wasn't thrown. For this reason, when you throw a checked exception from Java point of view in Kotlin and want to later handle it in Java, you need to add this annotation. Note that if you only use a function throwing an exception in Kotlin, then you don't need the throws annotation at all. We've discussed exceptions in Kotlin, and that concludes our story about Kotlin basics. Next, we're going to discuss the feature that has no direct analogs in Java, but is crucial for providing good interoperability with existing Java libraries. That's extension functions. In this section, you will learn about extension functions. What are they? Why are they important? And you'll see some examples. Extension function extends the class. It is defined outside of the class but can be called as a regular member to this class. Here, we define an extension function to string called lastChar, and we can use it as a member function. It's visible in completion, so it can be easily discovered. It's like a regular utility function defined outside of the class, but on the other hand, thanks to completion, it can be easily found and used like it was a member. Let's discuss how we define an extension function. The type that the function extends is called a receiver. Here, string is the receiver of the lastChar function. In the body of this function, we can access the receiver by this reference. In our example, this refers to string. As usual for this reference, we can omit it. We can call members of the receiver inside an extension function without explicit this.something specification. An important thing to note here is that you can't define an extension and use it everywhere. You have to import it explicitly. If you define an extension function lastChar somewhere and need to use it, you have to import it either as one function or inside the whole contents of the package. By default, an extension function is not accessible in the whole project. It's visible in completion, but to use it you have to put the explicit import. You can ask how to call an extension from Java. As we've already discussed, when you call a top-level function from Java, it's simply a static function. For extensions, it works in the same way. When you call an extension function from Java, you call it as a regular static function. You can add a static import and call it without specification. Under the hood, it's just a regular static function. The question to you: how many arguments does this repeat extension function have if you call it from Java? It's an extension function to string which repeats the given string by the specified number of times. And the options are 1, 2, or 3. Under the hood, at the bytecode level, when this function is compiled to a static function, the receiver is transformed to the extra first parameter. When you call this extension function from Java, you pass string expression explicitly as the first argument. In Java, the code with extensions looks like regular Java. In Kotlin, all the utility functions become easily discoverable and the code overall looks nicer. Another question: what do you think? Is it possible to call a private member of the class inside an extension to this class? Here we use string as an example. The answers are simply yes or no. Of course, you cannot do it. As in Java, it's only possible to call a private member inside the same class. In Java, you can't call a private member from a static function defined outside of this class. Kotlin extension functions are most of the time top-level functions defined in a special extra file, which content is compiled to the corresponding extra class. Therefore, it's not possible to call a private member of a class from an extension to this class. Extension functions don't give you any additional access rights to the class contents. The main benefit of extensions is that you can call them in a nicer and more convenient way. You've learned how to declare and use extension function. Next, you'll see some more examples. In this video, you'll see some extensions defined in the standard library. In fact, you already saw most of them during the previous videos, but now you'll find out that they are actual extensions. Extensions play an important role in the language. In fact, Kotlin's standard library is just Java standard library and a bunch of extensions. That provides very smooth interoperability between Java code and Kotlin code. To illustrate that Java standard collections are used under the hood, let's create hashSet, arrayList, and hashMap in Kotlin and check the classes of the created instances. To check the class, we call Java class property. It's analogous to Java's set.get class. You can see that Java standard collection classes from java.util package are used under the hood. When you create a collection using the functions from the Kotlin standard library, instances of Java standard classes are created. The Kotlin library simply provides extensions for regular Java collections. There is no such thing as Kotlin SDK, it's just Java standard library plus a bunch of extensions. That gives us a couple of important benefits. At first, the size of the runtime jar that you have to add to your application when it starts using Kotlin is relatively small. The Kotlin doesn't duplicate the standard implementations from Java, it tries to reuse them. The Kotlin library simply adds a bunch of extensions. If your application doesn't use some of these extensions, they can be eliminated so that the added jar can get even smaller. The second important benefit is that using standard Java collections provides very easy interoperability with Java. You don't have to convert one collection type to another, they are the same types under the hood. If you call Java API from Kotlin or vice versa, you call Kotlin from Java, that's very easy. You don't have to introduce any additional conversions for collections. Everything just works. We've already seen the majority of these functions, but now you learn that they are defined as extensions. The join-to-string function allows you to get a nice string representation of a collection. In Java, the square brackets are added by default, which is not always what you need. Join-to-string allows you to change the default behavior by specifying the values for some of the arguments. It's a regular extension function from the Kotlin library. Another function is getOnNull. We used it in one of the first videos of this module. We called the getOnNull on array. I've told you that under the hood, Kotlin array is the same array as in Java, but Java array lacks this getOnNull method. In Kotlin, getOnNull is defined as an extension, and that's why we can call it on a regular Java array. The similar function is available for list. It returns either an element or null if your index is wrong and the list contains fewer elements. We saw the nice syntax for iterating over a collection with index. The withinIndex function is also an extension. We'll discuss later how exactly the syntax for iterating over two variables works. But the important thing for now is that withindex is a function that is also provided as an extension. Having extensions in a language allows us to get new nice syntactic features for standard Java types. Extensions are very powerful. Until is also an extension. The until function is defined as infix. You can either call it in a regular way, as in the first line, or you can call it in an infix form by omitting dot and parentheses. Until looks like a built-in syntax, but it's not. It's just an extension function called in an infix form. Another function that we've already seen that is also an infix extension is to function. To in Kotlin simply returns a pair of values. Again, you can use it in a regular form, but no one does that. Everybody uses nicer infix form. Why it's called to? When you create a map of values, it's very convenient to enumerate key-to-value pairs using to. And it turned out that it can be used in other use cases as well. Whenever you need a pair of values, you can create it with to. There are many useful extension functions on char like isLetter or isDigit. You can look at what is available in the library using the completion list or just browsing the library. Now I want to highlight some extensions available for strings. Under the hood, Kotlin string is Java langstring, and the Kotlin library provides a bunch of useful extensions for it. Triple quoted string literals is another interesting feature in Kotlin. An alternative way to call them is the multi-line strings. You can't use any special characters there, but you can use string templates inside them. If you try to format triple quoted strings in your code, you'll probably want to add the indent, but by default, this indent becomes the part of the string. There are some ways to crop this indent, and one of these ways is using the function trim margin. Here the default margin is used, but you can specify another margin prefix if needed. The margin prefix is automatically cut out together with the indent. You can call the trim indent function directly, like in the second example. If there is the same indent for all the lines in your string, it will be automatically removed. Both trim indent and trim margin functions are defined as extensions. Another useful extension is the toRegex function. You can convert a string to the regex class representing regular expressions. After that, you can call, for instance, matches method on this regular expression class. Note that for regular expressions, it's very convenient to use triple quoted strings. You don't need to escape special characters there, including the backslash. The regular expression often becomes shorter. Another useful group of extensions allows you to convert strings to numbers. ToInt and ToDouble extension functions will try to convert string representations to int and double accordingly. Note, however, that if you try to convert something that doesn't make sense to an integer, you'll get number format exception. But there is another extension available, ToInt or null, which returns null if the string cannot be converted to an integer. In this course on Coursera, we'll use the eek extension for small tasks in the Kotlin playground. It lets us test what's going on. It's defined as a very simple extension function which checks whether the receiver equals its argument. It prints OK if they are equal, or it prints an error if they are not. When you do a task, usually you have to make sure that all of these equality checks print OK. We'll use this simple function instead of a regular testing system for simplicity. Now the question for you. What do you think? What is the type of this A21 construct? The right type is pair. 2 doesn't represent a type, it's a function used to create a pair. Pair is a class defined in the Kotlin standard library. As I've said, the Kotlin library consists mostly of extensions, but we still need some new classes. The to function returns a pair of 2 values of the corresponding pair type. You've seen a lot of examples of extensions functions from the standard library. Next, we are going to talk about how extensions are resolved, which functions are called in different cases. In this video, you'll understand how extensions interact with inheritance and whether extensions can hide members. Let's say we have 2 classes, parent and child extends parent. We can define 2 similar extension functions, the first one to parent, the second one to child. We create an instance of a child and store it in a reference of the parent type. The question for you is, which foo function will be called in this case? We can reword it as what will be printed here. The options are parent or child. An important thing to keep in mind here is that extensions under the hood are regular Java static functions. Parent is printed here. The resolution of which function should be called works in a similar manner as for Java static functions. You can convert this example into Java and answer the same question for static functions. Under the hood, these extension functions are compiled to Java static functions. The first one takes parent as a parameter. The second one takes child as a parameter. When extension functions are compiled, the type of the receiver is transformed to the type of the first additional parameter. Java resolves static functions statically. It finds the right function to be called during the compilation. It only uses the type of the argument to choose the right function. Thus, the parent function is chosen here since the parent variable has the parent type. In general case, we don't know what is stored in the parent variable. It can be an instance of child or parent or another child, and that's why Java works this way. The actual stored object at runtime doesn't change anything because the function to be called is already chosen during compilation. In Kotlin, it works in the same way as for static functions. Because extensions are static functions under the hood, there is no override for extensions. They cannot be overridden in Kotlin. When the compiler chooses the right function to be called, it only uses the type of the receiver expression, not the actual stored value. Another interesting question is, what happens if we try to define an extension which duplicates a member? For instance, the string class has a member function get, which simply returns a character by its index. We try to define an extension with the same signature. What do you think will be printed here? The options are star, A, or B. The right answer is B. Member always wins. The indexation of string or list contents starts with 0 as in Java. So in this case, the character returned by the first index is B. If you try to define an extension with the same signature as a member, then you get a warning that an extension is shadowed, so the member will always be chosen instead. However, you can overload a member. If you define an extension with a different signature, different parameter types, or the different number of parameters, your new function will be called if it fits better. In this video, you've learned that extensions can't be overridden because they're resolved the same way as static Java methods. An extension can't hide a member completely, but can overload it. That concludes our story about extensions and the whole first module. In the next module, we're going to discuss the topics of nullability and functional programming. Stay tuned! Extensions are often named among the most important or lovable features of Kotlin. Why are they so important?
Well, extensions have proven to be one of the most useful abstraction features of Kotlin. And I think their main purpose is to keep your classes and interfaces APIs minimal. This is really important because this keeps the abstractions, the things you try to describe to model with your classes and interfaces understandable. So it's important to capture the essence of the abstraction with this small set of members that covers like the essential functionality, and all the auxiliary functions, all the utilities, convenience methods can be written as extensions calling to this public API. So this is the main principle. As an example, you can take the string class from the Kotlin library. So what's a string? Essentially, it's a collection of characters that can be indexed. So string has only a handful of methods, like take a length, take a character by index, so on and so forth. And everything else, like the huge number of utility methods available on the string, like everything about regular expressions, matching, splitting, so on and so forth, converting to uppercase, lowercase, and many, many more methods are all extensions. So you can clearly see what a string is, and then express everything else through its API. This is the main principle, and I think we should develop all our abstractions this way. So when you have this division, like members for intrinsic things and extensions for everything else, it makes sense to put them closer to each other so that it's easy to discover extensions in the code. So you can oversee, survey the entire API surface of your abstraction. So when you use extensions for your own classes, define them close to the class itself if they are general purpose. Of course, if you have something specific to a subdomain in your application, like in a different module, you have something specific to add to this class, then keep that extension there in the module where it belongs to, but still group extensions to the same class together.
What other use cases are extensions good for?
Another important situation you want to use extension in is when you don't control some class or interface because it sits in a library or it's in another module or something like this, but you still want to extend its API somehow. So through this, you can even extend the APIs of existing Java libraries. So even if something has no knowledge, no awareness of Kotlin at all, you can turn it into a Kotlin-like ergonomic, idiomatic API through simply adding a couple of extensions. And that's proven to be a very useful thing. So many existing Java libraries have companion libraries with a number of extensions that are useful in Kotlin code. So it's important, again, to group extensions together. When you extend some library or some particular class, just put all the logically connected extensions into the same file so that they're easily discoverable. And otherwise, you just have a nicer API basically for free.
Let's see how the mastermind task can be solved in a functional style. We have an incomplete solution where we need to fill the remaining parts. At first, we need to count the number of letters guessed right with their positions. The number of letters that occur at the same places both in secret and guess strings. The zip function is really helpful for that. When you zip two strings, it returns you a list of pairs, where each pair consists of the characters at the same places from these strings. We zip secret and guess. If any pair in the resulting list consists of two similar characters, that means this character is guessed correctly with its position. Thus, to count the number of right positions, we need to count the number of pairs where the first character from secret is equal to the second character from guess. That's the solution for counting right positions. After that, we need to count the number of wrong positions, letters that are guessed correctly but stay not in their correct positions. We first find the number of common letters, the letters that are overall guessed correctly, ignoring their positions. In the end, we'll just subtract the number of right positions from common letters to get the number of wrong positions. To find the number of common letters, we analyze each letter in our alphabet and see how many times it's present in the common letters set. Let's see how it works for an example first. Our first sample doesn't contain the repetitive letters. For each letter, we mark whether it's present in secret and guess, and then find the letters that are present in both strings. 1 means the letter is present in a string, 0 that it's not there. In our case, the common letters are B and C. Now let's check the more complicated sample with repetitive letters. We'll take the A character first and see how many times it occurs in secret and guess. It's repeated 3 times in secret and twice in guess. The minimum of these two numbers gives us the number of A occurrences in the common letters set. All the rest letters are found only in one of the strings, so for B, C and F the same counting gives 0 as a result. The resulting common letter set consists then only of 2 A's. Now it's time to complete the function implementation. We check for each letter how many times it occurs in secret and guess. Then we compare these numbers to get a minimum. To count the occurrences of each letter, we compare it with it, which refers to letters in a string. First letters in secret, then letters in guess. That gives us the desired implementation. We can check these samples to make sure it works for them. In this task, we need to check whether string is a valid identifier or not. I will show you a solution. Note that that is one of possible solutions, so that doesn't mean that other solutions are wrong or so. You may compare it with your way to do the same task and to choose the elements that probably you like, or sometimes learn something new. Let's start implementing this function with implementing a function that checks whether a character is a valid character inside a string. And such function is a good candidate to be defined as a local function and put inside is valid identifier because it does make sense outside of this context. As an illustration, so in this case it doesn't really matter, but as for illustration, let's define it as a local function. So we have is valid character, and we need to check that this character is either underscore or digit. We check whether a character is a valid digit by checking belonging to a range, or we should check whether it's a letter, and we also will use belonging to a range, and we check explicitly separately for lowercase letters and uppercase letters. So now we have this function, and what we need to do next is for every character in a string to check whether it's valid character or not, and if it's not valid character, then we return false, and otherwise return true as the result. So let's check our function, how it works, and we'll notice that we have forgotten something, and our output is not as expected. Because here you see we have true, but that should be false. We forgot that empty string shouldn't be valid identifier, and also valid identifier can't start with digit. Let's fix that now. We explicitly check that if string is empty or its first character is a digit, then we return false. Now let's check, everything should work. Now the output is as expected. The other thing that I want to mention here is that this task was used for you to practice working with the ranges here, all these checks. So that was kind of expected solution, but in real life you don't need to check that character is a digit in such a way. You can call isDigit, and we'll later discuss how this function is defined. And the same works with letters. You can check that character is letter, and also you see that we have isLetterDigit defined in the library, so in this case we can just use isLetterDigit. And again, we'll see that the output is as expected. That is my final solution. In this task, we need to change the sum function so it was defined as an extension. Because I use IntelliJ, I can cheat here and call an action, convert parameter to receiver, that automatically will do the job for me. I'm calling this action, and let's see what has changed. At first, our function is defined as an extension, so our list became the receiver. Now we access this list by this reference inside the function body. And also the way how we call the function changed, because now we call it as an extension, and it looks like it was a member. Note that there is a reward detection. Also, you can say convert receiver to parameter. You can use this convert parameter to receiver and convert receiver to parameter for your own functions as well, when you, for instance, want to convert a regular function to an extension. In the first section of this module, called Nullability, we are going to discuss nullable types in Kotlin. The problem of nullability is sometimes referred as billion-dollar mistake. That's how Sir Tony Hoare, the inventor of null reference, later called his invention. The problem is that these null pointer exceptions problems are really hard to fix. And even if you go for details, you often can see just, sorry, null pointer exception was thrown. And the current approach, the modern approach, which is not unique to Kotlin, is to convert these problems, these exceptions, from runtime exceptions to compile time errors, to make it compile time problems, so that we could prevent these exceptions when we write the code and compile it, rather than later in production. Kotlin distinguishes nullable types and non-nullable types. If you use a regular type like string, you can only store non-nullable objects there. You can't store null references. If you try to initialize a variable of a non-nullable type with null, the Kotlin compiler will complain. If you want to store null, you need to declare a variable of a nullable type. To make a type nullable, add a question mark and at the end of its name. In this example, after adding a question mark to string, you can store either null or non-null string value there. If you try to dereference a variable of a non-nullable type, namely access its members or call extensions, everything is fine. The Kotlin compiler doesn't complain because it's sure that the exact value is not null. However, If you try to dereference a variable of a nullable type, the Kotlin compiler says it's not possible. The value of the nullable type can be null under the hood, and such dereference operation will then throw null pointer exception. What can you do if you want to dereference an object of a nullable type? The easiest way is to check explicitly that your reference is not null. After such check, you can simply dereference the variable and access its members. However, IDE will suggest you a better way to express the same logic. You can replace if expression with safe access expression. Safe access, or in other words, safe call, consists of two characters, the question mark and the dot. It allows you to dereference a value in a safe manner. This operator first checks whether the receiver is not null. If it's the case, then safe access operator calls the required member and returns the result. If the receiver is null, then null becomes the result. When you use the result of a safe call, like return it or assign it to a variable, that is the same as using the following explicit if expression. The question for you is, what is the type of length variable in this example? What do you think? The answer is nullable int. The length property of string returns you a variable of int type, but when you use safe access, that makes the result nullable. If S variable stores null, length will also be null. Because null might be stored only in variables of nullable types, the result type is nullable int. If you want to make the type of length non-nullable, you'll need to provide the default value for the case when S is null. When using if expression, you can simply say else 0. When using safe access, you can use so-called else operator and provide the default value that will be used when your expression is null. The following scheme illustrates how else operator works. The result is either the left expression if it's not null, or the right expression if the left expression is null. Why it's called like this? You can guess it if you read the operator as an emoticon. Else operator isn't a Kotlin invention. This name comes from Groovy. The whole bunch of nullability operators, including else operator, come from Groovy. They are proven to be very useful for working with expressions that can be null. The next question for you is, what will be printed here? In the first line, we sum up 0 and 2, having 2 as a result. In the second line, because b is not null, we sum up 1 and 2, having 3 as the result. So the answer is 23. Let's now go back to our discussion of how we can work with expressions of nullable types. The Kotlin compiler supports the control flow analysis. If you explicitly check that the reference is null and call fail function, which throws an exception, or simply return, then afterward you can access it without safe access. The compiler knows that S variable is smart cast to a non-nullable type. If you want, you can explicitly throw Kotlin null pointer exception. For this, you use this not null assertion, an operator consisting of 2 exclamation marks. It throws null pointer exception if its operand is null and returns the operand if it's not null. Note that after not null assertion, the value is smart cast to non-nullable type, and you can dereference it safely without the need to repeat this assertion. It's worth to warn against not null assertion operator. By default, try to avoid it. We have it in the language especially for rather rare use cases when the Kotlin compiler isn't smart enough to infer the right type. There are situations when you have an assumption that the expression is not null, but the Kotlin compiler cannot infer that for you, and you would rather prefer an exception if for some reason the assumption is not correct. The logic of assumption must then be localized so that it was hard to break it, or it can depend on external frameworks. In this example, the action performed function is called only if the isEnabled function returns true, and we can safely use not null assertion because the condition is checked is in another place. With not null assertion operator, you explicitly emphasize where null pointer exception can be thrown. And if it's thrown, you can see directly what might be the cause. That means it doesn't make sense to put two or more not null assertion operators in one line, as you won't be able to say which one caused the exception. In general, prefer using safe operators, safe access, Elvis operator, or explicit checks to cope with nullability. Use not null assertion only with care. The question for you to get used to nullable types is which lines won't compile, which lines will produce compiler errors. Let's do it one by one. The first function takes the parameter of non-nullable type. The function is fine, but the problem is that we can't pass null whenever a non-nullable type is expected. The compiler error tells us that null cannot be a value of a non-nullable type name. If passing null to a non-nullable parameter was allowed, then we would have a null pointer exception on dereferencing. The Kotlin compiler doesn't allow that. Let's now look at the second function, which makes the parameter type nullable. Now the invocation is fine, it compiles. However, there is an error in the function body. Only safe call or non-null asserted call are allowed. You can't access expressions of nullable types without additional checks, so the line number 2 doesn't compile. The third function fixes this problem, and this one is fine. We check explicitly that name is not null and then use smart cast value. The fourth function also compiles because we use safe access to get the value and then we compare it to the string. Everything is fine. Thus, the right answer is lines 2 and 5 don't compile. Another question for you. This one is not trivial. Such code might be confusing and sometimes called a puzzler. What will be printed here? The answer is rather unexpected, keep that in mind. The possible options are 1, 2, or 3. The right answer is 1. Operator precedence plays an important role here. If you omit the parentheses, some operator takes higher precedence than the Elvis operator. That means that by default the parentheses surround plus, not Elvis operator. If you want to call Elvis operator first, then you put the parentheses explicitly. If you are not sure about the right operator precedence and to make the code more readable, prefer the parentheses in all such confusing use cases. Now you know how to distinguish nullable types from non-nullable types, that only an expression of nullable types can store null references. You know how to work with them. You can use safe access operator, Elvis operator. You can enjoy smartcast or even prefer throw null pointer exception, but you have to use explicit syntax for that. Next, we're going to uncover the details and learn how nullable types are implemented under the hood. In this video, you'll learn how nullable types are implemented at the bytecode level. Also, we'll look at nullability and generics, and you'll learn the difference between a list of nullable values and a nullable list. Under the hood, nullable types are implemented using annotations. The Kotlin compiler simply adds nullable and not null annotations to the corresponding type usages, which gives us no performance overhead when using nullable types. There is another solution to the same nullability problem, which is called optional or option types. They are special library classes that store a value or absence of the value, and you can check whether the value is available or not. That solves the same problem as nullable types, because optionals allow you to say explicitly whether the variable can have no value option similar to null or not. Despite nullable types and optionals solve the same problem, they are very different in terms of the performance. Optional type is a wrapper that stores the reference to the initial object. For each optional value, an extra object is created. At the same time, nullable types don't create any wrappers. They are implemented via annotations. To make sure you understand it, answer this question. How many objects are created to store the value of a nullable string? The answer options are either 2 objects or only 1. only one object is created to store string value. There is no additional wrapper as with optionals. When you use nullable types under the hood, the Kotlin compiler adds additional annotations which are only checked at the compilation time. At runtime, nullable string is the same string as regular Java string. Both types, string and nullable string, correspond to Java-like string type in Java, but with different annotations. At runtime, it's one string. There is no wrapper. All the checks going on at the compilation time with the help of annotations. That's the end of the first story. Now another story not about annotations, but about nullability and generics. In this picture, you can see the difference between a list of nullable elements and a nullable list. When you use a list of ints, you can put the question mark after int, or after list itself, or in both places. The first one means that every element might be either null or not null. And the second one means that the whole list might be either null or not null. To better understand that, mark the lines that need a question mark to make the code compile. Of course, you can add a question mark to each line to make every access safe and make every int nullable int, but that's not the question. The question is, which are the minimum amount of question marks to make this compile? Add only the question marks that are really needed. Let's do the cases one by one. The first list is the list of nullable values. We can dereference it without a problem because it's a not null reference. But when we try to assign the first element into a variable, we see an error. The inferred type is nullable int, but int was expected. The content of the list is nullable ints, and the type of the first element is nullable int. That means that we need to add a question mark to the type of the I variable. That's all for the first list. For the second case, it's a little bit more complicated. We have a nullable list, and that means that both accesses won't compile. We need here safe access. We can add a couple of question marks to fix that. And now here is a tricky place because we've added a question mark that makes line 6 uncompiled. We have the type mismatch. Inferred type is nullable int, but regular int was expected. That makes us add another question mark to line 5. So the answer is lines 2, 3, 5, and 6.
In this video, you've learned that nullable types are implemented using annotations. That brings no performance overhead. Also, now you can confidently use question mark to mark either the list element type as nullable or the list itself. Next, we are going to look at the new operator that makes typecasts safe in Kotlin. In this video, you'll learn another language construct that uses question mark, a safe way to cast an expression to a type.
In Java, you use a common pattern to do something with a variable only if it is of specific type. First, you use instance of to check whether the variable is of the required type. Then you cast it to this type, often storing the result in a new variable. And eventually, you call members of this type on this new variable. In Kotlin, you can do absolutely the same. Is the analog of instance of, and as is the typecast. However, the explicit cast as is not really needed. You can simply use the initial variable afterward because it's smart cast to the right type. In this case, you can call string members on the any variable directly. And this example can be further improved. You can replace typecast with a safe cast. Typecast as throws an exception if the expression can't be cast, while safecast as question mark returns null in this case. The safecast returns you either the smart cast value or null as the result. If the value can be cast to the required type, then it is returned. Another way to express the same logic is to use if expression explicitly returning either the same expression or null. To better understand the difference between safecast and the cast to a nullable type, solve the next task in the Kotlin playground right after the video. You need to declare a variable so that the first line printed null and the second one threw an exception. Afterward, you can check the solution in the solution video.
Now you know how to use safe operators in Kotlin. the ones that allow you to return null if something went wrong instead of throwing an exception. The same approach might be beneficial in regular code as well. For instance, you may prefer to call a function to int or null on string, which returns you nullable value as a result, instead of calling a function to string, which can throw an exception. That mostly concludes our discussion about nullable types in Kotlin. We'll later also discuss how you can mix nullable types and Java. But for now, the next big topic for this module is functional programming. Why nullability is so important?
Nullability in the type system is also one of the key features of Kotlin. It's important because there are a lot of nulls around us. The introduction of null to earlier programming languages is known to be called a $1 billion mistake because nulls are ubiquitous and null pointer exceptions, attempts to dereference null pointers, are very common as an issue. Like so many stack traces that you collect from any application will be null pointer exceptions. And of course, it's something that occurs so often that it's worth controlling better, like not overlooking such exceptions, or at least the possibility of having such an exception makes a lot of sense. So this is why we support control for nullability in the type system itself and not like in a library or somewhere. So we tried to integrate this as a very small number of language features that are tightly connected together. We have non-null and nullable types and a handful of operators that help you work with nullability. Plus, there are smart casts and so on and so forth. So this machinery makes it easy to control nulls and also makes a null a first-class citizen, basically, in the language. Because before, like if you don't have this control in the type system, it's an outlaw. Using nulls for representing absence of things is an anti-pattern. And in Kotlin, it's a legitimate pattern. You can use it because the type system helps you track it. There is an important distinction in the approaches of tracking absences of things in different languages. One could think of creating like an option type, for example, or optional. That's a class that wraps something and just represents existence or absence of this something, like an optional of t, right? So the biggest difference between the nullable types in Kotlin and this optional is that in Kotlin, we don't have to wrap anything. So there is no extra object around your payload, for one thing. And then there is an important distinction regarding subtyping. So if you have a nullable type in Kotlin somewhere, then you can take a non-null value and simply assign there. With optional, it doesn't work this way. If you have an optional of string, you cannot simply assign a string into it. You have to wrap it first, right? It makes many manipulations with types a lot smoother in Kotlin. So I guess this is one of the most successful features in Kotlin. So it's proven to be a really useful and relevant one for real-life programming.
In this section, we are going to discuss functional programming. You'll learn how to write code in a functional style in Kotlin. In this video, you'll learn how to define and use lambdas. Lambda is an anonymous function that can be used as an expression. For instance, passed as an argument to another function invocation. In older versions of Java, anonymous classes were used for the same purpose. Modern JVM languages, including Kotlin, as well as Java starting from Java 8, support lambdas, which provide more concise syntax for the same functionality. Having lambdas in a language also makes it possible to work with collections in a functional style. You can use such functions as filter or map, which make the overall code more readable. We'll discuss these functions in detail soon. First, let's focus on the lambda syntax. In Kotlin, lambda always goes in curly braces. To distinguish regular curly braces, for instance for if expression, from curly braces used in lambdas, ID highlights in bold curly braces for lambdas. When you see highlighted in bold curly braces, that means you see a lambda. Inside curly braces, first you specify the parameters, then the arrow, then the lambda body. If you pass a lambda as an argument, you can put the whole lambda inside the parentheses. However, there is a better way to express that. You can move lambda out of parentheses if the lambda is the last argument. And if the parentheses are empty, you can omit them. This way you have the nicer syntax. At first, the same syntactic convention of moving lambda out of parentheses was used in Groovy, and it worked quite well there. Kotlin reuses the same idea, which is proven to be really convenient. If the type of the argument can be inferred, if it's clear from the context, it can be omitted. If your lambda has the only argument, you can replace its name with it. It's an automatically generated name for your lambda if it has only one argument and you don't specify a different argument name. If you want to express some complicated logic and need a multi-line lambda, then you just write several lines of code inside the parentheses, and the last expression of this lambda is the result. I want to highlight another mostly syntactic feature. If your lambda takes a pair of values as an argument, or as in this case map entry, you can use so-called destructuring syntax. The same syntax was used to iterate over map in a for loop, by assigning a key and a value to separate variables. We'll discuss in the next module how exactly this destructuring syntax works, but the usage is quite straightforward. Instead of declaring one lambda parameter entry, you can declare two parameters at once, but put them inside extra parentheses. The compiler will automatically destruct entry into key and value. That's quite convenient. Many functions take map entry as an argument, and you can use this nicer syntax to work with such functions. If one of the lambda parameters is not used, you can replace its name with the underscore. It's more readable, and you don't need to invent a name for the parameter if it's not used.
You've learned the syntax for lambdas. You now know that you can move a lambda out of the parentheses, use it if it's the only argument, or use destructuring declaration syntax if one of the arguments is map entry or pair. Next, we're going to discuss the common operations on collections. In this video, you'll learn the common operations that are used for working with collections in a functional style.
As we've already discussed, the Kotlin standard library consists mostly of extensions on Java collections. A lot of these extensions work with the collections in a functional style and use lambdas. For instance, filter and map are defined in the Kotlin standard library as extension functions. Now, we'll discuss the most common operations and how exactly do they behave. Let's start with filter. It filters out the content of the list and keeps only the elements that satisfy the given predicate. In this case, we have the predicate checking that a number is even, and only even numbers are present in the resulting list. Map transforms each element in a collection and stores all the resulting elements in a new list. Here we find a square of each given number, and the result is a list of squares. Note that the resulting list contains as many elements as the initial collection. There are several predicates checking whether the given facts about the elements are true. For instance, any checks that there is at least one element satisfying the given predicate. Here we check whether there is at least one even number in the list and the result is true. All checks whether all elements satisfy the predicate, and none makes sure that none of the elements satisfies the given predicate. Find finds an element satisfying the given predicate and returns it as the result. If there is no required element, find returns null. You can use another name for the same predicate. The synonymous function is called first or null. First or null does the same as find. It returns you an element or null as a result. First takes a predicate and throws an exception if no element satisfying the predicate was found. Count counts the number of elements that satisfy the given predicate. Partition divides the collection into two collections. Filter returns only the elements that satisfy the predicate, and in a sense throws out all the elements that don't satisfy the predicate. If you need to keep both groups of elements that satisfy or do not satisfy the predicate, you can use the partition. It returns two collections for the good elements and the remaining ones. If you need to divide your collection into more than two groups, you can use group by. As an argument, you provide the way how to group the elements, what should be the grouping key. For instance, here we group person elements by their age. The result is map from the given key to a list of elements that satisfy this key. Here, the result is a map from the age to a list of all people of this age. That's often the case that as a result of grouping, you will prefer one element instead of a list. If the key is unique, then it's more useful to have a map of the key to this unique element as a result. That's what the associate by function does for you. It also performs grouping, but it returns you one element as the map value. Note that associate by should be used when the key is unique. If it's not, pay attention that duplicates are removed, so the last element will be chosen. If your key isn't unique, it's safer to use group by to avoid losing some of the elements. You can use associate to build a map based on a list. As an argument, you pass a lambda creating a key-value pair based on each list element. Then associate builds a map by filling in specified keys and values. The first value in a pair becomes key in the map, the second becomes the value. Here, a plus it specifies how to create keys, while 10 multiply it is the way to create values. Note that it's often convenient to use the list element as a key and provide a way to fetch the value in the lambda. Zip provides you with a way to organize a couple of lists. It zips like a zipper the elements from two lists. It returns you a list of pairs where each pair contains one element from the first list and another element from the second list. If the initial lists have different sizes, then the resulting list of pairs will have the lengths of the shortest list. The remaining elements from the longest list will be ignored. The frequent use case is to zip neighboring elements in the list. That can be done with the help of the zip with next function. It returns you a list of pairs where each pair consists of neighboring elements from the initial list. Note that each element except the first and the last one will belong to two pairs. Like 3 in this example is the second element in the second pair and the first element in the third pair. Both zip and zip with next have overloaded versions taking a lambda as an argument that specifies how each pair of elements must be transformed. Flatten is an extension function that must be called on a list of lists. It combines all the elements from the nested list and returns you a list of these elements as the result. We can say it flattens the list of lists contents. Another useful function is flat map. It combines two operations, map and flatten. The argument to flat map must be a lambda that converts each initial element to a list. Here we first map each string to a list of characters. In the middle layer, after applying the first map operations, we have a list of lists. Often you would prefer a list of elements as a result instead, and flatten does that. Here, flat map returns a list of characters obtained from initial strings.
You've learned the common functions used for manipulating collections. Next, you'll have the video quiz to practice to read and understand these functions in action. In this video, you can practice your understanding of what the common operations on collections do. We'll have a lot of examples of operations in use, and each question will be followed by an explanation.
In this quiz, we'll use the class Hero. It has name, age, and gender properties. Gender might be male or female, or if it's unspecified, then null is stored. We will use the following values that are specified in the list. Your task for most of the questions will be to find the result of the expression. These heroes are based on the card game Lifeboat. The first task is to find the result of this first expression. The answer is Sir Stephen. We obtain the last element in the list and then we get its name. The Kotlin standard library contains useful functions. First, last, also first to null and last to null. First and last throw an exception if there are no elements, and first to null and last to null return null if the list is empty. All these functions are overloaded and are available as the functions with predicates. Here, we use the last function without arguments, but there is a similar one that takes a lambda as an argument. For instance, here, what is the result? The result is null because there is no element satisfying the given predicate. There is no hero of age 30. First to null returns null, then we use safe access, and null is returned as the result of the whole expression. If we use the first function with the predicate, then we'll get no such element exception as a result. First must return no nullable element, so when there is no required element, it can only throw an exception. The next question uses the function that we haven't yet discussed, but I think you can guess what it is doing by its name. Distinct function returns you only the elements which are distinct, different. Let's see step by step what is going on in this example. First, we map the heroes to a list of their ages. Then, we call distinct on it. It returns a new list which contains only non-repetitive elements. In this case, the duplicate of 29 was removed. At last, we get the size of the resulting list, which is 5. The next question uses the filter function. Here, filter returns all the heroes whose age is less than 30. There are 3 such elements, so the result is 3. The next question is about partition. We use the partition function that divides a list of elements into 2 lists. The first list contains the elements that satisfy the predicate, heroes that are younger than 30. The second list contains all the rest elements, heroes that are not younger than 30. In our case, the size of both lists is 3. The next question employs the function maxBy. You can use maxBy and minBy functions if the elements are not comparable themselves, but they can be compared by a property or in another specified way. Here we compare elements by comparing the corresponding values of the age property. We find the maximum by comparing ages. This maxBy function returns the first element with the maximum value of the property or null if the collection is empty. Here we find the oldest hero, which is the captain. His name is the result. The next question is about predicates. We use all function. The result is false. We check whether all the heroes are younger than 50. That's not true because we have the captain who is older. The next question is about the any predicate. The answer is true. We check whether any element in the collection satisfies the given predicate. There is the hero Lady Lauren, which specifies female gender, and therefore satisfies this predicate. Let's continue the quiz. The next question uses the function groupBy. What is printed here? Let's look at this example step by step and understand what's going on here. When we group elements by their ages, the groupBy returns a map from the age to a list of heroes of this age. Then we call maxBy on a resulting map. It finds the entry with the maximum value of the provided expression, in this case group size. Here the maximum group size is 2 elements for the age 29. Thus maxBy function will return 29 as the age and the highlighted list as the corresponding group. We print age and it's 29. The next question uses the function associateBy. Now we group the elements by their names by using the associateBy function. In our case, the name property is a unique key. The resulting map is the map from name to hero object. We access the element by the name Frenchy and get his age. He's 42. I want to highlight here 2 different ways to access elements in a map. You can either use square brackets or map getValue function to access the specific element. The access via square brackets returns null as a result. Here you see that to access h later we use save call operator. GetValue function will throw no such element exception if there is no such element. You don't need to use save access afterward, but you see that the exception might be thrown. The next example builds a map using the associate function and illustrates how get_or_else works. What is the result of the last expression? The associate function builds a map creating a key-value pair from each element list. In this case, it builds a map from int to string, from names to ages. The get_or_else function returns the value corresponding to the given key, if the key is present in the map. Otherwise, it computes the provided lambda and returns the result of this lambda. It's a very useful function because if the element is already present in the map, then nothing will be computed. The default value passed inside the lambda will be calculated only if needed. In this case, it's needed, and the get_or_else function returns 0 since unknown key is not present in the map. The next question is much less straightforward than the previous ones. It tries to illustrate how the code should not be written with lambdas. It's an example of bad code which is hard to read. You can spend some time trying to understand what's going on here and guess the answer. If it takes too much time, just check the result. Let's gradually note what are the problems here. At first, we use it in two neighboring lines, but it in the first line has a different type from it in the second line. We have the same name because of the syntactic convention that you can replace one argument with it, but these arguments in two different lambdas have different types, and that is really confusing. Just don't write code like this. To fix that, let's replace the first it with an explicit parameter, and then try to understand what's going on. We call flatMap on heroes. At first, it builds a list of pairs corresponding to each hero, then it flattens all the pairs. Let's replace hero parameter name with second to highlight that we are building pairs of heroes. The list corresponding to the first element, the captain, will contain all combinations of two hero elements where the captain is the first element. The similar list will correspond to the second element, Frenchie, and so on. The unification of all such lists and flattening it will produce the list of all possible pairs. Thus, the flatMap call here constructs the list of all possible pairs of heroes. Now we can extract it to a variable and give it the explicit name, all possible pairs. Now it's easier to understand what's going on here. This code is better. Now let's continue and look at the next line. We call maxBy on all possible pairs. The maxBy function returns a nullable pair, which we then assign to two variables, similar to how we assigned a pair to two variables in the update weather function in the very first video. We need not null assertion here to make the resulting pair non-nullable, to be able to destructure and assign it in this way. We'll discuss in detail the syntax for destructuring declarations in the next module. maxBy finds the maximum of all differences in ages of two heroes in one pair, but maximum of the age differences will be reached for pair consisting of the oldest and the youngest heroes. Basically, these first and second are just oldest and youngest. The maximum difference in ages gives us the maximum and the minimum ages. The whole piece of code might be replaced with finding the oldest and the youngest heroes. Since we don't really use the youngest in this example, we can only find the oldest. His name is the captain, and that's the result that is printed. The main point of this task was to illustrate an example of badly written code so that in the future you could avoid it and try to write your code so that it was readable and comprehensible. To sum up what we saw in this last example, there are some pieces of advice on what could be done in order to improve readability. At first, we have this problem with it variable. Try not to use it if it has different types in neighboring lines. The it parameter name is good if the lambda is trivial and straightforward, but if it's going to be more complicated, for instance in multi-line lambdas, it's often better to use explicit parameters. In any case, when any confusion is possible, prefer using explicit parameter names so that the code was easier to understand. The last thing to note here is it's a good idea to learn the library, to know it and not try to re-implement all the methods. It's often possible to find the function that will do the job for you.
Congratulations! You've practiced your understanding of the common operations for working with collections in a functional style. To learn more, you can read the documentation or just go through the completion list to see what other operations are available. Next, we are going to discuss the type of the lambda expression. In this video, you'll learn about function types. We'll also discuss how you can pass lambda as an argument to a Java method, and also touch a topic of function types and nullability.
In Kotlin, you can store a lambda in a variable. Which type does the variable have in this case? If we specify this type explicitly, we'll see a so-called function type. First, parameter types are written inside the parentheses, then an arrow, then the return type. In this case, it's the type that takes two integer parameters and returns an integer as a result. What will be the type of is-even variable here? In this case, we have a lambda that takes int as a parameter and returns boolean as a result. You can see the corresponding function type. Note the difference between storing a lambda and storing the result of applying this lambda. Lambda is the whole function containing the logic of how to compute the boolean result from the given int argument, while the result is simply a boolean value. You can call a variable of function type as a regular function, providing all the necessary arguments. In this case, you call a variable is-even as it was a regular function is-even. To call a lambda stored in a variable might be convenient if you want to postpone calling a lambda. Store it somewhere and call it only later. When you store a lambda in a variable, you can pass this variable whenever an expression of function type is expected. For instance, to all the functions working with collections in a functional style like any or filter. You can even call a lambda directly, putting parentheses right after lambda's curly braces. However, such invocation looks a bit strange. If you need to call a lambda right in place, better use run. The version with run does exactly the same, but it's much more readable than the code above. In Java, you can pass a lambda instead of a SAM interface, an interface with only one single abstract method. In Kotlin, you can use the function types directly, but when you mix Kotlin and Java, you'd want to do the same as in Java. Whenever you call a method that takes SAM interface as a parameter, you can pass a lambda as an argument to this method instead. In Kotlin, if you want to create an instance of such interface explicitly, you can use the auto-generated SAM constructor, like in this case, runnable, and pass a lambda as its only argument. Now let's talk about function types and nullability. I want to highlight the difference between function type that returns nullable value and nullable function type. To better understand that, answer which lines here don't compile. What is the difference between these two types? The first one means that return type is nullable. That's a possible mistake when you simply add a question mark after the function type. It means that you make the return type of this function type nullable, not the whole type itself. If you want to make the whole type nullable, you need to use the parentheses. In the example, you saw null in curly braces. It's a lambda without arguments that always returns null. The next line shows the variable which can store either null reference or a lambda returning int value. Let's go back to the task. The first line doesn't compile because you can't store null in a variable of a non-nullable type. To store null, you need to declare a variable of a nullable type, as in line 3. The second line is fine because you need to hear a lambda that can return nullable int. The lambda in the second line always returns null, so it fits. The last line doesn't compile, because the compiler expects a lambda that returns only integer values. But here we try to assign there a lambda which returns null. That is not allowed. You can ask how you should call a variable of a nullable function type. You can't call it as a regular function because it's nullable. So which options do you have? You can check the variable explicitly for being not null. Then you can simply call it because smartcast applies here, and the value is smartcast to the value of non-nullable type. An alternative is to use the safe access syntax. But in this case, you call a variable of function type by calling its invoke function. Each variable of function type can be called via invoke, but regularly you don't need that, since there is a simpler alternative, the syntax to call it directly.
You've learned about function types. Next, we are going to discuss how trivial lambdas might be replaced with member references. In this video, you'll learn about member references, and we'll discuss what is the difference between bound and unbound references.
Like Java, Kotlin has member references, which can replace simple lambdas that only call a member function or return a member property. IDE can convert lambda to a member reference automatically when it's possible. The syntax for member reference is the same as in Java. First goes the class name, then the double colon, then the member which we refer. As we've previously discussed, in Kotlin, you can store a lambda in a variable. However, you can't store a function in a variable. It's not like in a truly functional language where each function is a variable. No, in Kotlin, there is a clear distinction between functions and variables. That's connected with how JVM works under the hood. If you try to assign a function to a variable, you'll get a compiler error. To fix this issue, use the function reference syntax. Function references allow you to store a reference to any defined function in a variable to be able to store it and call it later. Keep in mind that this syntax is just another way to call a function inside a lambda. Underlying implementations are the same. Here, the full analogous syntax is a lambda that only calls the isEven function. If a referred member is a property, or it's a function that takes 0 or 1 argument, then member reference syntax isn't that concise in comparison with the explicit lambda syntax. However, if the referred function takes several arguments, you have to repeat all the parameter names as lambda parameters, and then explicitly parse them through. That makes the syntax verbose. Member references allow you to hide all the parameters because the compiler infers the types for you. You can parse a function reference as an argument. Whenever your lambda tends to grow too large and to become too complicated, it makes sense to extract the lambda code into a separate function. Then you use a reference to this function instead of a huge lambda. Now I want to highlight the difference between bound and non-bound references. In Kotlin, you can create a bound reference. Let's discuss what it is. In this example, we use a regular non-bound reference, which refers to a member of the person class. If we check what type this member reference has, we see that the first argument of this function type is person. Whenever we want to call this variable of function type, we need to parse the person instance explicitly. If we look under the hood and check what lambda does correspond to this member reference, we'll find that this lambda takes 2 arguments, person and age limit. It simply calls the member function is older inside on a parsed person element. This reference is called non-bound, since it's not bound to any specific instance. You can call it on any objects of the person class. Bound reference is a member reference that is attached to a specific instance of the class. Here, the alias variable is an instance of the class person, and we can bound a member reference to this specific instance. If we look at the type of the bound member reference, we see that now there is no person parameter because the person instance is already set. the isOlder function takes int as a parameter, and the bound reference also expects only int as an argument. If we check which lambda corresponds to this member reference under the hood, we'll find the lambda that calls the member isOlder on the bound instance. In this case, this bound instance is Alice variable. Member references can be bound to this reference. Here, we return a predicate directly from the class person. This predicate is a member reference to isOlder function. This is the object which this member reference is bound to, and as usual for this, we can omit it. Now we have this nice short syntax without left-hand side, just a reference to the member. To make sure you understand it, answer this question. What is the type of this member reference here? We have two options, either taking person or without person as an argument. The right answer is the second one. It is a bound reference which stores the person, this instance, inside. The reference will always be bound to a specific instance of the person class. We can call getAgePredicate only on a specific instance, which becomes the bound object for member reference. Another question for you. Is isEven in this example a bound reference or not? Yes or no are the possible answers. The answer is no, because here it's just a reference to a top-level function. There is no stored object which this function is bound to. Whenever you see the function reference without the left-hand side, it's either a reference to a top-level function or a bound reference. In IDE, you can always navigate and see which function this function reference refers to. It's very convenient.
Now you can use both bound and unbound references in your code. Bound references store the object on which the member can be later called, while unbound references might be called on any object of a given type. Next, we are going to demystify one of the common puzzlers which may occur if you use return expression inside a lambda. In this video, you'll learn what does return expression inside a lambda do, why it works like that, and how to safely use it for your purposes.
Let's start with an example that sometimes might be really confusing. It's a puzzler, so you can expect something surprising as a result. The duplicate non-zero function is intended to duplicate all the elements except 0. The question is, what does it produce as a result? You can try to guess what's going on, and later we'll discuss the details. The options are: a list of lists is the result, the same list but flattened, or in other words, the list of all the non-zero elements, or an empty list. The right answer here is an empty list, which is really unexpected. You can easily write similar code and expect this function to print duplicated non-zero elements. Let's see what's going on here. Return in Kotlin always returns from a function marked with fun. That's something you may consider as a rule. It explains an empty list here as a result. When the function finds 0 element, it returns an empty list, but it returns an empty list from the whole function. That's why an empty list is printed out as a result. Let's discuss why it works this way. Why in Kotlin return returns from the outer function? Consider the following example when you have a regular for loop, and inside this for loop you use return. Return simply returns from the function. If you convert the for loop to for each, then you kind of expect that return continue to behave in the same way. Return inside for each returns from the whole function as well. In this scenario, we are glad that return returns from the whole function, not from the lambda. That explains the motivation of why it works like this. A lot of functions in Kotlin, like for each, behave like language constructs, and we want to provide such almost language construct experience. What can you do if you need to return from a lambda? You can use the labeled return syntax. Here, the labeled return will return from the corresponding lambda. By default, you can use the name of the function that calls this lambda as a label. But if you want, you can specify any label name. Put it right before the lambda followed by @. Here we provide the custom name, just L, to label the lambda. You then use this name in a labeled return. Now the duplicate non-zero function implementation uses labels. It returns what we expect, the flattened list of duplicated non-zero numbers. There is another solution to the same problem. Instead of lambda, you can use a local function and then pass a reference to this local function. In this case, return behaves as expected. It returns from the local function marked with the fun keyword. Another alternative solution is to use an anonymous function. If you don't want to invent a name for a local function, you can use an anonymous function instead. You can define an anonymous function in place, similar to the lambda when you pass it as an argument. In essence, it's simply an alternative syntax for lambdas. The under-the-hood implementation, the compiled bytecode, will be the same for lambda and an anonymous function. The only difference is syntactic. You can now use return, which returns from the anonymous function marked with the fun keyword. What's more, you can specify the return type for an anonymous function, which is not possible for a lambda. Sometimes it's possible to simply avoid return. In this case, we use the result of if instead of return, and we get what we expect as a result. One more question to you. What do you think? Does labeled return inside for each correspond to break or continue inside for a loop? The right answer is continue. Break stops the for loop completely, while continue stops only the current iteration and goes to the next one. Like continue, return from a lambda only stops the current iteration, the current lambda, but doesn't stop the whole loop. Note that the regular return doesn't correspond to break. They are the same only if the for each iteration or for loop is the last statement in the function. Otherwise, they differ in whether the statements following right afterward are called. Return returns from the whole function, while break completes only the for loop iteration. There is no direct analog to break other than extracting the for each call to a separate function.
This explanation of how to use return inside lambda completes our discussion of functional programming so far. Later in the course, we'll return to the topic of operations on collections and discuss inlining and the difference between eager and lazy iteration. Our next module will focus on object-oriented programming in Kotlin, which has some small differences with Java. Would you call Kotlin a functional language?
Well, it's not so easy to define what a functional language is for practical purposes. Kotlin is definitely not a purely functional language like Haskell, for example. Modern mainstream languages tend to combine ideas from different paradigms, and Kotlin does so as well. So we have OOP ideas, we have structural ideas, we have functional programming ideas combined in the same design. So when you're using classes and interfaces, you're on the OOP side, but at the same time, when you're using function types and lambdas and other functional features of Kotlin, you are doing something functional already. And I would say it's more of a style issue. So it's not about being a functional language, but it's about enabling the functional style of programming. For example, Kotlin promotes immutable data. So you are encouraged to use immutable things, but immutable things are also first-class citizens in Kotlin. You can use them freely whenever you like. It's a matter of style. So I would say if you rely on immutability, if you use higher-order functions and lambdas and function types, of course, you are doing Kotlin in the functional style, and it's very often beneficial. So I totally recommend it.
Let's see how we can solve the nice string task. At first, let's take a sample solution which works and passes all the tests but doesn't use the full power of the Kotlin functional features. It represents what can be submitted as a solution. Let's try to improve it and make it more functional. This sample solution works fine. It checks separately 3 required conditions. At first, it checks that the string doesn't contain bad substrings, then it counts the number of vowels and makes sure that there are at least 3 of them. At last, it checks whether the string has some repetitive characters. If the string satisfies more than 2 conditions, it's nice, and true is returned as a result. Let's improve this solution and start with the first condition. Here, we check that a string doesn't contain any of the specified substrings. Instead of repeating this check for every substring, we can put all the substrings in a set and then check the condition for each element in the set. For all the substrings, the following must be satisfied. The initial string doesn't contain this substring. Here, this refers to the receiver of the function, to string itself, and it refers to each of the substrings in turn. We use not in the condition, but one exclamation mark is often not very noticeable. Thus, we can use another predicate that doesn't need this exclamation mark. Instead of all, we can use none. It performs the same check. None of the substrings is the part of the initial string. That's our improved result for the first check. For the second check, we need to count the number of vowel letters. But instead of checking every vowel letter separately, we can again put them all in a set. Then we can check for each character in the initial string whether it belongs to this set or not. If it's a vowel, we count it. We can simplify this logic even more and check whether a character belongs to a string consisting of all vowel letters. Probably the check for belonging to a set is slightly better in terms of performance, but since we only have 5 characters, that's not a noticeable difference. We are mostly interested in how to make the code more readable now, and this last version looks really nice. The sample solution for the third condition exploits the traditional for loop and doesn't use any of the functional features. Let's see what we can do here. We need to check whether a string contains a double letter. At first, we can work with indexes directly. We check all the indexes in the string by saying from 0 to the last index. For each index, we get 2 characters, by this index and by the next one, and compare these 2 neighboring characters. In this way, we compare all pairs of neighboring characters and find the result. But there must be a better way to express that. You can use the zip with next function. Zip with next zips each character in a string with the next character and returns a list of pairs. Each pair consists of 2 neighboring characters. To check that there are 2 similar letters following one another, you simply check that there is a pair with 2 equal characters. Specifically, you check that the first element in a pair equals the second element. Zip with next works for lists of any elements. There is also another possible solution using the function specific for strings. I mean the windowed function. The windowed function returns a list of slices of the given size obtained from the initial string. You can see the result for the slices of the size 4, 3, and 2. Note that you can also specify a step between the starting points of the neighboring slices. If we get the slices of the size 2, it gives us basically the same result as zip with next, but as a list of strings, not a list of pairs. To solve the initial task, we do a similar thing. We check whether the first character in a string equals the second one, which is also the last one. Both solutions are possible. I'll pick the one with the zip with next as a result. Note that we no longer need the mutable variable, now has double is val. And it's only one line of code instead of the whole for loop. At last, we need to count the number of satisfied conditions. By the way, note the pattern if the condition is satisfied, return true, else return false here. The whole if can be replaced with return the condition. But this solution can be further improved. There are many ways to solve this last part. You can count the numbers explicitly like here, or you can write several if-else expressions, but that will be code repetition. The nicer way to do it would be to build a list of all the conditions, a list of 3 Boolean values, and see how many true values this list contains. Let's try to use filter for that. For each Boolean element, you check whether it's true or false, and you are only interested in true values. Then you get the size of the resulting list and compare it with 2. Note that you can filter simply it. You don't need to compare it with true since the list element is a Boolean value. However, there is one more important improvement. You can replace the combination of filter and size with only one function count. It counts the number of true values among our Boolean conditions in one iteration. That's our resulting function. You can see how we simplified this solution and how much shorter it became. Let's discuss how we can solve the taxi park assignment. I will again show sample solution first, which we'll then try to improve. The first task is to find the drivers that didn't perform any trips. There are 2 basic ways to solve this task. You can use either drivers or trips as a starting point. The first solution starts with all drivers, and you filter out those drivers who performed some trips. The drivers without trips stay in the resulting list. Finally, you need to convert it to a set because we require a set as a result. In the second case, you find the drivers that performed some trips and then you subtract the resulting collection from the set of all drivers. Thus, you get the drivers that performed no trips. Note that in Kotlin, you can use minus syntax directly instead of calling the minus function. We'll discuss the details of how exactly it works in the next module. Note that the second solution, subtracting the drivers that performed some trips from the set of all drivers, is slightly better since it does only one iteration via map. The first solution calls none for each driver. In the worst case scenario, the number of iterations will then be the multiplication of the number of drivers and the number of trips. However, the difference between these 2 solutions isn't that noticeable for not the worst case scenario. The second task is to find faithful passengers, the passengers that performed at least the required number of trips. There are again 2 basic ways to solve this task. Either start with trips or start with passengers. Let's look at 2 sample solutions and try to improve them. The first solution starts with trips. At first, we use flat map to get the list of all the passengers that made some trips. Each passenger is present in this list as many times as the number of trips he or she performed. Then, by grouping the same passenger's elements, we can find how many trips each passenger performed. The solution works and passes all the tests, however, it's not very readable. It makes the common readability mistake. It uses several it in neighboring lines, and it in different lines have different types. Because of that, it's not clear what's going on here. It's counterintuitive that the variable of the same name will have different types and different meanings in different lines. How we can improve that? In the first case, I would convert lambda to a reference. Then it's clear that we get passengers for each trip. When we group it, I would rather say passenger, passenger. There is nothing wrong in repeating it if it improves readability. Then I would again introduce an explicit parameter for it. Here it is map entry, but we are only interested in the value of this entry to access the group of equal passengers elements. I would say that everywhere destruction declaration syntax is better than one variable for entry. We don't use key here, so we can replace its name with underscore. This exact use case might be also simplified. Filter can be replaced with filter values, and now we have group as the only argument. The last simplification. Instead of first transforming entries to the keys and then converting the resulting list to a set, you can access keys directly. The second solution starts with the list of passengers and keeps only those who satisfy the given predicate. This solution uses functional features, but it somehow overuses them. For instance, it uses partition here where a filter would be enough. Partition splits the initial list of passengers into two lists, but then only the first list is later used. There is no sense to use partition if you're interested only in one of the parts. You have the specific filter function for that. By the way, if you're interested in the remaining part, in the elements that do not satisfy the given predicate, you can use filter not. Then this solution uses a rather complicated way to count the number of passengers that satisfy the given condition. It sums either 0 or 1 depending on whether a passenger took part in a specific trip. The direct way to express that is to use count. That's our solution. It simply uses filter and count. That was my simplification for the solutions. You can compare the initial variants with the improved versions. Hopefully, you can find something useful here. The next function finds all the passengers who performed more than one trip with a specific driver. Again, you can start either with passengers or with trips. Since the solutions are very similar to the previous task, I'm only showing the improved versions. Now let's talk about the next task, finding smart passengers, the passengers who performed the majority of their trips with a discount. I will start with some sample solution first and will try to improve them. Let's look at the first solution. Here we partition the whole list of trips into two lists. The first one contains all the trips with the discount, and the second contains the trips without discount. Note that the partition result is stored in a pair here. And given the variable is called simply pair, it's not at all obvious what is stored inside. We need to check the variable type explicitly. It's always better to use destructuring declaration syntax with partition and give meaningful names to two variables, rather than use pair. In this case, it will be trips with discount and trips without discount. Then we apply filter to all the passengers, and for each passenger, compare the number of trips he or she made with discount and without discount. Only the passengers with the majority of the trips with discount remain. Another thing I want to highlight in this solution is using isDouble check, for basically checking something for being not null. The more easy and straightforward check you can apply, the better. Try not to overcomplicate things. The intention might be not clear. When you use isDouble here, the reader automatically assumes that it's not just nullable variables stored in the list, but probably something else, integers or other types. That's confusing. The most straightforward way to check something for being not null is, unsurprisingly, just to check for being not null without overcomplication. The last thing we can improve here is to replace contains call with in. In also checks whether your element belongs to a collection or list. Under the hood, in calls contains, so basically they are the same. We can even navigate to in and see that indeed contains is called. Later in the next module, we'll discuss how exactly it works. After you get used to it, in looks more concise. Now, let's look at the alternative solution. It's a bit overcomplicated solution, but it can exist. I will suggest just some small improvements here. We start with all passengers and build a map storing all the trips performed by each passenger. Then, for each passenger, we compare the number of trips with a discount that he or she made with the number of trips without a discount. In the end, we keep only the passengers that have more trips with a discount. Let's see what we can improve here. The used groupBy function is the overloaded version of groupBy, which takes not only the key selector as an argument, but also the way to fetch the value. In this way, instead of grouping the elements, we group the transformed values. The result is a map from a passenger to all the trips he or she performed. Note that groupBy here is probably not the best choice, because the key passenger is unique. But groupBy doesn't know that and returns a map from passenger to a list of trips. To avoid this list of elements as the result value, it's better to use AssociateBy function. AssociateBy returns a map from key to the corresponding value directly. Note that we no longer need to call first later to get the first element. First was used here because the map values were lists with only one element, so first was used to get this element. Now it's no longer needed. But for this use case, I would rather use another function, not associate by, but simply associate. It takes one lambda as an argument. You specify the pair from key to value, which builds the values in the resulting map. In our case, the key is the passenger, and the value is all the trips that this passenger made. This way, it's a bit more readable. The next simplification for the solution concerns this entries line. Associate returns as map, and entries returns a set of entries. But you rarely need to convert a map to a collection of entries or pairs, since the majority of the operations are available for maps directly. Instead of converting a map to a list of entries, you can call filter on a map directly. Then I would replace it with explicit parameter because it's not that clear what is the type of it. Then I would use destructuring declaration syntax instead of entry. Since we use only entry value, we don't need a separate variable for entry key. And as we've already seen in the previous task, we can use filter values instead. First, we grouped the transformed values, then we filtered map contents. At last, we are interested in the set of keys in the resulting map. As before, we can directly use keys instead of mapping keys and calling to set. It's important to understand the difference between group by and associate by. Prefer associate or associate by if your key is unique. The last solution tries to be very concise, probably too concise. Don't strive to put the whole function at one line. Even if you can do it, doesn't mean you should. In this case, it's really unreadable. Even if you have a huge monitor, reading it from another place is inconvenient. Even if you use soft ropes IntelliJ feature, which might be switched on by View Active Editor Use Software Apps, it's still not readable in comparison with a properly formatted solution. After we formatted this solution, it became better. Don't neglect the possibility to extract variables with clear names. Even if you can make the solution very concise and functional, it's important not to lose readability. And good variable names can greatly help to understand what's going on in a piece of code. Here we count the number of trips with discount and without discount for each passenger and compare these numbers. With clear names, the intention is easier to understand in comparison with the version when you inline all the expressions. The resulting function is much better than the initial version written in one line. The next function finds the most frequent trip duration period. Again, I will show you a sample solution which will improve. Here we start with trips. Then we group trips by the duration period. However, there is a small repetition here. You repeat the expression of finding the start of trip duration. Extracting it into a variable and giving it a clear name helps to understand what's going on here. I would also introduce another variable end here. Now it's more clear that you group your trips by the range from start to end. Another thing I sometimes find in the code, I don't really understand why someone uses this syntax. You define a separate parameter name for lambda, but you name it as it. That's not needed. If the name of your parameter is clear from the context, simply omit the parameter name and use it inside. In this case, another it refers to a trip in the earlier line, but here it means something else, so it's better to introduce a new name. Whenever you see such it arrows syntax, you either replace it with a specific name or leave only it inside. We even have the inspection for that which tells redundant lambda arrow. Don't ignore such inspections. If they work wrong for your use case, file an issue, which the Kotlin team will fix, but don't ignore these suggestions. Note that toList here, which converts a map to a list, is needed because there is no sorted function on a map. toList returns a list of entries as a list of pairs. Because we are only interested in the second value, we again can use destructuring declaration syntax and specify the explicit name. Each group of trips corresponds to the specific trip duration. Another simplification here. There is no need to use sorted by descending only to find the first value. Basically, what we're doing here is we're finding maximum. You don't need to sort all the rest elements when you just need the first value. Max or max by will be more performant for that. And you can call max by directly on a map. Let's see how we can complete the solution for the last task. I suppose that you've already solved that in the playground. This task is to check whether 20% of the drivers contribute 80% of the income. To check that, at first we need to count the total income of all the drivers. For that, we use the cost of each trip. Trip has a property cost. We sum up all the costs of all the trips, and that is the total income. Note that we can use property references. After that, we build a sorted list of drivers' income. We are not interested in which exact drivers are the top drivers and contributed the majority of the income. We are okay with sorting only the income values. Thus, here we have the list of doubles as the result. First, we group the trips by drivers to build a map from driver to all trips by this driver. Then map function transforms each entry in this map. The first parameter represents driver, but we are interested in only the trips by this driver. We find the overall income of the specific driver. For that, we sum up the income for all the trips made by this specific driver. Again, we simply sum up the values returned by trip cost. Now, we have the total income and the list of sorted incomes for all the drivers. At last, we'll need to compare two numbers: the income of top drivers with 80% of the total income. Thus, we need to find the income of 20% of the top drivers. For this, we use sorted drivers' income. The take function returns us the required number of the first elements in the list. We want the list consisting of only the first top drivers. We've already found this number of top drivers in the previous line. Thus, we take the list consisting of only the income for the top drivers and count the sum of all the elements to find the total income of these top drivers. At last, we just compare these numbers and that gives us the result. That's how we can solve this check Pareto principle function in a rather concise fashion. Other solutions are also possible. There are many ways to solve this task. I just wanted to share one possible solution.
The task here is to implement an extension function is empty or null. And the most interesting thing here is that the receiver might be nullable. Here we have nullable string and we want to call this function on a nullable string. Indeed, in Kotlin, you can define functions on a nullable receiver, extension functions. That's not a problem. You just mark this receiver as nullable, and then you may implement your function. When you consider a receiver as just an extra parameter with this very nice special syntax to call it, that becomes very easy to understand what's going on and to implement it. You can simply check your parameter for null for being empty. You will do the same trick. We convert parameter to receiver, and now you see the answer. Note how you can explicitly check this for being null. So inside the extension function to nullable, this might be null. Here, the smart cast is used because now this is converted to non-null type after the check. Note that is very useful for such simple cases like strings. The library actually contains functions is null or empty and is null or blank, which checks whether string is null or empty or blank. Specifically for this task, I have to swap the name in order to let you implement it yourself. But you use such functions in Kotlin from the standard library by default. Indeed, when you read the code and you see that something is called just as a regular reference, that doesn't always mean that the variable is not null. So for most of the cases, that's true, but note that there is this special case when there is a function on a nullable receiver. In this case, you just call it like a regular reference without safe access. That's something to keep in mind. Because this confusion is possible, when you define your own such functions. You may define your own functions on an nullable receiver, but do it with care, because it's better if your function explicitly tells in its name that this receiver might be null, because in this case, it's easier to understand what's going on and you don't have to guess how it checks null or whether it checks whether it's possible to call it on null or not. You can use it by do it with care in order to not to confuse the readers of your code. In this task, we need to define a variable so that the first cast return just safe cast return just null, and the second one cast to a nullable type throw an exception. This task is a good illustration for the difference between safe cast and the regular cast to a nullable type. Any variable that stores not an integer value will do the job. So, for instance, in this example, you define a string, and after that, if you just use safecast, then you get null as a result, because that's how safecast works. If it doesn't cast, it simply returns you null. But the difference with the cast to nullable type is that if your variable cannot be casted to a nullable type, then you'll have here class cast exception that the cast is impossible. So that's the difference between the safecast and the cast to a nullable type. Our task is to complete the implementations of these functions using different predicates, and the purpose of this task is to illustrate that the predicates all, none, and any are interchangeable. So let's start. The first function is rather straightforward because we need to check that all the elements are non-zero, and we have this explicit all function, so we just check that all the elements are non-zero, as written, as expected. With the next function, that's a bit less trivial. When we check that there is one element that is non-zero, that's the same as saying that there is no zero element. No zero is present in the list. That's exactly what none function checks, that there is no zero element. So you see that these predicates are interchangeable, these functions are interchangeable. You just need to negate the predicate in order to use the different function, and that's just the Boolean logic. So it's rather straightforward. With any, it's a little bit less trivial because we have to negate the result of the function. When you think about it, none says there is no element, and it's the same as saying not any. Not any means there is no such element, as none also says there is no such element. So if we say not any zero, that's the same as saying no zero. That's the same as saying all are non-zero. Let's move on to the second task. The first one is again straightforward because it simply duplicates the function name. We say we are checking that this list contains zero. Zero, that means that we check that it contains any zero element. So when we use any, we explicitly check that the list contains zero. Then we know already that none is not any, so we can negate it in the other direction as well, and we'll have here this not very easy idea of not none. And we know again that all and none are interchangeable just with the different predicates, so we can replace here. We can use the same none. So here we already have this solution. When we replace none to all, in this case, we just need to negate the predicate, and that's what we do. Conceptually, this is the same as contains zero, because if all are non-zero, that means that there is no zero, and in order to check that it has at least one zero, then we have to negate this predicate. The main purpose of this task is for you to have the idea that all these predicates are interchangeable, and the most important thing is that it's better to use the most simple predicate for the case. That's something that I've seen in the code. That's a good idea to keep in mind, that there is no need to negate the whole expression. There is always the way to simplify the code without using the negation, because the negation is really, really hard to read and understand. You can see here. But here we have our task where you have to specifically write such code. But if you If you see the code like this in the code, you may ask why it's written in so complicated manner? Why just not simply replace it with other function and a more simple predicate? That's something to keep in mind, that it's often possible to simplify your logic. We can run the code to make sure that we have all okay. Yes, so we've done everything correctly. In this section, we are going to discuss properties in Kotlin. You might already know the concept of a Java bean property. Unlike Java, where property is not a language construct, Kotlin supports it as a separate language feature. In a most common scenario, for a trivial case, property syntax is really concise, but you can customize it if needed. Java classes contain fields and methods inside. They don't have the direct feature of property. However, if you define a field with the corresponding getter and setter in Java, that concept will be considered a property. For instance, a field foo, together with getFoo and setFoo methods, is called the foo property. In Kotlin, a property is absolutely the same idea, the same concept. The syntax is different. You define the property itself rather than separately fields and accessors. But under the hood, the implementation doesn't change. It's the same field and accessors as in Java. When you use a property in Kotlin, you don't call getters or setters. You use property directly and access it like a variable. When you access the property by its name, the getter is called under the hood. If you want to change its value, to call a setter, you do it like it was a variable. Under the hood, the setter is called. If you use the Kotlin properties from Java, you will need to call getters and setters explicitly like in Java. In Java, code looks like Java. Interestingly, there is no difference whether this construct class is defined in Kotlin or in Java. If you define a Java class with a field getter and probably setter, following the convention, then in Kotlin you can use it as a regular Kotlin property. You access Java properties from Kotlin by their names, not via getters and setters. The usage of properties now looks much nicer. The question for you: how many methods does the class person have under the hood? Note that we don't count the constructors here. We have one read-only property name, which has the corresponding getter under the hood, and a mutable property age, which has a getter and a setter, getAge and setAge. That makes it 3 as a result. This is the person class written in Java. And at the same time, that's what's going on under the hood. At the bytecode level, we have the same implementation as in Java. 2 fields, constructor, 2 getters, and a setter. The Kotlin syntax looks nice, straightforward, and concise, while the bytecode stays the same. You can define properties without fields, like in Java when you can only define getFoo method that returns a value. If you don't need a field, you omit it. You can redefine the accessor's behavior without the necessity to store a value in a field. Here, we define a custom getter for the is_square property, which is calculated on each access. From Kotlin, you use the is_square property as a regular property. There is no difference. The question for you is, how many times the phrase calculating their answer will be printed in this example? We use the run function that we've discussed in the previous module. It runs the lambda and returns its result, the last expression. We assign 42 to a variable foo1 and print calculating the answer on the way. The lambda result is calculated only once when we assign it. Then the property value is used. Therefore, the phrase calculating the answer is printed only once here. In the second example, the foo2 property has a custom getter which is called on each access. Every time we call the property, the getter is called and the calculating the answer phrase is printed. That gives us 3 as the number of times the phrase will be printed. Let's now talk about fields. In Kotlin, you don't work with fields directly, you work with properties. However, if you need, you can access a field inside its property accessors. It's not visible for other methods of the class. You access a field inside its getter or setter by using the field keyword.
Here we access a field inside a custom setter. We add logging to mark the situation when the property value was changed. Note that no backing field is generated by the compiler if you redefine accessors and don't use field keyword there. Here, state mutable property uses another private property bool state to store the data. State only delegates to it. Because state doesn't use field keyword inside its getter and setter, no backing field is generated for it. If you don't redefine accessors for a property, the compiler generates a trivial getter that returns the field value, and a trivial setter updating the value, if the property is mutable. You don't access fields, getters, or setters directly. You only use properties, both inside and outside of the class. I want to highlight here that under the hood, the getters and setters are called. When you access counter here, then at the bytecode, getCounter is called instead. However, inside the class, the optimization takes place. If the property accessors are trivial, they are default ones, which return you the value or assign it, then the calls are optimized by the compiler and replaced with accessing the field directly. It's not safe to perform this optimization for code outside of the class. You might want to change the implementation of the getter, making it non-trivial. Then you will need to recompile the depending code so that it used the getter instead of the field. However, in general case, you can use different versions of the class and the depending code. So such property change won't be safe. The old depending code will continue to use the old trivial property implementation. To prevent such problems, outside of the class, getters and setters are always called in the generated bytecode. But inside the class, optimization performed by the compiler are possible, but only for the trivial properties. Sometimes you want a var mutable property to be accessible only as a read-only property outside of the class. For that, you can make a setter private. Then the getter is accessible everywhere, and therefore the property is accessible everywhere, but it's allowed to modify it only inside the same class. Note that we change only the visibility of the setter, but use the default implementation.
We've discussed read-only and mutable properties, how to define custom getters and setters, and how to mix Kotlin properties and Java. Next, we're going to talk about defining properties in interfaces and making them extensions. In this video, you'll see examples of how to define properties in interfaces and how to define extension properties.
You can define a property in an interface. Why not? Under the hood, it's just a getter. Then you can redefine this getter in subclasses in the way you want. A question for you here. Which property among these two is calculated on each access? The nickname property with a custom getter in subscribing user calculates the value each time you access it. The property in Facebook user stores the value in a field. The property with a custom getter doesn't have the corresponding field. Note that all the properties in interfaces are open and can't be used in smart casts. Open means that they can be written in subclasses, they are not final. When you check whether the session user property is of type Facebook user, and afterward try to use a smart cast to access the account ID property of Facebook user, the compiler shows you an error. It's impossible because this property has an open or custom getter. If a property has a custom getter, it's not safe to use it in a smart cast, because a custom getter can return you a new value on each access. There is no guarantee that after you cast, there will be the same value. If the property is open, then the actual implementation in a subclass may have the custom getter, which will return you different values on each access. So it's also not safe. What you can do here? You can introduce a local variable, then the smart cast applies. Alternatively, you can use other language mechanisms, which we'll discuss later. Note also that smart casts don't also work for mutable properties. because the mutable property might be changed in a different thread after you have checked it for being of a specific type. To fix this, you can again introduce a local variable. Sometimes SmartCast will work for mutable local variables. In Kotlin, you can define extension properties. The syntax is very similar to the one of defining extension functions. You simply define a property but specify the receiver type first. You can access the receiver as this reference inside accessors. Or you can omit this reference and call members as in the second example. You can call extension properties as they were member properties. The syntax looks nicer, in the same way as it works for extension functions. The question for you: what do you think? Does the extension property perform any optimizations in terms of the stored value? Here we have this ABC string, and we call an extension property twice on it. How many times the getter will be called? Probably it's somehow optimized and the value is stored. What's your guess? Of course, there are no optimizations. This extension property is compiled to the getMedianTer static method with an extra parameter under the hood, which is called on each access. There is no magic here. Extension properties are very similar to extension functions. The only difference is the different syntax, the one without parentheses when you call it a property. You can define mutable extension properties. Here we define the mutable extension property lastChar on string builder. It allows to get or update the last character. You then can use it as a regular property with a concise syntax to access a setter that just assigns a value to a property.
You've learned that you can define a property in an interface and why it can't be SmartCast. You now know how to define a read-only or even mutable extension property. Next, we are going to discuss the concepts of lazy and late-init properties. In this video, you'll learn how to define a lazy property. Also, how to define a property that should be initialized not in the constructor, but sometime later.
Lazy property is a property which values are computed only on the first access. It's lazy in a sense that it won't do anything unless the result is really needed. In Kotlin, you define a lazy property using by-lazy syntax. It's an example of applying the feature delegated properties, which we'll discuss in the next course. But even now you can use it for defining lazy properties. Lazy is a function that takes a lambda as an argument. Inside this lambda, you provide a way to compute a value that should be stored in this property. When you access this property, you see that its value is computed only once, when we access it for the first time. After that, the stored value is returned. The question for you is, how many times computed will be printed in this example when we don't access the property at all? The options are 0 or 1. The right answer is of course 0, because the lazy property is lazy in a sense that it won't do anything unless it's needed. In this case, the result is not needed, and that's why it's not computed at all. Our next topic is late initialization. It's very useful for some frameworks, for instance for Android activities, initializing unit tests, or dependency injections frameworks. Sometimes we want to initialize the property not in a constructor, but in a specially designated for that purpose method. Here we initialize the myData property in onCreate method, but not in the constructor. We can't define it as a non-nullable property because we don't have an initial value. We can use null as an initial value, but in this case, we have to make the property nullable. Then, every time we access it, we have to cope with nullability. But we know that this property cannot be null after it was properly initialized. That's where late init properties can be really helpful. We can define the property as late init. After that, we can use it as a value of a non-nullable type. What happens if the property wasn't initialized properly? We access it as a regular non-nullable property. Null pointer exceptions are possible or what? In fact, at runtime, an exception is indeed thrown, but a runtime exception with a detailed message of what was wrong. In this case, we get the message that the MyData property wasn't initialized, and we see what caused this alternative, more detailed version of null pointer exception. There are some constraints that apply to lateInit properties. For instance, it can't be val. That is connected with how the lateInit properties are implemented under the hood. LateInit variable can't be final at the bytecode level because it is initialized not in the constructor but later. It doesn't conform to the final constraints. Because of that, it can be changed from Java. And because it can be changed from Java, if it was val, it would be confusing. Imagine val property which can't be modified from Kotlin but can be modified from Java. Because of that, it was decided that it's safer to explicitly say that this property is always mutable. Another constraint, kind of obvious, is that the type of this property is non-nullable. That's a purpose of lateInit, to make the type of the variable non-nullable so that we won't have to cope with nullability issues. Another constraint is that lateInit property can't have a primitive type. That's also connected with the underlying implementation. Only reference types might be initialized with null under the hood. The compiler could possibly initialize integer values with some constants, but which exact constants? It's unclear. That's not how it works. If you know which value the primitive can be initialized with, you can do it by hand. Use 0 for an integer, for instance. Thus, the lateInit modifier can be only applied to non-nullable reference types. It's possible to check whether lateInit property was or wasn't initialized. To do that, you call isInitialized on the property reference. We saw examples of member references, including property references, in the previous module. That is another case when property references might be useful, when you check whether your lateInit property was or was not initialized.
You've learned about lazy and lateInit properties. That concludes our discussion of properties so far. We'll also cover the nuances of how to define constants as properties at the end of the next section. Next, we're going to discuss the details of object-oriented programming in Kotlin. In this section, we'll focus on object-oriented programming in Kotlin. Overall, Kotlin doesn't introduce anything conceptually new here. The experience is very similar. However, Kotlin brings many small niceties and practical improvements. Note that in this course, we assume that you already understand such concepts as inheritance or member overriding, so I won't explain you the familiar ideas, but just show you the different syntax.
The defaults in Kotlin are different. Any declaration is public and final by default. If you want to make it non-final, you explicitly need to mark it as open. Also, there is no package private visibility in Kotlin. There is a new one, internal. That means the declaration is visible inside the same module. A module is a set of Kotlin files compiled together. It can be an IntelliJ IDEA module, a Maven project, or a Gradle source set. Now, to make sure you are familiar with these modifiers, find the correspondence between the modifiers applied to members and their meaning. Final means that the declaration cannot be overridden. Open is the opposite, and it should be marked explicitly. Abstract is the same as in Java. It means that the declaration must be overridden. You explicitly add the override modifier to a member that overrides another member from a superclass. To avoid accidental overriding clashes, override now is mandatory. You can't override something accidentally and not notice it. Now fill the table with the explanation for visibility modifiers. Public is visible everywhere. Internal is visible in the same module. Protected is the same as in Java. It means that the declaration is visible in subclasses. However, there is a small difference with Java. In Java, protected is also visible inside the same package. In Kotlin, it's no longer the case. Protected is only about subclasses. Private differs in meaning for a class member and a top-level declaration. Class member is visible inside the class, and private top-level declaration is visible inside the same file. You may ask what happens under the hood at the bytecode level. For public and protected declarations, it's clear. there is the direct correspondence. Private functions and properties also stay private. A private class is converted to a package private class, because there is no such thing in JVM as a private class. The main question is what happens with internal. A package private is different, it's not the same as the same module. Under the hood, internal is transformed to a public declaration. However, the names of internal members are mangled. Here you have internal fun foo. At the bytecode, this function has a really long name which you can't accidentally use from Java. There is also a difference with package structure. In Java, every class should be located in its own separate file, even if the class is very small. In Kotlin, it's no longer the case. You can put several classes into one file. It's especially useful if your classes are data classes that are small and simple. You can combine several classes connected to each other in one file. You can also put top-level declarations, functions, and properties and the class into one file. It makes sense to unite the class and all the utility members connected with this class and put them all together into one file. There is one more difference. In Kotlin, the package name doesn't need to correspond to the directory structure. Your package name can be any name. However, the Kotlin style guide still recommends you to omit only the first prefix, the company name, from the directory structure, and keep everything else so that it was easier to navigate your code.
After watching this video, you know that public and final are used by default, and a write modifier is mandatory. You've also learned that you no longer need to create a separate file to store a small simple class. Next, we are going to discuss the syntax for constructors in Kotlin. In this section, you'll learn the syntax for constructors in Kotlin, what is the difference between primary and secondary constructor, and why the inheritance syntax also looks different than in Java.
A constructor is a special function used to initialize a newly created object. We don't use new keyword in Kotlin. You call a constructor as a regular function. You can distinguish a constructor call from a function call because of the convention. The class name starts with the uppercase letter and you call the constructor by the class name, but the function name starts with a lowercase letter. If you define no constructors in the class, the Kotlin compiler generates one without parameters by default. That's why you can create an instance of the A class here. The default constructor was generated automatically. Often you need some arguments to create a new class instance. Then you define constructors explicitly. The main constructor is called a primary constructor. It has a very concise syntax when it's trivial. It only initializes the properties with its past values. Here we have two properties which are initialized with the values from the constructor. The syntax is concise and readable. In Java you have to write the constructor code explicitly. After the class name inside the parentheses, you specify the constructor parameters. You can put the complicated initialization logic inside the init section, which represents the constructor body. By default, you define properties inside the class body between the curly braces. Here you can see the full syntax. When you initialize the property with the corresponding constructor parameter in the constructor body. When you put val or var before the parameter, that automatically creates a property. Without val or var, it's only a constructor parameter. You can change the visibility of the constructor if needed. In this case, you need to explicitly use the constructor keyword and put it between the class name and the parentheses. You can add private or internal visibility, whatever you need. You can define secondary constructors. If default arguments don't do a job for you, and you need a different argument list, you can do that. Each secondary constructor must call another secondary or primary constructor. You call another constructor using this keyword. Note that if a primary or secondary constructor is present, no default constructor without arguments is generated. The later one is automatically generated only if you define no other constructors. In Kotlin, the syntax to express inheritance is a bit different than in Java. You use colon to replace both extends and implements keywords. The parentheses while extending a class denote the constructor call. If you need to pass any arguments to initialize a superclass, you put them inside these parentheses. Use the super keyword to call the constructor of the parent class from the secondary constructor. The question: in which order the init section of parent and child classes are called? What is printed? There are options child, child parent, or parent child. When you create an instance of a child class, at first, parent constructor is called and parent properties are initialized. Then child constructor is called and child properties are initialized. That works directly as in Java. The subclass inherits all the properties of the superclass, even if it can't access them. To create a correct instance of the subclass, the compiler should initialize all the inherited properties from the superclass, so it calls the superclass constructor. The next question is about overriding properties. What will be printed in this example? 1, 2, or 0? The right answer is surprisingly 0. Now let's understand why. In Java, it's impossible to override fields, and under the hood in Kotlin it's the same. When you override a property, in fact, you override a getter, not a field. For instance, you can override a property that doesn't have a field with a property that has a field. That's totally legal. However, when both a property from a superclass and an overridden property in a subclass have fields, that might lead to unexpected results. Let's see what bytecode is generated for the Kotlin class in our example. As usual, we'll look at the corresponding Java code instead for simplicity. Note two things here. First, the foo getter is trivial, so a field and a getter correspond to the foo property. Then, because the property is open and can be overridden in a subclass, its usage inside the class is compiled to a getter call, not a field call. Now the generated code for the child class. Note that the overridden property in the parent class is also compiled to a field and a getter, and now it's another field. What happens when you create an instance of the child class? At first, the parent constructor is called. The parent constructor initializes the first foo field with 1. But inside the init section, an overridden getter is called, which calls getFoo from the child class. Because the field in the child class is not yet initialized, 0 is returned. That's why 0 is printed here. In the playground right after the video, you'll find another illustration of the problems that can arise if you override a property and try to use it inside the constructor of a superclass.
You've learned the syntax for constructors in Kotlin. Next, we'll discuss different modifiers that can be applied to classes. In Kotlin, you can use class modifiers to add new semantics to classes. Modifiers can instruct the compiler to generate new methods or introduce additional constraints. In this video, you'll learn the details about enum and data classes.
Enum class represents an enumeration, like in Java. If you need a class with a fixed number of values, you can define these values as enum constants. The difference with Java is that now enum is not a separate instance, but a modifier before the class keyword. The most common way to work with enum constants is to use when expressions. You specify the actions that should be done for different enum constants. As a reminder, by default, you access enum constants by their full names. But if you import enum constants, you can use them without explicit specification. Inside enum class, you can define member functions and properties. Note the syntax of how we initialize the enum constants. You pass different values as constructor arguments inside the parentheses. Afterwards, you call the methods and properties directly on enum constants. Probably it's the only place when you need a semicolon in Kotlin to separate the enum constant list from the members list. Next, we are going to talk about data classes. We've already come across this feature, but now we are going to discuss what methods are generated under the hood. We'll cover the majority of the methods and leave the rest for the next section. Data modifier adds equals, hashcode, nice to string, and copy methods. you can call the copy method to copy an instance of the data class and specify only the arguments that must be changed. The rest values remain the same. Or you can omit all the arguments and only explicitly copy the reference. In Java, everyone knows that one needs to call the equals method instead of the double equal sign. Otherwise, you get the reference equality instead of comparing the contents in the case when equals is redefined. In Kotlin, it's no longer the case. By default, when you use the double equal sign, it calls equals under the hood. If your class redefines equals, it will compare the elements in a meaningful way. If you still need reference equality for some reason, you can use the triple equal sign. The question for you is, what will be printed here? The only difference is that the second class is defined as data class. The right answer is the third one. Let's try to understand what's going on here. By default, like in Java, in Kotlin every class inherits default equals implementation, which just checks reference equality. When we compare reference of the type foo, we compare them by reference equality. Despite equals is called, by default this equals is the trivial one. That's why this line prints false. If we compare the reference that refer to the same object in memory, we'll get true, obviously. For data classes, the right equals and hashcode methods are generated. We now compare the elements by their content. For the bar data class, here we again call equals under the hood, but now equals compares the content, so we have true as a result. Note that the compiler only uses the properties defined inside the primary constructor for the automatically generated functions like toString, equals, and hashcode. To exclude a property from the generated implementations, declare it inside the class body, like the nickname property in this example. Then it won't be included into string representation and its value won't be used to compare instances. Here, the first user equals the second one, despite they have different values for the nickname property, because only email values are compared by default.
You now know how to conveniently use enum constants by importing them, or which methods are generated when you add data annotation. Next, we'll discuss sealed classes, inner classes, and class delegation. In this video, we'll continue to discuss class modifiers and look at sealed and inner classes. You'll also learn about class delegation.
In Kotlin, you can put sealed modifier in front of the class. Let's discuss what does that mean. To better understand that, let's look at the class hierarchy and see how we can work with it. We are going to represent very simple expressions. An expression is either a number or a sum of two expressions. Imagine you need to evaluate the result of the stored expression. The eval function will be responsible for that. How would you implement this function? You would probably write the code like this using when expression. Then you would check whether the variable is of type number or is of type sum, and afterward do things accordingly. The problem with this code is that it doesn't compile. The Kotlin compiler says that with expression is not exhaustive. There is no guarantee that there are no other subclasses implementing expression interface defined somewhere. There is no guarantee that your code won't break because of that. To make your intentions explicit, you will need to provide your own way to process this problem. You need to tell exactly what should be done if not all the subclasses are present in branches. A sealed modifier solves this problem for the case when you already know your full hierarchy. It restricts the class hierarchy. Now with sealed modifier, we don't need else branch. Note that all the subclasses must be present in the same file as the parent sealed class. It works well for simple hierarchies. The difference with the previous case is that now expression is a class, not an interface. That's connected with the underlying implementation. Under the hood, the sealed class has a private default constructor, so that you couldn't accidentally instantiate this class from Java or create subclasses. I want to mention here that there is no full pattern matching support in Kotlin. When, with smart casts, covers the majority of the cases, like this one, when you check the upper level of expression of being a specific type. Because it's already so useful, there is no full support for more complicated comparisons. Now let's discuss another topic. Let's discuss inner modifier and compare inner and nested classes. First, the question: which class, nested or inner, stores the reference to an outer class? The answer is inner class. In Kotlin, the default for nested and inner classes is different. In Java, if you forget to put static in front of the nested class, that will generate the reference to the outer class. That is something to keep in mind. If you forget about this, it can lead to memory leaks in a situation when you no longer use the outer class, but the reference to it is nevertheless stored. In Kotlin, the default has changed. Now you get a static nested class by default, the one that doesn't store the reference to the outer class. If you want this reference, you will need to explicitly add inner modifier. To access this reference of the outer class, you use labeled this. As a label name, you specify the name of the outer class. A couple of words about the class delegation. To understand why we need that, let's imagine you have a couple of interfaces, and you have a class that implements these interfaces by delegating to some properties. Instead of implementing all the methods, you just need to delegate to some other instances. You can write this code by hand or generate the delegating methods. They are trivial. There might be more of them if the interfaces are larger, and all the methods just delegate all the implementations to other instances. By using class delegation, you can express the same logic simply by saying, I want to implement this interface by delegating to this instance. This by means by delegating to the following instance. In essence, class delegation allows you to delegate the task of generating trivial methods to the compiler. Note that the controller class implements both interfaces, so we can call interface members on it.
Now you know how to constrain the type hierarchy using sealed classes, what is the difference between inner and nested classes, and what class delegation can be used for. Next, we are going to discuss the object keyword in Kotlin. In this video, you learned the difference between object declaration and object expression, and what benefits companion object brings in comparison with Java static methods.
Object is a singleton in Kotlin. Singleton is a class which has only one instance. By using object keyword, you create a class and its instance in one place. In Java, when you need a singleton, you probably do something like this. You make the constructor private and create only one static instance field, which you instantiate right away. Because the constructor is private, it's impossible to create any other instance outside of this class. Under the hood, the object in Kotlin is absolutely the same as this Java singleton. Exactly the same code is generated. To use Java singleton, you call members on the instance field. If you need to use Kotlin object from Java, you would do the same thing. Note that from Kotlin, you simply call members on Kotlin object. Now let's discuss object expressions. Despite this feature uses object keyword, it represents a different idea. Object expressions replace Java's anonymous classes. Imagine you need to implement an interface or override a couple of methods in a class. That's going to be the only usage of this new class, so you don't want to create a named class for that. In Java, you create an anonymous class in this situation. In Kotlin, you use object expressions. Note that whenever your interface has only one single abstract method, then you can use lambda. There is no need for object expression. But if you need to implement several methods, then you will use object expressions. The question: what do you think? Is object expression a singleton? Is it true that for object expression only one instance of the anonymous class is created or not? The answer is no. Object expressions and object declarations, singletons, are different concepts. A new instance of object expression is actually created for each call. If your object expression captures some variable from the outer context, like here, then new instances of the anonymous class will need to use different values on each access. It's not even possible to optimize that. Each different call to register repository needs its own instance of the updated repository class, which stores the corresponding value for the customer's variable. You can not only put an inner or nested class inside another class, but also a nested object. One of the examples of such nested objects is a companion object. It's a nested object inside a class, but a special one, the one which members can be accessed by the class name. In Kotlin, there are no static methods like in Java, and companion objects might be a replacement for that. I want to give you some motivation of why Kotlin has companion objects but not static methods, in which case companion objects can be better. At first, companion object can implement an interface. Sometimes we lack this feature in Java. It would be nice if a static method could override a member of an interface, but for static, that's not possible. Now it's possible for companion object. Here, a companion object implements factory. You can use the companion object instance accessed simply by the class name as an instance of factory. Another thing which you can do with companion object is you can define extensions to it. To distinguish an extension to a class from an extension to a companion object, you use the companion suffix. After that, you can call such extension function like a companion object member, simply by the class name. There is no static keyword in Kotlin. There are no static members. You can ask where you should now define the static members. The answer is you can define them at the top level inside objects and inside companion object. By default, strive to put everything at the top level. This is the first place to put your previously static members in Java. But that's not always possible. Imagine your static method takes an instance of your class and needs to call a private member on it, or create a new instance using the private constructor. You don't have the access to private members from the top-level functions outside of the class. You can only call it from an object or companion object inside the same class. By default, your functions defined in a companion object or in an object won't be compiled to static members. From Java, you can't call them as static members, but if you need that, you can add the JVM static annotation. The question: which lines do you think won't compile in this code? The second line won't compile because we try to access bar as a static function, but by default it can't be accessed like that. To access it as static, you need to add JVM static annotation, which generates an additional static function to be called from Java. Note that from Java you still can access companion object members as members of special companion instance. The same works with objects. If you need a member to be compiled as static and to be called as static from Java, add the JVM static annotation. What do you think? Is it possible to declare an inner object, the one that stores the reference to the outer class? Yes or no? The answer is no. The compiler gives you an error that inner modifier can't be used with the object. Object is a singleton, so only one instance of class B exists. And there might be potentially many instances of the outer A class. It's unclear which exact reference should be stored then. You can define an object as nested inside another object or another class.
You now know that object declaration is a singleton, object expression corresponds to a Java anonymous class, and JVM static annotation makes an object member visible as static from Java. Next, we'll discuss how you can define constants in Kotlin. In this video, you'll learn how to define constants to achieve better performance and improve Java interoperability.
If you define a constant of a primitive type or string in Kotlin, you can declare it using a const modifier that will make it a compile time constant. For reference types, if for some reason you don't want to generate getters under the hood, you can apply the JVM field annotation that will instruct the compiler to generate only the field. In Java, if a primitive type or a string is defined as a constant and its value is known at compile time, the compiler replaces the constant name everywhere in the code with its value. Then it's called a compile time constant. In Java, the rules for what is a constant are rather complicated. In Kotlin, all the compile time constants are marked explicitly. When you add const to a property, that makes it a compile time constant. The Kotlin compiler also inlines the value of such constant. It replaces its name with its value everywhere in the code. Note that it works only for primitive types and strings. JVM field exposes a property as a field. It makes it public if a property is public. Then this field can be accessed from Java. It's useful for some frameworks that need public fields available. After you apply JVM field annotation, no getter is generated for read-only property and no setter if the property is mutable. Here, prop is a top-level property, so applying JVM field is the same as defining static field directly. Note that you can also want to eliminate accessors for performance reasons. JVM field makes a property static if used at the top level or inside object. If used inside a regular class, the regular field will be generated. To better understand how it works, there is a question. Which declarations will expose answer as a static field when used from Java? There are options with JVM static, JVM field, or const. The right answer is JVM fields or const, not JVM static. When you simply define a property inside an object, then it becomes available from Java only via getter because the field by default is private. And the getter is only available as a member of instance field. To make it available as a static member, you can apply JVM static annotation. In this case, however, you can only access the getter as a static member, not the field. That means it doesn't make sense to apply JVM static to properties. To expose the field, apply the JVM field annotation. In the case of primitive types and strings, you can use const modifier. The next question is, which declarations will inline the value in the resulting bytecode? That means the compiler will substitute the value instead of calling this property. Again, the same options. The right answer is the const modifier. That's exactly what the const does. With JVM static, the compiler calls the getter under the hood. With JVM field, the compiler calls the field. Only const property in the resulting bytecode will be replaced with the actual value. The last question kind of duplicates the first one. The difference is that now it's about a top-level property. Which declaration will expose a top-level property as a static field if used from Java? The answer is JVM field and const, as we've already discussed. If you declare a property at the top level, it will be accessible only by the getter. JVM field eliminates the getter, and const does the same. In this video, we'll discuss generics. As in Java, you can define an interface or a class with a generic parameter. Then, when you use this class, you substitute a specific type instead of a parameter. Here, we define functions that work separately with a list of ints or a list of strings. If your function should work with all generic types, rather than with a specific type like a list of ints, you can make the function itself generic. You define a type parameter for a function and later use this type parameter in the function declaration and in the function body. You can call a generic function on different types. When you call the filter function, list of t might become list of ints, list of strings, or something else. The generic type parameter t takes different values. Note that we don't know whether t is nullable or not. It might become either not nullable or a nullable type. You can call filter on a list of nullable ints or on a list of nullable strings. Nullable types are suitable as generic arguments. you can explicitly make the generic parameter nullable. Then the substituted type also becomes nullable. The first onNull function returns nullable type as a result. When you call first onNull on a list of ints, you get a nullable int. If it's called on a list of nullable elements, then t is nullable itself, and nullable t remains simply nullable int. The question for you: can the list element type be nullable in the example below? Yes or no? You can easily pass a list of nullable elements as an argument here, so the element can be null. If you want to restrict the generic argument so that it was non-nullable, you can specify a non-null upper bound. You add an upper bound right after the type parameter declaration, using the same colon which replaces the extends keyword in Kotlin. If you try to call a function expecting a list of non-nullable elements, passing a list of nullable elements, you'll get the compiler error. Nullable type is not a subtype of non-nullable any, so such function can't be called like that. There is a useful library function that filters out all nulls from the list. It's called on a list of nullable elements and returns a list of non-nullable elements. Non-null any upper bound emphasizes that the return list doesn't contain nulls. You can specify a different upper bound. In this case, you can pass both integer and double numbers, since they both extend number. An upper bound can be nullable. Here you can pass an integer, a double number, or null as an argument. As in Java, the upper bound can contain the type parameter. That's the standard way to define a function that should work with comparable elements. To define multiple upper bound constraints for a type parameter, use the where syntax at the end of the function declaration. Here, you can pass any type that extends to different interfaces, char sequence and appendable. String builder implements both char sequence and appendable, so it's a valid argument for this function. Because of JVM platform constraints, you can't define two functions with the same JVM signature, the signature with erased generic type parameters. Here, we try to define two extension functions on list int and list double. The functions differ only in generic type argument value, int versus double, and that's not enough. The Kotlin compiler doesn't allow that. However, applying one annotation can fix this example and make such declaration legal. We've already discussed this annotation but applied it only to the whole file before. Check your guess. That's JVM name. When applied before the package declaration, it modifies the file name under the hood. But also it can modify the name of the function at the bytecode. In this case, two functions now have different names at the bytecode. The first one is average, the second one is average of double. At the JVM level, there are two different functions, so there is no error. However, from Kotlin, you use both functions simply by the average name. The Kotlin compiler infers which function you want to call in each case. The question to check your understanding: how do you call the second function from Java, as average or average of double? Since the second function is named average of double at the bytecode, from Java you call it as average of double. Java sees the Kotlin compiled code only through the bytecode. You add the dependencies on class files to a mixed Kotlin and Java projects. That means from Java you call the functions as they are named in the bytecode, but from Kotlin different improvements are possible. For instance, in this case, you call both functions by simple average name when used from Kotlin. Later, in the future course, we'll discuss a couple more features around generics, in and out modifiers used in an interface declaration, and verification of type arguments possible for inline functions only. Because these features are mostly used by library authors, you can safely ignore them for now if you come across out or verified keywords in the codebase. The purpose of the interface or function doesn't usually depend on these keywords.
This video concludes our section about object-oriented programming. Next section will focus on conventions. Why final and public are used by default.
Picking public and final as default may seem controversial because public is the most permissive, right? So everyone can see this, and final is the most restrictive. Like no one can override this. But there is a reason behind it. It's basically striking the balance between the needs of application developers and library developers. Application developers are a much bigger group of people, of course. Library developers are still a very important group of people. So we were going after making life as easy as possible for application developers without hurting the library developers too much. So for a library developer, it's very important to control how visible your API is, because if you accidentally publish anything, then it's very hard to take it back, right? And same for making things overwritable. If you make something open accidentally, it's a problem for a library. While in the application code, it doesn't matter that much because nobody depends on you. You can easily change it back. Well, it does propagate through a big project. Like if you have a huge multi-module project, then one module is a library for another. And it gets more and more important, but still, it's a lot less of an issue in terms of retroactively taking things back. So we were looking at many use cases in application code and library code. And just decided on the most common things. So most commonly, public is the best choice for application code. Most commonly, final is the best choice as well because it enables things. So public just makes things visible. But final also enables language features like smartcasts. For example, if you have a val that's a member in a class, and it's just a simple thing, stores the value in the backing field. If it's open, you can't smartcast it because you can't be sure that it's not overridden and not computed somehow. But if it's final, you can smartcast it, and it makes the usability at the call site much better. So this is why final. And public is just the most popular visibility for declarations in application code bases. It wasn't an easy choice. It was debated till the very end, till right before Kotlin 1.0 was published. But I think we did find the right balance here, although it's an inherently debatable thing. So it's a very tightly constrained problem.
Why there is no full pattern matching support in Kotlin?
Well, Kotlin's pattern matching capabilities are very limited. Well, strictly speaking, we don't have a pattern matching as a language feature at all. What we have is a when expression plus smartcasts, which covers a lot of functionality of pattern matching, at least for simple use cases. And it turns out that most use cases out there are simple. So it was basically a pragmatic language choice. We decided not to introduce a lot of syntax and a lot of other language machinery to have full pattern matching. What we sacrificed was the ability of matching deeply nested structures, but it turns out that our users, a lot of them at least, can be really happy with what we have. So our idea in the beginning was that we better try first without pattern matching and see how needed it is so that we can add it later. We still have the design. We can introduce it in a later language version, but so far it hasn't been the most desired feature among the things we don't have. So I think if pattern matching makes it into Kotlin, it will be at some time later. We'll have more interesting things to add before that.
Why companion objects?
So this all starts with our issues with statics. If you think about it, there is something strange about a member in a class that is not actually calling its instances. You end up with classes full of only statics and no instance members at all. These classes are not really instantiated ever, so they are not proper abstractions. We wanted to get rid of this in Kotlin, and this is why we have top-level functions. So you can put all your utilities at the top level and not create classes that are not really types or not intended to be instantiated. But then you may need to call something on the class name, say class.something. And to facilitate that, we use the idea of companion objects when you can attach a singleton to a class so that its members are called in the class name. This abstraction is somewhat more powerful because such an object can extend other classes or implement interfaces, so there is more code reuse to it. And also it has a type, so you can define an extension for some class's companion object. Thus, you have more flexibility defining new API members on the class name outside of the class itself.
In this section, you'll learn how to improve the experience of working with custom classes via operator overloading and other conventions. In Kotlin, you can use the syntax of arithmetic operations not only for primitives or strings, but for custom types as well. You define a function, a member or an extension with a specific name and mark it as operator. Then you can use the concise syntax for working with your custom type. The operator keyword is important here. It allows you to call plus as an operator. There is a fixed list of arithmetic operations. It's not that you can use any name. You can see the correspondence between the syntax and the operator name that allows you to use this syntax. There are no restrictions on parameter type. It doesn't have to be the same as the receiver type. For instance, you can define a function that multiplies the point and an integer number. There is a similar list of unary operations. Unary operator is a function without arguments, which you can call as an operator on the specified receiver. Here is the list of unary operators. Prefix and postfix forms of increment and decrement operators have the classical semantics. There are two possible meanings for the plus assign operations. At first, it might be resolved to a plus function if the mutable variable is changed. That means you simply modify its value. Another option is the plus assign function. If it is defined, then this operation might be resolved to plus assign call under the hood. This convention works for list. If you use plus on a read-only list, pay attention that then it will create a new list and return it as a result. For mutable list, you can use plus assign and it calls the corresponding plus assign function. It's a bit confusing. To better understand that, answer this question. What is printed in this example? There are two options. What's going on here is that we use not the right convention for list. List 1 is defined as a mutable variable which stores a reference to a read-only list. We need the list2 variable purely to observe the initial list. The plus assign operator doesn't modify it, but rather creates a new list and returns it as the result. In general, it's wrong to write the code like this. Under the hood, a new list is created if you define a read-only list as a var and add something to it. Be aware of that. It's another reason why to prefer val to var. Such a mistake can be done by someone new to Kotlin. If we replace list of and var with mutable list of and val, then we get what we expect. Both references just observe the modification. Now you know how to define arithmetic operations for your custom classes. Next, you see how you can add comparison operations accessing by index and what other conventions are supported. In this video, you'll learn that many things that may look like built-in language constructs, like accessing map elements using square brackets, actually work via conventions, and the same syntax might be supported for your custom classes. In Kotlin, you can compare strings using this nice syntax. And not only strings, but any classes that define comparator method. Under the hood, the comparison operators are all compiled using the comparator method comparisons. Note that if your class implements comparable interface, then you can automatically compare its instances using this nice syntax. Equality check, as we've already discussed, is compiled to calling equals under the hood. It not only invokes equals, but also correctly handles nulls. You no longer need to remember to check a variable for being not null before equality check. When you access elements by index, that also works through a convention. Under the hood, the get and set methods are called. You can define get and set operator functions as members or extensions for your own custom classes. Note that you can put several arguments inside square brackets. In also works through a convention. When you check whether an element belongs to a map, a list, or a range, under the hood contains is called. Creating a range is another convention. Whenever you use the double dot syntax, you actually call the range to operator function. That means you can support the same syntax for your custom classes. For loop iteration also works through a convention. In Kotlin, you can iterate over a string. I've told you that Kotlin string under the hood is a regular Java-lang string, but Java-lang string doesn't implement iterable interface, so in Java you can't iterate over it. In Kotlin, that's possible because we can define this iterator operator as an extension function. Destructuring declarations allow you to define several variables at once by assigning one expression and automatically destructuring it. We've already seen the examples of destructuring declaration syntax in the course. Here, in both cases, we initialize two variables using one pair, and the pair components are automatically assigned to the first and the second variables. The similar destructuring works in a for loop or for lambda argument. Note that you always put the several variables that you want to initialize after the destructuring inside parentheses. That all works through a convention. Under the hood, the assignment syntax is compiled to calling component 1, component 2, etc. functions. Whenever the expression has the right number of operator component and functions, it can be used as the right-hand side for destructuring in initialization, also in a for loop or inside a lambda. The Kotlin compiler generates the code using component functions. Note the difference between declaring two parameters and declaring a destructuring pair inside of a parameter. You always surround with the parentheses the variables which are the result of the destructuring. Note that iterating over a list with its index also works using destructuring declarations. With index, extension function returns a list of indexed value elements. Index value has component 1 and component 2 defined, and therefore can be used with destructuring syntax. You rarely need to add component operator functions by hand. You can use any data class as a right-hand side for the destructuring declarations, since the necessary component functions are automatically generated for it. Component methods are the remaining methods that we haven't yet discussed, which are automatically generated for data classes. The order of the destructured variables is set. For data class, the compiler simply follows the order of the constructor val arguments. Note that you can omit one of the new variables if you are not going to use it. Put underscore instead of its name. Then it takes part in destructuring, but the variable is not created. Pair and index values classes are simply defined as data classes in the library. That's why the destructuring syntax works for them. The question: after declaring which function, you can use the following nicer syntax for your custom board class. The options are: it's enough to add set extension function, you need operator get function in this case, or operator set function. The right answer is operator set function. You need the operator keyword to make the syntax work, so the second function is not enough. In this case, we use the syntax for modification, and that's the set operator. Note that as for regular functions, the types don't need to be exact. You easily can define parameters of any type and pass ints as arguments. When you define set operator, no additional get operator is required. This short syntax is replaced with the direct set function call in the bytecode. Another question: which elements do you think can be compared using these comparison operations? And there are options: all primitives like int, double or boolean, strings, elements implementing a variable interface, or elements that define member or extension operator function compared to. Note that several options might be true here. We can't compare booleans by this syntax. What is greater, true or false? That doesn't make any sense. All the rest elements can be compared using this syntax. Because the conventions work through extensions, you can define an extension function compared to your class and implement the necessary logic there. Imagine for the purpose of your algorithm, you need a specific way to compare, for instance, points. If point implements comparable, then the comparison logic becomes available everywhere. But if you define the comparator extension, you can make it private or internal in your module, so that it was available only for the purposes of your algorithm. Then the operator syntax isn't visible for other parts of your application that use the same point class. That's a powerful way to limit visibility, but make things convenient enough for some small parts. You can ask how it works with Java, whether it's possible to use Java classes via the same conventions. The answer is yes. Operation syntax works for all Java methods with the right signature. In Java, there is no operator keyword, but if Java method happens to be named in the right way and to have the right signature, you can use the operator syntax for it when you use this Java class from Kotlin. If a method is called differently, you can always add an extension and use it from Kotlin in a nicer manner.
You've learned a language mechanism called conventions that allows you to use language constructs like accessing by index or for loop iteration with your custom types. This discussion completes the module. The next module will return you to the topic of functional operations on collections, and we'll discuss how they might work under the hood, what are sequences, and when to prefer sequences over collections. Also, we'll discuss the correspondence between Kotlin and Java types. Can you give some use cases when to use and when not to use operator overloading?
Operator overloading is a very powerful mechanism, but with a lot of power comes a lot of responsibility. And this is why Kotlin only provides a very restricted version of operator overloading. For example, you cannot invent your own new operator or alter precedence of existing operators. All you're allowed to do is overload a predefined set of operators. These are mostly related to arithmetic, indexation, comparison, so on and so forth. So it can be very tempting to abuse this and make up your own syntax, so to speak. Like, for example, one can think of a path class that uses a slash operator for concatenation, making like Linux-like /separated path objects. But I would say that this is already an abuse of the language mechanism. So you're supposed to use slash for division and plus for sums or concatenation, so on and so forth. So my advice would be to only use operator overloading on the abstractions that have natural, commonly acknowledged operations signified with the symbols we have in the language. So use it with care, and it will provide for a readable, intuitive code.
Why does Kotlin rely on naming conventions and not interfaces?
Customizable language constructs are very useful. Iteration is an archetypical example of this, where you have a for loop that's customizable through a user-provided iterator, for example. And there, Kotlin relies on naming conventions and not interfaces, like Java does. There are reasons to it, and one is that such an iterator method or any other convention-provided operator can be supplied through an extension, which makes it possible to add these things to classes not under our control. For example, classes sitting in libraries or JDK or something in a different module, something that I cannot simply add a method to, at least easily. So that's one important reason. And the other is it again provides a way of decoupling the additional operations, utility things, from the essence of the abstraction. So if iteration, for example, is not an intrinsic part of your class and just a convenience, you can put it into an extension and separate from the clean interface you keep with your members. So two ideas, minimal abstractions and extending existing code, basically the same as we have for keeping extensions in the language.
Let's discuss how rational assignment can be implemented. The first question you probably ask yourself when starting to implement this assignment is when and where to perform the normalization. Two rationals in a non-normalized form must be equal to each other. For instance, 1/2 might be represented as 2 divided by 4 as well as -1 divided by -2. The normalized form is 1 divided by 2. You might decide to store the fraction in a normalized or non-normalized form, define the rational class as data class or not, and perform normalization in a primary constructor or outside of the class. Let's discuss and compare these choices. To perform the normalization, you find the great common denominator of numerator and denominator, and divide both numerator and denominator to it. For instance, in this example, the great common denominator of 6 and 14 is 2. So we divide both 6 and 14 by 2 and get 3 divided by 7 as a result. The code of the normalized function does exactly that. To find the great common denominator of two numbers, we use the GCD method on big integer mentioned in the assignment description. Note, however, that in the normalized form, the denominator is always positive. Only the numerator can be negative. Thus, if the initial denominator is negative, we need to change the sign of both numerator and denominator. In other words, we need to multiply them both to -1. To achieve that, we multiply both numbers to the sign variable, which is either 1 or -1. Now let's discuss when we perform the normalization. Specifically, whether we want to store the values in a non-normalized or in a normalized form. You can decide to store a rational number in a non-normalized form, but then you'll need to repeat the normalization for many operations. For instance, toString should print the normalized form of rational. When we check whether two numbers are equal, we need to compare their normalized forms. Then equals and hashcode need to perform normalization, but then their implementation becomes really non-trivial. What's more, when you want to add some functionality in the future, imagine you add the possibility to compare rationals at some point later, it's so easy to forget about the normalization. The contract that you need to perform the normalization for all internal methods is implicit, so this approach is too error-prone. If you don't need to store the initial values, creating rationals in the normalized form is less error-prone than having a hidden implicit contract to perform the normalization before doing anything meaningful with the values. Okay, we've decided that we perform the normalization when we create the class and store the values in the normalized form. Now toString can return the straightforward representation. But the question still is, where do we perform the normalization? It seems it's not possible to do that in the constructor of such data class, because we can't modify the read-only properties. What are the other options? That might be implemented in many ways, and many solutions will pass all the tests. However, let's discuss what are the pros and cons of each one. Probably it's the first idea how to implement that. Define data class with var. Then you can update the values in the constructor, because now you can modify them, and store rational in a normalized form. However, this solution has a huge drawback, that now you can modify the rationals outside of the class. All the properties are now mutable. Now we have a similar problem again. We have the assumption that no one should modify the property values, but we don't express this contract anyhow in the code, it's hidden. The design of this class is unclear. Rational number looks like an immutable entity, but you allow to modify it via its public API. Thus, this approach again is too error-prone and inconsistent. Ideally, the class should specify in its API how it is intended to be used. If the properties are not supposed to be modified outside of the class, such modification should be forbidden. In general, try to avoid defining mutable properties as parameters in data classes. It is not forbidden by the compiler. Sometimes you might need that, for example, for performance reasons. However, in a general case, try to pick up the alternative solution. Data classes with vars have too many possible problems. Imagine you store a value of such data class as a key and a hash map. Then modify the property values. If you don't override the hashcode and equals methods properly, the map falls into an inconsistent state. The instance is stored by its old value of hashcode, but now the new value is returned. Map_of creates hashmap, and this hashmap stores values using their hashcode. When you ask for an element by a given key, such map first checks whether it stores any values with the same hashcode. If it doesn't, then it just says no such element. Using hashcodes is the core idea of hash sets and hash maps. As a result, you observe some mysterious bugs. The data is not found in the map, but it's there. And your application crashes, or user gets incorrect data, or the purchase is lost, or the flight is delayed, or a self-driving car without passengers crashes into a tree just because you used mutable property in a data class, and somehow it got modified. If you accidentally modify this mutable property, you can get too many mysterious problems. If you need mutable properties parameters in data classes, justify why you need them and why you don't have alternative ways to express the same logic. Consider making them private. And don't forget to redefine equals and hashcode so that the modification didn't change the state. Note that if a mutable property can be excluded from equals and hashcode, then you don't need to define it as a constructor parameter at all, because all the properties inside the body are excluded automatically. Probably you simply don't need data class with mutable properties, just a regular class instead. Let's return to our assignment. Where to put the normalization then? You can move the normalization logic outside of the class and say one needs to create rationals only by special means. It works, but the problem is that it's too easy to create a non-normalized version of rational. You have to be very attentive that you don't invoke rational constructor and you only create rational via this additional method. For me, it also looks error-prone because again we have a hidden construct that is not expressed in the code. Here the construct is use the createRational method to create instances of rational class. But this construct isn't clear from the code. Even if you add the command, no one reads the commands while browsing through the available methods in the completion, and the method will definitely be called by someone someday. What can we do here? We can make the constructor private. In this case, we show explicitly that this class is intended to be created by some other function. Now this construct is explicit, so can't be accidentally broken. You just can't call the constructor, it's not visible in the API. We moved the create and normalize functions to companion object. We call a private constructor inside the companion object, and now it's impossible to create a non-normalized version of rational outside of this class. Of course, you have to be careful and call only createRational methods inside the class. However, if you write this code, you'll see the warning that private data class constructor is still exposed via the generated copy method. In this case, we can suppress this warning. Note that you can simply call an intention in IntelliJ IDEA. You don't need to look up the warning name to suppress it. The next solution is to define a known data class. In this case, you can perform all the normalization inside the constructor, because you define constructor parameters and properties that store a numerator and a denominator separately. Now you can use the normalized values of the constructor parameters to initialize the properties. The normalization takes place inside the init section. This solution is also a good one. However, don't forget about equals and hashcode here, because we need to compare instances. For data classes, we have equals and hashcode generated by the compiler. Here, it's not the case, so we have to write them by hand. Note that IntelliJ IDEA can generate them automatically. There is no need to implement them by hand. Just choose to generate equals and hashcode. Don't forget about the hashcode. They must be consistent. That's why IntelliJ IDEA nicely suggests generating both of them at once. What happens if we forget about hashcode? For instance, we redefine only equals without hashcode. The smaller question for you that helps to answer the first question is, what will be printed in this example? The answer is null. At first, these two rationals, 1/2 and 2/4, seem to be equal, because equals returns true, However, if we put these rationals in a map, we get null as a result because these values have different hash codes, and map decides that there is no element with the same hash code. Another thing I want to mention about implementing rational is the idea of checking prerequisites. If the denominator is 0, we need to throw a legal argument exception. Require does exactly that. You call require and tell which conditions must be satisfied. Then require throws a legal argument exception with a specified message if the prerequisite is not satisfied. By the way, note that you can import the constant and use it by name. If the constant name is self-descriptive and is clear from the context, you don't need to use the whole specification. You can import the constant name. Then we need to implement a convenient way to create rationals. Note how we've defined an infix extension function for basic types. Making this function infix allows us to use this nice syntax. In order to implement operators, you define them as operator functions and simply follow the formulas. In this case, the operator functions are member functions which are defined inside the rational class. Here, the numer and denom variables refer to member properties. You can also define operator functions as extensions. It's more a matter of choice. The same for plus and minus operators, then times and division. They all can be either members or extensions. Note that in Kotlin, you can use operator syntax for big integers as well. You don't need to call explicitly times and plus. The operator syntax works. The necessary operator functions are defined in the Kotlin standard library. To compare two rational numbers, we again use the formula. Note that the easiest way to make all the comparison operators available for the class is to implement the comparable interface and its comparator method. There is no operator modifier because it's an overridden method here. Note that you don't need to create the separate class rational range. Belonging to range automatically works if your class implements comparable. The Kotlin standard library contains the closed range interface and its comparable range implementation. Whenever you use double dot syntax on two comparable elements, an instance of the comparable range is automatically created, and you can check for belonging to this range. The last thing I wanted to talk about is converting a string to a rational number. I'm showing you one way to implement it, but note that there are also other possible ways. At first, you need to check whether there is slash in this string. If it's missing, you expect an integer number and create a rational from it. Otherwise, you split the string and create a rational using both numerator and denominator. The first thing we can improve here is the result of the split function. We can use distraction declaration syntax while having list or array on the right-hand side. Several first component functions are defined for them. The first element will be assigned to the first variable, the second element to the second variable, and so on. Now it looks a bit nicer, because we give explicit clear names for these two parts. The next thing that should be improved in this function is throwing the clear error message if the output is not correct. If we call this function on the wrong output, we'll get number format exception. But we prefer legal argument exception with a clear message, expecting rational the corresponding form but was this string. It's the more clear message saying exactly what's going on. We can use 2-big integer or null instead of 2-big integer. If null is returned, then we throw a legal argument exception with a detailed message. However, there is some repetition here, because we need to repeat throwing the same illegal argument exception 3 times. We can extract it to a function. In Kotlin, you can extract throwing an exception into a separate function. You only need to define the type nothing for that. We are discussing the nothing type in detail in the last module in this course. However, there is still some repetition. We repeat here 2-big integer or null call and then the fail function call 3 times. We can improve it even more. We can define a local extension function that does 2 operations. First, it tries to convert a receiver string to big integer. Then, if null is returned, it throws our illegal argument exception with a detailed message. So, what is the main benefit of it? Now we separated the function logic and error reporting. The code that does the conversion looks almost identical to the first version without error reporting. The error reporting logic is extracted into a separate function. Since it's local, it can't be used outside of this scope, and it doesn't really make sense to do that. You also don't need to pass an extra string parameter to it. The receiver of the RT function is nicely captured automatically for us. With that, I covered the major points about this assignment. I hope you find it useful.
This task is to implement a val property that returns you a new value in each access. One way to do that is to define another variable, another property, and while returning it, also modify it. For instance, we can count how many times this property was called, and you see that it returns us a different value in each access. Another solution would be to simply use random. So we can say random next int, and that also gives us different values when we access them. So this Kotlin random API appeared in Kotlin 1.3. Note that in 1.2 you can use only Java 2 random. Hey, what's going on? So the main purpose of this task is to illustrate to you that the way to think that of a property as something immutable, as a mutable property, that's wrong. And I've seen sometimes such confusion that people think of it as immutable and can be really surprised that it's actually not. So it can return you a different value. And that's why it's more convenient to think of a property of a val property as read-only property. And that's why we use these terms to avoid confusion. And the thing is that it just means that you cannot reassign it. So this corresponding property doesn't have a setter, but you can do whenever you want inside the corresponding getter for val. This task allows you to better understand how latent properties work. At first, we need to write the code in a way that an exception was thrown. That's very easy. We just need to forget to call setup. And in this case, we see an exception that our latent property value has not been initialized. And that's a rather clear exception because it clarifies what went wrong. And also, such exception, you may find it if setup was wrong or you forget about something, but it won't happen unexpectedly because of wrong input or so. So it's not that bad as regular null pointer exception. And to fix it, you simply call setup method in the right place. And probably usually it's happen automatically by using a framework. But in this case, now everything works. Our task here is to add something to the implementation of the A class so that null pointer exception was thrown. This example illustrates a rare case when null pointer exception is still possible in Kotlin, in pure Kotlin. When you mix Kotlin and Java, you can have null pointer exceptions. We discuss the details, how it works in the next module, and also we'll discuss how to possibly prevent that. This example illustrates null pointer exception in pure Kotlin code. However, with a warning, so Kotlin compiler still tries to warn you against possible problems. And we'll discuss what's the problem here. To get null pointer exception here, you simply call any member on value. For instance, we can call length. If we run this code, we'll see that indeed null pointer exception is thrown from this line where we dereference value. And the Kotlin compiler tries to warn us because it says you try to access non-final property value from the constructor, and that may cause problems. It's an anti-pattern like in Java, don't do that, but it's still possible for some cases. To better understand what exactly is going on here, let's look at the same class as written in Java. In this case, we have class A that has property value. Let's comment it by now.
which we initialize in the constructor. So in Java, the same class will be written like this. We have the class A, we have private field. In Java, we write fields directly. We have the constructor, and we have getter that returns the field value. When we return to class B, in this case, we use the syntax override val value, and that will generate extra field. So in Java, we'll do the similar thing, but we will override the getter. If you, in Java, right now, do write the same code as in Kotlin, but in Java, you'll call get value and call length on it, then you'll have null pointer exception. Because in the constructor, you are calling getter, but this getter is overridden. So instead of getter from A class, getter from B class is called, and that returns you another field, the value of another field, which is not yet initialized when the constructor of A is called. And that's why you get this null pointer exception. Because here in this case, the second field in the class B is not initialized. If you say value here, everything works because it's field. Here it's even the parameter. But the problem is calling an open non-final method from the constructor that might be overridden. And in Kotlin, the problem is the same. If you call the non-final method from the constructor, you'll get null pointer exception. What we have here in Kotlin, here you somehow want to override property, but in this case, it's not needed. You can simply define the constructor parameter and pass it to the outer class. And in this case, if you don't need to redefine the behavior of the getter, you can omit this open modifier if they are defaults. Then you may write the code like this. And in this case, there is no problem. There is no null pointer exception anymore because you just dereference the final property, the one that is initialized already. And you can access the value because it's simply inherited. Now you understand how that works, why here we have null pointer exception if we have overridden the property. Sometimes you still may need this functionality, but that's something to be aware of, that it may cause problems calling open members from the constructor. So it works the same as in Java. You can have the same possible problems as in Java here. Our task here is to implement equality without using equality. So we may only use equals and reference equality. So the task helps you understand how it works. And we could simply call equals, but that's won't work because nulls are processed properly in Kotlin. So you can see that both arguments might be null if you use equality and that result in true. Only one argument might be null, any of them, and that results in false. So here we have to express that properly, and we can use safe access here, but then we'll need to say what to do in the other case. And in this case, so if the first value is null, then if the second value is also null, then the result is true. If the second value is non-null, then the result is false. And we can express this by checking the second value for being null reference. We can run it and make sure that we have all OKs. Yes, everything works. So this task illustrates how you can rewrite this equality and what the compiler does under the hood. But obviously, in the bytecode level, there is no safe access operator, so they're just implemented directly. Note that if you omit the parentheses here, then the result will be wrong because in this case, at first, safe access, the analysis operator called, and afterwards the result is compared with null, which is wrong, which is not right. So use the parentheses, as I've told you before. It's safer to use the parentheses to avoid some kind of mistakes, especially if you mix some Elvis operator with arithmetic operations. So with all these checks, you may check the operator precedence table, but just putting the parentheses is a really safe approach.
In this section,
you'll learn how the mechanism of inlining makes it possible to create library functions that look like built-in language constructs. Under the hood, lambdas might be inlined, which creates no performance overhead. We'll discuss what does that mean, how inlining works, and why it's important. But before we start, let's look at some small library functions so that we could later discuss why we can use them without any performance drawbacks. We already saw the run function. At first sight, it looks like a built-in language construct that runs the block of code and returns the result. But in fact, it's just a library function that takes a lambda as an argument. The curly braces in bold here mean that it's really a lambda. Another helpful function is let. This one can be used for coping with nullable types. You already learned many ways to work with nullable types, especially when you use expressions of nullable types as receivers, when you call a member or an extension on an expression of a nullable type. However, there are often cases when you want to pass something as an argument, only if it's non-null. For instance, here we have the getEmail function that returns nullable email. We want to send an email only if it's non-null. If it's null, then we do nothing. You can use explicit if check for that, but let gives you an alternative. What you can do is you can use let, which introduces a new name for the receiver. Then you can access the receiver inside the lambda by the name of the argument. Note that here we use safe access. That means that we call the let function only if the receiver is non-null. We perform the send email action only if the email is non-null. You can use the whole expression as the receiver. You no longer need to introduce a new variable to be able to smart cast it. In a sense, let itself introduces a new variable. Its name comes from functional programming, where let is used to introduce a new variable. Kotlin is not a pure functional language. You can just declare a variable. There is a syntax for that. However, for such use cases with nullability, let is really useful. To better understand how it works, answer the following question. What is the type of it in the code below? The answer here is nullable email. The problem is that we forgot to use safe access. That can happen that you remember to use let to cope with nullability, but forget to use it with safe access. Then it refers to get email directly and has a nullable type. The compiler then gives you an error about type mismatch. You can't call the send email to function, which expects a non-nullable value, and you can be surprised, like why. The trick with let works only if you use safe access. Because you call the let function only if the receiver is non-null, then it is known to be non-null inside the lambda. Now the type of it is email. Another example for let and nullability. Now it's nullability and safe typecast. Remember the example when we have a property defined in an interface. It's an open property, that's why you can't smart cast it. The compiler doesn't know how it can be overridden in the subclasses. To smart cast, you need to copy the property to a new local variable. Let gives you an alternative. If the property session user can be cast to Facebook user, we perform an action on it. Otherwise, nothing happens. The meaning of two code snippets with explicit if and let is the same. Using let is just another way to write it. Here we use safecast, as with question mark, to check of being the right type. If the cast is successful, then the result is non-null. In this case, we call a let, and inside let, our lambda argument has the required non-null type. At first, this new let way might look inconvenient and unfamiliar, but I suppose after some time you'll get used to it and prefer using it more often. Now let's go back to our discussion of useful functions in the library. Another one is takeIf, which returns the receiver if it satisfies the given predicate or returns null. Here the result is the value of issue variable itself if its status is fixed and null otherwise. Or we might want to replace the patronymic name with null if it's empty. Take this string if it is not empty does exactly that. The question for you is, what is the result of the call below? In this case, The receiver satisfies the predicate. Number is more than 10, so the receiver itself is returned. Otherwise, null would be returned as a result. The takeIf function is extremely helpful in side-chained calls. Imagine you need to continue a list of operations only if a predicate is satisfied. You can call this predicate on the result of the previous expression in the call chain. Using the save operator after takeIf result continues the calls only if the predicate is satisfied. Otherwise, you have null as the result, and all the rest calls won't be called for you. Here, the line "there are some open issues" will be printed only if the filtered open issues list is not empty. There is the opposite, take unless, which returns the receiver if the predicate is not satisfied. There is another function that looks like a built-in language construct. It simply repeats an action for a given number of times. It's very convenient, and instead of for loop with the indexes, for simple scenarios you can use repeat. Again, the same pattern. Repeat is not a built-in syntax, but a function defined in the library. Here you can see the declarations for all the functions we've just discussed. Run only runs the lambda, let runs the lambda on the receiver value, the receiver becomes the lambda argument, takeIf and take unless nicely replace if in call chains, and repeat is an alternative for the for loop. New syntax is used here. All these functions are declared as inline functions. Because of that, using these functions doesn't bring you any performance overhead. Next, we'll discuss why and why it's so important.
In this video, we'll slowly unwrap how inlining works and how it's different from non-inline case.
Let's imagine we define our run function as a regular function without the inline modifier. What happens then? When we call a function that takes a lambda as an argument, under the hood, to store the lambda, an anonymous class is created. If the lambda captures some variables, then a new object will be created to store the content of captured variables for each invocation. That's quite an overhead for such a simple case in terms of performance. In comparison with simply writing the code without run function with lambda, that would be a considerable difference. If we defined the run function like this, then probably there would be style guides that would recommend don't use run in a performance critical part of the code, use it with care, be aware that under the hood there is an anonymous class corresponding to this lambda. It wouldn't be zero overhead to use run in your code. With inlining, it's no longer the case. Inlining a function means that the compiler substitutes the body of this function instead of calling it. If the inline function takes a lambda as an argument and only calls this lambda inside, then inlining will substitute the body of the lambda instead of the code that calls this lambda. Run is the simplest example. It only calls the lambda and does nothing else. At the bytecode level, while generating the code for the run call, the compiler, instead of calling run and creating an object for the lambda, will generate the lambda body directly. As a result, we have no performance overhead of creating an anonymous class and an object for the lambda. Again, in the case without inline, we have the performance overhead in comparison to writing the similar code without run. When we make it inline, it stays the same. The generated bytecode doesn't differ from the code without run. That was a trivial example. Run simply calls the lambda. Now let's look at the take unless function that does something less trivial. It contains some logic with if expression. Instead of calling the take unless function in the bytecode, the compiler inlines it and substitutes its body. Instead of the lambda invocation, it substitutes the code of the lambda body. You can see here that instead of creating an object for lambda, we have the lambda code written directly in the resulting bytecode. Of course, the compiler imposes some constraints of what can be done with lambdas inside inline functions. You can't store the lambda anywhere, you can only call it directly. Then it's possible to generate the lambda code in place. All mentioned library functions simply call the lambda by 0 several times, but don't try to postpone the call. Let's look at another example. Java has the synchronized language construct. In Kotlin, a similar construct can be defined as a function in the library. When the synchronized function is marked as inline, that means it produces no performance overhead. In the resulting bytecode, the whole function body is substituted instead of one call. The compiler generates the body of the synchronized function, replacing the parameters usages with actual arguments passed. Whenever the compiler finds the lambda invocation, it generates the lambda body instead. Note that whenever you need to do something with logs, instead of synchronized in Kotlin, you can use with log. It does a similar thing, but it is defined as an extension. You call with log on the log object. Yet another function to illustrate the pattern that in Kotlin some functions look like built-in language constructs and replace built-in language constructs, but in fact declared as functions in the library. In Java, we have try with resources syntax. The try expression can close your resource in the correct manner if an exception was thrown. It correctly propagates the initial exception if another exception is thrown when you close the resource. In Java, it's a special construct in the language. In Kotlin, all this logic is defined inside a regular library function. This library function is defined as inline, so there is no performance overhead because of lambdas. The use function contains all the aforementioned logic of closing the resources in the correct way. There is no performance overhead when you use the library functions like run or let. No anonymous classes or extra objects are created for lambdas under the hood. It's free to use these functions in your code. You can note that the filter function is also defined as inline. We'll discuss in the next section what consequences we have because of that for operations working with collections. But for now, to better understand how it works, do this exercise. Write the code that will be generated for the filter function. Perform the exercise right after the video in the Kotlin playground. Write your solution and then check the proposed solution in a separate video. One more question before that. What do you think? Will the filter function be inlined in the bytecode if you call it from Java? I've already told you that this filter function is defined in the library as inline. Yes or no? The answer is of course no. Inlining is the feature of the Kotlin compiler. Whenever the compiler sees that the inline function is called, it will generate the body of this function instead of one call. But Java doesn't know anything about inlining. From Java, you can easily call the Kotlin functions, but this magic of inlining happens only inside the Kotlin compiler, not inside the Java compiler. From Java, inline functions are called like regular functions. Nothing is inlined. If you navigate to the sources of the mentioned functions, you'll find out that the majority of them are defined as inline only. That means these functions are always inlined. If the library function is always inlined in Kotlin, there is no sense to store it in the resulting jar file when you build your application, so that decreases the size of your application. Inline-only annotation marks which functions can be removed from the resulting jar. That means you won't be able to call them from Java. They are only accessible and visible from Kotlin. This annotation is internal and intended to be used only in the standard library, at least so far. By covering this internal annotation, I'm trying to explain how that works and share the power of the Kotlin standard library.
Note that the main disadvantage of inlining is the size of the resulting application, because for each inline function, when you call it, its whole body is substituted instead of only one function call. Thus, only small functions must be inlined. By default, don't define your functions as inline. Hotspot, when running the bytecode, does the good job of optimizing and inlining pieces of code that are really frequently used. So don't do the premature optimization. We spent a lot of time discussing inlining so you can better understand the language and its powerful library. However, don't overuse inlining. Use that with care. You now know about such library functions as run, let, take, if, repeat, or with log, and you can use them in your code. And you know that using them doesn't affect performance because they are declared as inline and no extra objects or classes are created when you pass lambdas as arguments.
Next, we'll discuss how inlining affects functional operations on collections. When does it make sense to declare your own function as inline?
So it can be very tempting to use inline functions for performance optimization in your code. But here's where I have to warn you against optimizing prematurely. Most of the time, you don't really need inline functions in your application code. If you really see that something is affecting your performance, here is what inlining is good for. So first of all, since virtual machines are really good at inlining at runtime, you don't really need inlining for eliminating stack frames. So it's not for having less calls. What it's good for is to eliminate allocations of Lambda objects. So if you have a higher order function that takes a Lambda, and you're calling it somewhere in a tight loop, for example, and allocations really affect your performance, you can optimize this away using inlining. But again, use it with a lot of care. There are other use cases for inline functions, but they will be covered in the next chapter of this course.
In this section, you'll learn about sequences and the difference between the same operations on collections and sequences. All the extension functions for collections, which allow us to work with collections in a functional style, are defined as inline functions. As we discussed, that means their bodies are generated in the bytecode instead of function calls. Another thing that we can notice looking at declarations is that these functions return new collections. For instance, filter creates a new collection that contains the result and returns it. To make sure you understand it, answer this question: how many collections are created while running the code below? The answer is 3. Let's count all the intermediate collections. At first, we create an initial list, which contains all the elements. Then, when we call map, map creates a new collection and returns it as a result. Then we call filter. Filter, on its turn, again creates a new collection and returns it. At last, we call max, which just returns the value. That makes it 3 as the answer. When you use simple operations on collections, all the intermediate collections are created, and that's something to keep in mind. The benefit of inlining the lambdas is, as we already know, that there is no performance overhead. And that truly works great, especially when you only use one function. For instance, when you need only filtering, you call filter and everything is fine. However, if you have a chain of calls, several calls one after another, then you'll have a different kind of problem. Probably a bigger performance overhead because an intermediate collection will be created for each of the chained calls. There is an option how to avoid it. This option is called sequences. Sequences can be compared in a sense with Java 8 streams, because sequences and streams both perform computations in a lazy manner. The Kotlin sequences are called sequences because the name streams was already taken. When we mix Kotlin with Java, we want to avoid the confusion with clashed names. If we use operations on collections, they eagerly return the result, while operations on sequences postpone the actual computation, and therefore avoid creating intermediate collections. How to convert from list to sequence? That's very easy. You just add a sequence method which builds a sequence from a list. After that, you can call all the same methods that are available for regular collections. If we try to print out the result, we see that there is no intermediate collection. Sequence objects are printed. These objects somehow store the reference to the first collection together with all the operations that need to be performed, but they perform the postponed computation only when the result is required. In the next video, we'll discuss how exactly it works in detail. In this video, we'll compare operations on collections and sequences in detail. Let's look at a specific example of chained operations for working with a collection. It produces an integer result. First, we use operations on collections. To convert it to sequences, we only need to add a sequence as the first operation. That will perform all the operations in a lazy manner. Let's discuss in detail the difference between eager and lazy evaluation. When you call the chained operations on collections, each operation produces a new collection as an intermediate result. It computes the result in an eager fashion. You can always observe the result after an intermediate stage. When you use sequences and lazy evaluation, nothing happens until the result is needed. All the transformations for the first element are performed only when you call a terminal operation that requires the previous results. In this example, with sequences and lazy evaluation, we perform all the transformations for the first two elements and then find already finds the answer and returns it. That means that we don't need to perform any operations for the rest elements. We don't need to transform them because we've already found the answer, so the result is not needed. That illustrates the laziness of the operation. We don't do anything unless it's needed. If we found the result already and some operations remain, then we don't perform them. Eager evaluation always performs all the operations for all the elements. That's the difference. Sometimes the terms horizontal and vertical evaluations are used to describe the same idea. With horizontal evaluation, you apply operations on the elements in a horizontal manner. At first, you perform all the operations for the elements in the first collection. Then you perform the operations for the elements after the first transformations, and so on. With vertical evaluation, when the result is asked for, you first process the first element and all the chained operations for it, then you apply all the chained operations for the second element, and so on, until the result is found. To practice your understanding, write the output after the evaluation of the expressions below. At first, we call the operations on collections and then replace them with sequences. Operations on collections first apply map to all the elements of the list, then apply filter to all the transformed elements. First all maps, then all filters. Here is the answer for the next line using sequence. Operations on sequences first apply map and filter to the first element, then map and filter to the second element, and so on. An interesting thing is that here in the last line, nothing is printed. Nothing happens until the terminal operation is called. The operations are lazy, and until you explicitly ask for the result, nothing will happen. The intermediate sequences only store the operations to be performed. You can ask what is the difference between intermediate and terminal operations. It's very simple. Intermediate operations return you another sequence, while terminal operations return you everything else. It might be a collection, sum of the elements, a value, a Boolean result, whether there are any elements, no elements, and so on. Until you call this last operation, nothing happens. Note that when you work with sequences, the order of the operations might be important. Sometimes you can apply the transformations in a different order. For instance, here, if we first call map, then filter, then map will be applied to all the elements. If we switch them, however, then map will be applied only to the elements that weren't filtered out. It's not always possible to switch the order of operations, but if it's possible, it might change the number of the resulting operations that will be performed. To practice that, write the output after the evaluation of the last expression. This exact example is illustrated in the previous picture. We filter out the first and third elements, and that means we don't apply map to them. We only apply map to the elements that remain after filtering. Operations on collections are inlined. That works great for simple cases, but creates a significant performance overhead for chained calls, because intermediate collections are created. Sequences solve this problem by storing operations to be performed and evaluating them in a lazy manner. Operations on sequences mainly duplicate operations on collections. You can convert your chained calls from collections to sequences by adding a sequence at the beginning.
Now you know how to avoid creating intermediate collections for chained calls using sequences. Next, let's discuss how you can create sequence from scratch when you don't have an initial collection you can convert to it. In this video, you'll learn about different ways to create a sequence.
Sequence is a regular interface defined in the Kotlin standard library. It has one member function iterator marked with the operator modifier in order to make it possible to use sequence in a for loop. Note that despite sequence is very similar to iterable, which is implemented by all the collections and iterable ranges, they are defined as two different interfaces in order to distinguish eager and lazy ways of performing operations. Extensions on sequences mostly match extensions on iterables or collections. Having similar names for both groups of extensions makes it really easy to change from eager to lazy evaluation. You only need to add one as sequence call at the beginning of the call chain. Intermediate operations, the ones that return another sequence, are not marked as inline. The operations to be performed must be stored to make it possible to call them later. Postponing the operations until they are needed is the core idea of the lazy evaluation. Because the action in a lambda must be stored somewhere, that means that the corresponding lambda cannot be inlined. Terminal operations which return a primitive value or a type or a collection can be declared as inline. If you need to build a sequence from scratch, for instance, you define a way to receive each new element from the network, you can use the generate sequence function. Here, it generates a sequence of random numbers. When the lambda that computes each new element returns null, the sequence is finished. Note how we used the takeIf function to check the predicate and return null if this predicate is not satisfied. The generate sequence function can be useful when you need to read input and stop when a specific string is typed. You can use another overloaded version of the generate sequence function. It takes the first element and the way how to compute each new element based on the previous one. In this case, we generate an infinite sequence of integer numbers. Note that because the sequence is computed lazily, it might be infinite. Nothing happens until you explicitly ask for it. In this case, we only ask for the first 5 elements, and they are returned. Note that because the same integer types as in Java are hidden under the hood, you will still have integer overflow. To prevent it, you can use big integers. The question to you: how many times the phrase generating element will be printed in the example below? What do you think? There are the options 0, 1, or 4. The right answer is 0 because we only asked for the first element, and this first element is already given. Because sequences are evaluated lazily, nothing happens until you explicitly ask for it. And here we only ask for the first element, so this lambda is never called. When you explicitly ask for other elements, then the necessary elements are generated. Another important functionality that you can use to generate a sequence is yield. Unlike in some other languages, yield is not a built-in language feature. It's a regular library function in Kotlin. You note the same pattern again. Lots of things are implemented in the library, not as the language features. Yield allows you to yield elements in a custom way. The generate sequence functions that we saw before are quite constrained. The lambda that generates a sequence element must be either based on external sources or based on the previous element, but you cannot really customize that. With yield, you can generate any elements in any convenient order. You need to use yield inside lambda argument of the sequence function. We won't cover the details of implementation of yield now. Partly, we'll discuss that in the next section of lambdas with receiver. However, mainly it is based on the feature of coroutines. Coroutines deserve the whole separate course to be covered properly, so we'll talk about them separately later. For now, we'll discuss how yield works. Here, you see another example of how you can generate an infinite sequence of integers, now by using yield. You can yield one specific value, or you can yield the whole list or sequence. Yield works lazily. It will be called in a lazy manner only when necessary. If something is not required, it won't be computed. You can yield any elements that you want. The core idea is that you can do any intermediate computations between these yieldings. To better understand how it works, answer this question. How many times one of these phrases starting with yield will be printed in the following example? The right answer is 0. It was a tricky question because the take function is only an intermediate operation. It returns another sequence. But no elements are yielded until the terminal operation is called. In this case, no terminal operation is called, so nothing happens. Let's replace the take function with first, which is a terminal operation, and see what happens then. In this specific example, only the first two yield statements will be called. The last statement is not needed because the result is found earlier. Let's see how it works. At first, we yield the first element by calling yield1, but then we filter it out after mapping because it doesn't satisfy our predicate. Only after that, we yield the range of elements 3, 4, and 5 one by one. The first element 3 doesn't satisfy the predicate. Then we have the next element 4, which satisfies the predicate. Because the first function needs only one element, it simply returns the answer. 16 becomes the answer, and only two first yield statements are called. We already found the answer, and that means we don't need to call the last part at all. The result is already found. That illustrates the lazy way of building a sequence using yield. Whenever you need some custom logic to build a sequence, you can use yield. To practice, implement the function that builds a sequence of Fibonacci numbers using yield. You can declare local variables inside the lambda and then use these variables while yielding new elements in a sequence. Do this task in the playground right after the video and later watch the solution video.
In this video, you can practice your knowledge of Kotlin library functions and see that in some cases several chained calls might be replaced with one function.
The following code can be simplified and replaced with only one function call. This function will take a lambda as an argument. Your task is to write only the function name. If you don't know the answer, you can check the completion list in IDE trying to find the right function, or read the documentation, or simply guess, and you learn the answer right afterward. In this case, count will do the job. It's the same as first filtering the collection and then getting its size. Obviously, for one function call, no extra intermediate collections are created. For simple cases, you don't need to create all the ceremony of sequences or streams, you simply call one function. That's the advantage of Kotlin collections and sequences in comparison with Java streams. The simple code doesn't require the ceremony and looks as simple as it is. Do you know how to simplify this code using only one function? In Kotlin, there is a convenient sorted by descending function, which sorts the collection or sequence by a given key in a descending order. The next question is about the pattern when you first map the contents of a collection or sequence and then filter out nulls from the resulting list or sequence. Do you know the name of the function that does this job at one go? That's the map.not_null function. Note that map.not_null performs the same two operations at one go, so it's better than two separate calls, first map, then filter.not_null. When you first stumble upon this function name, you can read it in two ways. It's either first filter.not_null elements, then map only those that are not null, or alternatively, first map the elements, then filter.not_null the result. As you can see from this example, map.not_null uses the second scenario. It's an exact replacement for map plus calling filter.not_null on the result. The first case can be often also expressed using map.not_null. You simply use safe_access or another mechanism to return null from lambda if the element is null. The next question is about another pattern when you need to modify the map element stored by the given key. If there is no element, you need to initialize it. Here we fill in the map from the int key age to a list of people. An initializer for the not analyzed age is a newly created mutable list. If the person is of a given age, it's added to the corresponding list. Do you know how to replace the highlighted code with one function call? Write only the function name. There is the convenient getToPut function, which allows you to either get the value by the given key or put the default value if there is no such key. Note that the second argument for the getToPut function is a lambda, and the lambda body is called only if needed. Here, new instances of mutable list will be created only if they should be added to the map. If there is already age key, no list instance is created. The getToPut function is inlined, so there is no performance overhead from using the lambda. The next question is how to replace this whole code with only one call. Note that the result will differ a bit because it will be a read-only map of int to read-only list. But still, do you recognize this pattern? The right answer to this question is the group by function. It does exactly the same as the code above. It groups the elements by a given key and returns a map from the key to the corresponding group. The next question is about an analog of the group by function for sequences. Do you know how to perform grouping in a lazy manner, like for other operations on sequences like filter and map, without returning the result immediately? Write only the function name. Grouping by does the job. Let's first see what's going on here. You can use group by both on collections and on sequences. It immediately builds a map from the specified key to a group of elements having this key. In this example, we then count each group size and have a map from age to group size as a result. However, sometimes you might want to perform grouping in a lazy manner, so that the actual result or other required information based on the grouping could be later retrieved by request. Grouping by, like other lazy operations on sequences, returns an object storing the operations to be performed rather than the resulting map itself. The grouping object stores the initial sequence and the grouping key so that the actual grouping could be performed when the result is needed. Each count is the function that can be called on such grouping object to get the size of each group. We have the same map from age to group size as a result as before. Later in the next course, we'll discuss other operations that might be performed on the grouping object.
Now you know about sequences and their difference with collections. When you have several chained calls, it's better to use sequences because they allow you to avoid performance overhead caused by creating intermediate collections. And know the Kotlin library because sometimes one function might be present that can't do the necessary job for you. Next, you'll learn about Lambda with Receiver, the feature that is really helpful for creating DSLs, domain-specific languages in Kotlin. In this section, you'll learn about a powerful feature of the Kotlin language, which is called Lambda with Receiver. In essence, it might be considered as a union of two ideas, of two other features, extension functions and lambdas. Now we'll discuss what does that mean.
Let's start with the example. We create a string builder, append some strings to it, and then get the resulting string. Probably, we intend to somehow return it. The problem in this code, a small one, the one that everyone is used to working in Java, is that you have to repeat the variable name several times to call different operations on it. In slides, I have a very short name for the variable, but in real life, it probably will be called string builder, and you will have to repeat this name several times. In Kotlin, you can do better. You can use with for this case. I suppose it should be clear what's going on. You no longer need to repeat the receiver several times. You can call all the members and extensions without explicit receiver specification, like members inside the class. The most interesting thing on this slide is actually its name. It's called the with function. Thus, with is a regular function defined in the standard library. Here we see the same pattern in use as we've discussed before. Something that looks like a built-in language construct is a regular function defined in the Kotlin standard library. In some other languages, with or a similar concept is a language construct. To make it possible to define such functions in the library, Kotlin supports the concept of lambda with receiver. Let's first find the lambda here. With is a regular function, and lambda is its second argument. When we introduced lambdas, we've already talked about the rule that if lambda is the last argument, it can be moved out of the parentheses. Another syntax is putting lambda explicitly as the second argument. No one does that because it's not very readable, but it demonstrates that with is a regular function call. So curly braces mark the lambda, and this is an implicit receiver inside this lambda. Lambda with receiver is a lambda with this reference available inside. As usual for this reference, it can be omitted. That's how we get this nice syntax without explicit this. Lambda with receiver is simply a lambda with implicit this. You can access this inside lambda and call members on this receiver. To check that you understand that, answer the question: what is the type of this in the following example? The type is string builder. When we are talking about the with function, this refers to the first argument. Its type is the same as the type of the first argument, which is string builder here. There is a direct correspondence between regular functions and regular lambdas, and between extension functions and lambdas with receiver. The first name for lambdas with receiver was extension lambdas. Sometimes people may call them extension lambdas because of this correspondence. It's the synonym. At some point, we decided that lambda with receiver is a more clear name, which better explains the concept and illustrates what is going on, and is preferable for learning this feature. What is the correspondence? Inside the body of the extension function, you can use this as an implicit receiver. You can omit this and simply call the members of the receiver. Lambda with receiver is very similar because of this inside this lambda. You can omit it and simply call members without explicit specification. There is also the correspondence between the ways how you call lambdas. We've discussed that you can store a lambda in a variable. The same works for lambda with receiver. You can see how the type for lambda with receiver looks in Kotlin. You put a receiver type before the parameter list. Then follows the dot, then the parameters as usual in the parentheses. The return type is specified after the arrow, like for regular lambda. When you call a regular lambda, you call it as a regular function. You can also call lambda with receiver. You call it as an extension function. You see this correspondence. Regular lambdas correspond to regular functions, lambdas with receiver correspond to extension functions. Another example that I want to show you is the build string function. You don't need to use with for building a string, it was used for illustration. In real life, you can use build string to build a string builder and convert it to a string. It takes a lambda with receiver as an argument. Now let's look under the hood and look at how the build string function is implemented. We know that it takes lambda with receiver as an argument, so it expects a parameter of extension function type to string builder. What it does inside is something very simple. It creates a string builder. In the end, it returns the resulting string from the string builder. But without adding content to the string builder, you'll get an empty string as the result. In the middle, you should somehow call all the actions on the string builder provided in the lambda. Now try to complete this build string definition. The answer is that you call this lambda as an extension function on the string builder variable. As we've discussed, you call the variables of extension function types as extension functions. This is exactly what you do inside this function. This line invokes the lambda body and performs all the actions specified there. In this case, it calls all append actions specified in the lambda. Note that the build string function is also declared as inline. Under the hood, the function body and the lambda body will be inlined, so no extra objects for storing lambda will be created. The same inlining magic works with lambdas with receivers. Lambda with receiver is a syntactic thing for the lambda that interprets one of its parameters as this. To some extent, an extension function stores one of its parameters as a receiver, and the extension lambda does the same. That's how with is implemented. It's a very simple function. It only calls its second argument, the lambda with receiver, on its first argument, the receiver itself. You call block on the receiver argument as an extension function. Lambda with the receiver is a very powerful mechanism that allows us to create domain-specific languages, DSLs, in Kotlin. The whole topic of how to do that we'll discuss in the next course in detail. Right now, I only want to briefly mention that and show you that lambdas with receivers are really useful. In Kotlin, you can define DSLs for any XML-like structure like HTML. Everyone knows HTML, that's why it is such a good example to illustrate the idea. This code looks like HTML, but it's not a text, it's a regular Kotlin code. HTML and table are regular Kotlin functions. You can see how you mix the Kotlin language constructs like for loop with HTML syntax. All these curly braces denote in fact lambdas with the receivers. I've mentioned that if the curly braces are colored bold, that means they surround lambdas. Here, they are also lambdas with receivers. You invoke table function on the receiver of some specific type corresponding to HTML tag. Later we'll discuss in detail how to define such functions. Another example that employs lambdas with receivers is Gradle build scripts. Now Gradle script can be written in Kotlin. You again can notice all the curly braces. As you expect, they are lambdas with receivers.
You now know that lambda with receiver is simply a lambda with an implicit this inside. In this sense, it's similar to an extension function. Later in the next course, we'll discuss how to use lambdas with receivers to create DSLs, domain-specific languages in Kotlin. Next, let's see what other functions that use lambdas with receivers you may find in the Kotlin standard library. In this video, you'll learn more library functions similar to with that look like built-in language constructs, but just take lambda or lambda with receiver as an argument.
There are many similar to with functions defined in the standard library. I'll try to show you briefly when each one might be used and why we do have so many of them. What is the difference? We've already seen with. It takes any expression as an argument and uses it as the receiver inside the following lambda. Here we can access members of window without explicit specification. We adjust directly window properties. Run is very similar to with, but it is defined as an extension, which makes it possible to use it with a nullable receiver. If the receiver, window in our case, can be null, then you can't use with because this will be nullable inside the lambda. Then this can't be omitted. You will need to explicitly check whether it's not null. Run is helpful for such a case because you can use it with safe access. Run will be called only when the receiver is not null. But note that in many other cases, run and with are interchangeable. You can use the whole expression as the receiver. Here, the run will be called only when window by ID main exists and is not null. Apply is different because it returns the receiver as a result. We haven't used it, but actually with and run functions return the result of the lambda. The last expression inside the lambda will be the result of the whole invocation. Sometimes, however, it's convenient to return the receiver as the result. For instance, in a chain of calls. You can call other methods afterward, or you can, like in this example, simply assign the result to a variable. When you create a window instance, you might want to modify some of its properties right away. Apply is really useful for that, because the result is the modified main window. Note that we assign the variable here only if the result is non-null, and if it's null, we stop the current execution and return from the outer function. Also is similar to apply. It returns the receiver as well. However, there is the difference that it takes a regular lambda, not lambda with receiver, as an argument. Lambda with receiver is really useful when you can omit this reference, because you only call its members. However, there are cases when you pass the receiver as an argument, like here, when we pass window as an argument to the function showWindow. In this case, the also function is better, because it takes a regular lambda as an argument. Here, it, inside also, refers to window. You can introduce the window name for it if you want. Sometimes you can explicitly prefer to change the lambda parameter name. When you use also, that's possible. This table shows you the difference between all these functions. With goes in a cell together with run. With is only one non-extension function here. All other functions, including run, are extensions. The difference between them is which functions return the result of the lambda and which functions return the receiver. The functions in the first column take lambda with the receiver as an argument, with, run, and apply. The rest two take the regular lambda as an argument. Without looking back at the first slide with all the function declarations, you may practice your understanding and find the correspondence between these function declarations and their implementations. Note that we consider only extension functions now. Right afterward, we'll discuss the answer. The table is very useful. At first, let's focus on the functions returning the receiver as the result. They should return explicit this because this refers to the receiver inside the lambda. The rest two functions return the result of the lambda. We now distinguish at least pairs of functions. After that, we can go on and focus on which lambda do the functions take as an argument. Two functions take lambda with receiver. They expect a parameter of extension function type. This parameter of extension function type must be called as an extension function. If we call this block as an extension, then block corresponds to lambda of the receiver. The other two functions take a regular lambda, and then call a variable of a function type as a regular function. That gives us the result.
You now know what lambda with receiver is, and can use many helpful functions defined in the standard library. Next section will dive into the topic of Kotlin types and explain the correspondence between Kotlin and Java types. In this section, we'll discuss Kotlin types, see what Java types they correspond to, and discuss what happens with these types under the hood at the bytecode level.
In Kotlin, we don't distinguish primitive types and reference types. You either use int or nullable int. There are no primitives in the language. However, let's discuss what happens under the hood at the bytecode level. You can call Show Kotlin Bytecode action in IntelliJ IDEA or Android Studio. It opens you the generated bytecode corresponding to the open Kotlin file. In the bytecode, you can check the return type for functions, whether it returns a primitive value or a wrapper type. However, there is an easier option. You see here the decompile button. This button will decompile the generated bytecode to the analogous Java code. If you click on it, you'll see the Java code that corresponds to the initial Kotlin code. That's a good illustration of how the Kotlin functions and classes are implemented under the hood. At the same time, it shows how Java sees Kotlin functions and classes, because Java just accesses the Kotlin code via generated bytecode. As you can see, when you use a regular int type in Kotlin, it corresponds to a primitive int type under the hood. And when you use nullable int, this value can store nulls, so it should correspond to a wrapper type in Java. We don't have primitive types in the language, but we still have them at the bytecode level. The same applies to other primitives like double, float, or boolean. Note, however, that if you use int as a generic argument, then it can't be compiled to a primitive because you cannot use primitives as generic arguments. It becomes a reference type. The same works for arrays. When you use int as a generic argument of array, that corresponds to an array of wrapper types. To get an array of primitive types under the hood, you need to use an extra class like int array or double array. Kotlin string is replaced with Java lang string at the bytecode. Kotlin doesn't have its own string implementation. However, it modifies a bit the string API. For instance, Kotlin string hides some confusing methods that are present in Java lang string. In Java, you can use the replace all method. Surprisingly, it will return you all stars when you try to replace only a dot with a star. That happens because dot here is a regular expression. In Kotlin, we have two separate methods. The first one replaces dot with stars and works as you expect. It simply replaces substrings. If you want regular expressions, you pass a specific regular expression type, not a string. Now you're not surprised seeing the result. Any is replaced with Java lang object at the bytecode. Any in Kotlin is a supertype for all non-nullable types. Unlike object, any is not only a supertype for all reference types, but it's also a supertype for types like int corresponding to primitives. Note that under the hood, the autoboxing still happens like in Java. When you pass an integer as an argument to a function that expects any, this integer will be outboxed to a reference type. The same happens in Java when you pass a primitive as an instance of object. If you want to avoid it, you declare a function that takes int. Now it corresponds to a function that takes a primitive int, and the primitive value can be just passed to it. No boxing happens in this case. At the bytecode, unless lambdas are inlined, the Kotlin function types are replaced with regular interfaces, like function 0, function 1, and function 2, with the corresponding generic arguments. You can find the declarations of these function interfaces in the library. In the Kotlin code, you use the concise syntactic forms for function types, which are replaced by the corresponding interfaces under the hood. When the lambda is not inlined, an instance of the corresponding function interface is passed. If the lambda is inlined, then no instance is created, all the code is generated directly. When you call a variable of a function type as a function using the parentheses, in the bytecode, this call is replaced with a direct invoke call, unless this code is inlined, of course. As we've already discussed, you can call invoke explicitly from Kotlin. For expressions of function types, it's the same as using the concise syntax. The case when it's really helpful is working with variables of nullable function types. The next question returns us to the discussion of arrays. What will be printed here? True or false? Under the hood, Kotlin arrays are regular Java arrays. Specifically, they don't override the equals implementation. Equals for Kotlin arrays works in the same way as for Java arrays. The right answer is false. I've told you that Kotlin arrays simply correspond to Java arrays. In Java, you have to be aware that by default, equals checks reference equality for arrays. If you need to check the contents instead of reference equality, you use arrays equals. In Kotlin, it works in a similar manner. Double equals sign, which calls equals in Kotlin, only checks reference equality since equals method for arrays works that way. In Kotlin, you use the extension content equals to compare the contents. The good news is that in Kotlin you rarely use arrays. Kotlin has arrays specifically to have good Java interoperability, to make it easy to work with Java API that uses arrays. But if you write the Kotlin application from scratch and use only Kotlin, there is no reason for arrays, you can simply use lists. As we'll discuss later, mutable list is Java util array list under the hood. Array list is very close to array in terms of performance, so prefer lists to arrays by default, and avoid the necessity to remember the right way to compare arrays.
You now know that despite Kotlin doesn't distinguish between primitive and reference types, they are still hidden under the hood. And the boxing happens whenever you interpret a primitive value as a value of a reference type. Next, we'll uncover the difference between nothing and unit types and compare them with Java's void. In this video, you'll see how the Kotlin type hierarchy looks, what nothing type is used for, and why you can't use unit instead.
Kotlin has the top type in the hierarchy, any, which is a supertype of all types. Kotlin also has a bottom type, which is a subtype of all the other types. This one is called nothing. Now let's understand what it is used for and why it's called like this. The confusion is possible because in Kotlin we have two new types, unit and nothing, in comparison to Java's void. Unit is used instead of void, but nothing has the name similar to void. It might be unclear why these types are different. Let's try to understand why. First, let's start with unit. In Kotlin, unit is used always instead of void. Whenever you used void in Java, you use unit in Kotlin. It denotes that no meaningful value is returned from this function. These two syntactic forms are equivalent. You can either specify unit explicitly, which no one does, or you can simply omit it. At the bytecode, unit is replaced with Java void. In Kotlin, you always use it instead of void for the function that has no return value. Nothing is different to unit and void. It means the function never returns. You specify nothing return type for the function that only throws an exception. In Kotlin, you can define such a function and use it instead of throwing an exception. Imagine there is a specific for you use case exception and you always throw it with different details in messages. You can extract throwing this exception into a function and later call this function instead of all places where you had to throw an exception explicitly. If you specify that this function returns nothing type, then the Kotlin compiler uses the information that this function can't be completed normally for type inference and while locating the dead code. Unit and nothing names come from functional programming. If we look at their definitions, unit is the type that allows only one value, while nothing type has no values. You can think of one unit value as of the fact that the function completes successfully. And you can think of the fact that nothing has no values as of this function never completes. The function that only throws an exception cannot complete normally. Another way to put that is to say that the function returning unit is expected to complete normally, while the function returning nothing always completes abnormally. If you write a function that has an empty infinite while true loop inside, this function also never completes, and you can define nothing return type for it. Using an empty infinite loop is not really practical, but the exception cases are helpful. You can use an expression of nothing type anywhere where you otherwise would throw an exception. For instance, as an if branch. Here, if the condition is not satisfied, you can throw an exception, or call the function that throws the specific exception. Let's look at more examples of expressions of nothing type. To do is a function defined in the standard library. It throws not implemented error. You can use throw as a part of other expressions. For example, it might be convenient to use it as a part of else operator. Here, you throw a meaningful exception when the left-hand expression is null. Fail can be your custom function throwing your exception defined for the specific use case. Even return can be used as a part of other expressions, it just works. Under the hood, the compiler interprets return as an expression of nothing type. The question to you: which of the following expressions are expressions of nothing type? When you throw an exception, this expression itself has nothing type. When you call the function that throws an exception, that is also an expression of nothing type. You can use return as part of other expressions, and the compiler interprets it also as an expression of nothing type. Note that you can use Kotlin unit as a standalone expression. It refers to one instance of unit type. If you assign a function returning unit to a variable, then this variable will store this unit value. No one needs to assign it to a variable or explicitly return unit, since the compiler automatically infers that when no other value is returned. But that's possible. Now let's discuss why we need a separate nothing type, why we can't simply use unit for functions throwing exceptions or vice versa, nothing for functions completing normally. At first, let's try to use a report inside the if expression, like we did for functions throwing exceptions. It doesn't really make sense. Report returns unit value, and this unit value will be stored in the answer variable. Answer might then contain either integer or unit as a result. That's probably not what we want. Now let's imagine our fail function returns unit. We define a function that throws an exception, but we somehow forget to say that it returns nothing. We use the regular syntax, and then it automatically returns unit. What happens in this case? We'll try to understand how the compiler infers the type of the resulting expression, and we'll use the representation of type hierarchy for that. Let's see how the compiler infers the type of the answer variable. Its type should be a supertype of expressions in the first branch and in the second branch. At first, the compiler analyzes the integer constant. It has the int type. The fail function in our example returns unit. The compiler infers the supertype for int and unit, which is any. A function returning unit can be assigned to a variable. Then this variable stores Kotlin unit value. The unit value can't be stored in a variable of int type, but can be easily stored in any variable. That's why the compiler infers any as the type of this if expression, which totally is not what we want here. It happens if we use unit as the return type of fail. Now let's correctly use nothing and see what changes. The type of the first expression is again int. In the second branch, we now have fail call, which has nothing type. Since nothing is a subtype of any other type, that allows the compiler to infer int as the result. It's the right value because we always throw an exception if the if condition is not satisfied, so only integer value can be stored in the answer variable. The Kotlin type system allows us to express that. That's why it's great that we have the nothing type in the language. It allows us to use expressions of nothing type, extract throwing an exception into a function, and use this function as part of other expressions. Nothing is replaced by void. If your function returns nothing, then at the bytecode it will still return void, because there is no nothing type at JVM. That means that from Java you use functions returning nothing as returning void. In Kotlin, you use all the bunch of convenient nothing features. Now you can better understand the type hierarchy. Any is the top type, nothing is the bottom type. However, that's not that easy because we also have nullable types. User type is a subtype of nullable user type, because you can assign user expression to a variable of nullable user type but not vice versa. Thus, the correct top type is nullable any, not any. An interesting question here is what means this nullable nothing type? Think of what is the simplest expression of nullable nothing type. The answer is null constant. Say you define a variable and initialize it with null. Then if you try to assign a new value to it, you bump into an error saying something about type mismatch. Inferred type is user, but nullable nothing was expected. You can note the inferred nullable nothing for user variable here. The same thing happens when you create a list and store null inside. Nullable nothing and list of nullable nothing types are inferred by the compiler. If you think about it, that makes sense. You can assign null, as well as the variable that stores null, to any other nullable type. If you have a variable of nullable int, you can assign null there. Having a variable of nullable nothing is not really practical, but sometimes you can see similar errors, so it's good to know how it works from the compiler point of view. There is an easy solution that fixes this example. You specify the variable type explicitly whenever you want to initialize it with null. Then it has the right type, the type you want.
Now you know why unit can't be used instead of nothing, and that the only expression of nullable nothing type is the null constant. Next, we'll discuss how Kotlin nullable types interact with Java types. In this video, you'll learn how to mix Java and Kotlin code in terms of nullability. Java types are not divided into nullable and non-nullable types. So what happens when you call Java methods from Kotlin?
Kotlin nullable types under the hood are implemented using annotations. If you use the same annotations to annotate your Java code, then annotated Java types will be visible from Kotlin as nullable and non-nullable Kotlin types accordingly. An interesting question is, what happens if you use unannotated Java types? These are probably the majority of Java types. Let's discuss that. Such unannotated Java type will be visible from Kotlin as a regular Java type, and it will behave like in Java. It even has a special name. It's called a platform type. It's neither nullable nor a non-nullable type. You can sometimes see the notation type followed by the exclamation mark. It's annotation, not syntax. That means you can't declare a variable of such type in the Kotlin language. You can only sometimes find this type in error messages. If you see it, that means that this type came from Java and it is so-called of unknown nullability. A little bit of history first. The safest approach when you mix Java and Kotlin is to interpret each Java type as nullable Kotlin type. In this case, you are free from null pointer exceptions because you have to always check for the types explicitly. And in Kotlin, this approach was tried at first, but it didn't work out well. Kotlin wanted at first to interpret each Java type as nullable type. But then the early adopters said that the code was full of exclamation marks, and it wasn't really readable. It's the first problem. The second problem, which is more important, is that such an approach doesn't really work with generics. It wasn't a solution, so instead Kotlin uses the idea of platform type, which refers to the type that came from Java. When you see a platform type in an error message, like in this example, most probably you can safely ignore it. The fact that you see the exclamation mark is not connected with the source of the problem. Here we try to assign string to Boolean. The problem lies in incompatible types, but is not connected with the fact that it's a platform type. Exclamation mark means that the type came from Java, but you need to look for a different source of the problem if you see it in error message. There is a question to you. You know that the platform type behaves like a regular Java type. What do you think would happen in this example? We dereference a variable of platform type, which stores null that came from Java. We have several options. Null pointer exception is thrown, null is printed, compilation error, or illegal state exception is thrown. The right answer here is null pointer exception. This code behaves like regular Java. That means that when we try to dereference the variable of the platform type, we get null pointer exception. Kotlin compiler infers the type of session description as string platform type, since this type is not annotated in Java. Kotlin allows you to dereference it, so you can use it as in Java. It's a known nullability, so it can probably work fine. However, you can also get a null pointer exception like in Java. If you use the safe access here, then everything is fine, you have null as a result. Now you know that if you mix Kotlin and Java, you'll still have null pointer exceptions. It seems that Kotlin doesn't save you from NPS in this case. For convenience, we have to sacrifice the 100% null safety. The question then is whether it's still possible to prevent null pointer exceptions. What can be done? There are still some things that you can do to achieve a better level of null safety. There are two main pieces of advice. At first, you can annotate your Java types. If that's not an option, it's useful to specify explicitly types of variables which get values from Java functions. Now let's consider these two pieces of advice in turn. First, let's talk about annotating Java types. Annotating Java types is easy. Simply add nullable and not null annotations to Java code, and Kotlin will interpret annotated types as nullable and non-nullable types. You can annotate a function return type, parameter types, and Kotlin will interpret the types accordingly. Different annotations are supported. Many frameworks define their own nullability annotations. Kotlin tries to support all of them. These annotations have different names, but they all mean the same. The question: what happens with the code after we add nullable annotation? We have all the same possible options. Here we get a compilation error. Now Kotlin sees the getDescription function as the function returning nullable string. Then it infers the type of the description variable as nullable string. That produces an error that you can't dereference a nullable string. Now Kotlin forces you to use either safe access operator or another way to cope with nullable types. Annotating Java types really helps. However, you can ask whether you really need to annotate all Java types in your codebase. And the answer is, if you have an option that might be used by default, you can specify only the other one. For instance, you can annotate only nullable types if you pick not null by default, or vice versa. It's supported via GSR 305. You need to introduce your own annotation that specifies the default. You annotate it itself with type qualifier default, define the scope of applicability, and specify which value, nullable or not null, should be used by default. For instance, you can apply the declared minor null by default annotation to a package. Then all the types in this package will be considered as annotated by your default choice, not null in this example. Note that the Kotlin compiler interprets such problems as warnings. To explicitly make such warnings errors, you add the compiler option. afterward you get an error if the code doesn't compile because of nullable and non-nullable types, which are inferred using the specified default. That was all about the first option. You can annotate your Java types, and you can specify the default annotation to reduce the number of annotations added to your Java code. Read the Kotlin documentation to find more details about JSR 305 support. However, annotating Java code isn't always possible. This Java code can be an external library, the part of your application that you don't want to touch, or you don't want to annotate the Java code for some other reasons. There is still good advice on what can be done to minimize nullability issues when you write the code in Kotlin which calls Java methods. The following example should be rather trivial. What happens if you add an explicit nullable type annotation for our previous example? The answer is straightforward. We annotate the type as nullable, which forces us to check the value explicitly for being non-null. Null is printed as a result. The other case is more interesting. What happens if you make the explicit variable type not a nullable, but a regular string? The same options again. Now the last option is correct. You could have guessed that because all others were already present. A legal state exception is thrown. Let's look deeper at what's going on here. If you specify the non-null type of a variable explicitly and assign to this variable something that comes from Java, formally an expression of a platform type, then Kotlin generates additional checks that will throw an exception if this expression turns out to be null. That is much better than getting null pointer exceptions sometime later, because you know the source of the problem right away. You get the detailed message of what was null. It's much better than trying to guess which reference caused NPE and why, like in Java. If you don't add explicit type specification, you have the same problems as in Java. Let's closely look at what happens in the bytecode when you define a variable and assign something that comes from Java to it. Kotlin compiler generates a special additional check that ensures that your write expression is not null. You can assign a value of a platform type to a non-nullable type, but if the actual value turns out to be null, then the exception will be thrown at runtime. The similar check is generated for your public APIs that can be called from Java. The Kotlin compiler tries to check that what comes and supposed to be not null is not null, so no one could pass null while using the Kotlin function from Java. These intrinsic checks allow you to catch all the possible null problems earlier and with the detailed error messages. If you want, you can switch off generating these intrinsic checks. They are really useful, but if it's critical for you, for example for performance reasons, or you don't use any Java libraries and don't mix Kotlin and Java, it's possible to switch it off using the compiler option. Now we've discussed both options of what you can do to prevent null pointer exceptions if you mix Kotlin and Java in one project.
When you mix Kotlin and Java code, to prevent NPEs, you can either add nullability annotations to your Java types or add explicit type specifications to the Kotlin code that uses regular Java types. I would say that Kotlin platform types represent a good compromise between safety and convenience. On the one hand, you have NPE-free guarantees when you write pure Kotlin code. On the other hand, you lose these guarantees when you use Java libraries. However, that still works well for majority of practical use cases. Next, we'll discuss how Kotlin list and Kotlin mutable list correspond to Java util list and what kind of compromise we can achieve there. In this video, you'll learn about the correspondence between Kotlin collection types and Java collection types.
While talking about extensions, we've discussed that Kotlin's standard library contains a bunch of extension methods on Java collections. And when you create a collection in Kotlin, you actually create an instance of Java standard collection under the hood. Thus, there should be the correspondence between the list in Kotlin and the interface Java util list. We already saw that other types are replaced at the bytecode with Java types, so probably here it works the same way. However, it's not that straightforward, because in Kotlin we have both read-only list and mutable list. They both somehow correspond to one Java util list. How it works then? Now let's discuss that. List and mutable list are simple interfaces defined in Kotlin collection package, and mutable list extends list. Note that we specifically use the word read-only to describe the interface list in Kotlin. It's not the same as immutable. It's not immutable data structure which cannot be changed. No, a read-only interface just lacks mutating methods. The actual list can be modified via different reference. The question to you: what happens when running the code below? Here we create a new mutable list, assign the mutable list variable to a read-only list, and modify the initial list. There are options. The assignment won't compile, we can't modify the initial list will be printed, or the modified list will be printed. What's your choice? This code compiles fine. What's happening here is the read-only reference observes the mutation of the mutable list. Here, the first mutable list refers to the created list object in memory. Then we assign the reference to this list to another variable of read-only list type. Having the variable of a read-only list only means that you can't call add members on such a list. List lacks mutating method. However, this list can be modified because there is another reference through which you can modify it. The read-only list will simply observe this change. At the bytecode, both Kotlin list and mutable list interfaces are replaced with Java util list. By default, when you create an instance of mutable list, Java util array list will be created. Kotlin somehow pretends that Java util array list implements Kotlin mutable list. There is some kind of compiler magic when a Java interface is substituted by the Kotlin interface. Under the hood, it works via the same mechanism as nullable types. The similar idea of platform types is used. That's how the platform type for the collection type is written. Again, you cannot define a variable of such type, you can only find it in error messages or when you check in ID what type does this variable have. This platform type means that it came from Java, and it is a type of unknown mutability. We don't know whether it was intended to be mutable or read-only, so we can use such type as both. You can ask, why do we need this? Why do we need these read-only types at all if they are not truly immutable? And the answer is that with Kotlin, it's now much more difficult or even impossible to break something accidentally. The problem with always having mutable methods in a list is that you cannot understand that this list shouldn't be changed. For instance, it is a part of API and the API didn't intend the list to be modified, but it's not a library, it's a piece of your own application. You usually simply return this variable in Java as of Java util list type, and in Java, you can accidentally call the add method because you think it's a local collection, but it's not. In Kotlin, it's no longer the case. You can still call a modification method if you explicitly cast it to the mutable collection, but in this case, you really want to break this code. Accidentally, you can't do it, so such approach prevents from some possible errors.
Like with nullable types, Kotlin collection types provide a good compromise between safety and convenience. You explicitly say whether a collection is intended to be modified by using a read-only or mutable type. And you can easily mix Kotlin and Java collection types because the same classes are used under the hood. No extra wrapping is needed. We've discussed the correspondence between Kotlin and Java types. You now know how to mix two languages and better understand how the Kotlin types are represented at the bytecode level. Our next task is to write the code that the compiler will generate for instead of calling the filter function, because filter is inlined. And here I provided the one more implementation of the filter function that we can use. The implementation of the standard library is
kind of the same but a bit different. So we may use this one for simplicity. So now our task is what code is generated instead of this line, instead of this calling filter. And we can simply copy paste the filter function call, and then replace all the values that are substituted to different values. So at first, here we know that our t is int, so we have a list of int. Then this reference, so filter is an extension function called on a receiver. In this case, our receiver is list. So here we call filter on list, and when we generate the code, list is substituted instead of usages of this. And then we have this predicate, and the main idea is that the lambda bodies are inlined. So instead of calling this predicate, creating this predicate and storing this lambda, its body is substituted directly. And in this case, it is replaced with element. So what we'll have in the end is element is not null. So we check whether element is not null, and if so, we do what we've done before. So this task illustrates you, let you practice to understand what code is generated by the compiler when you actually write a filter function. So that was only for practice. All this code is generated at the bytecode level. You may try to see what the bytecode is generated by itself. But that illustrates what's going on under the hood of this task. Our task here is to implement the function that builds a sequence of Fibonacci numbers using this build sequence function and the yield mechanism. So let's do that. And for convenience, let's store the pair of elements, the first two elements, in a pair. So at first it will be 1 and 0. So it will these elements will denote last two elements that we of our sequence, and because they are used to calculate each new element, so we store two of them and we store them as one pair, and the first two are 1 and 0. So then we can say while true, because we don't know when we stop. This sequence might be infinite. And while true, at first we can yield each new element, we should yield it, and then we just return the first element in our pair. And then we need to update the elements. So what we do is we say that now the second element becomes the first one, and the sum of first and second element becomes the next element, the second element. So now, if we run it, so let's format it like this. When we run it, we'll see that that is exactly the answer that we expected. In this task, we need to simplify the usages of the auxiliary functions. So they, in this case, they're used not in their best way, not in the most straightforward way. In the first task, we have this let function, and it assigns some values to properties. The problem here is this it variable, which we can which somehow we use, and we use it only as the receiver, so it makes sense to replace it with an implicit receiver, to replace this lambda to lambda with implicit receiver. And we can simply do this by converting let to run, or overall to use with instead. So for instance here we can either use run, or because in this case it's possible, we can use also with. So both options are possible in this case. Next, our next example also shows kind of anti-pattern, because you use both these auxiliary functions one after another. And that really happens sometimes in the code. And probably you just wanted to express something, then you change your mind, you had some idea, then you used again another function. But this usage of like when you use something with it after calling let, that just can be replaced with one run call, for instance, here, and that's just looks more simple. So no need to use this function one after another. In the last case, we use with in this case, but you see that you return this as the last expression, and there is another function that does exactly that. That returns this, and it's apply function. So apply function just calls this, and it says you that this expression is unused because in the apply case there is the lambda returns unit, so it is considered to return nothing meaningful, and the receiver is used as the result. So there was just simple cases when these functions were kind of misused. There are often situations when one or the other is possible and both options are correct, and you may find more information about that on different style guides in the internet. In this task, we need to implement two member extension functions, which later will be called as extensions on string, but only inside the specific context of the words class. So let's start with the first one and comment this for now. Let's implement a record function. So we need we need to call it as an extension on string. So we simply can define an extension on string here, and it will be member extension, so it can access all the members of the class. So what we can do here is, what we need to do here is to simply add this string receiver to the list of our words, and that's it. So that will add this string when we call it to a list of our words. And speaking about this member extension function, so here it is extension function, but it is also a member because it's defined inside the class. And you can call such an extension function, which is defined in the context of the class, whenever this instance of the class is available. So it's clear that, for instance, you can call such function inside class for, like, I don't know, we can say initialize and add some first word here. Then you can call it as inside extension to the class words. So say it full, and here we can say we can, inside this extension function, we can also call this extension on full, because this implicit receiver to implicit this of the type words is available. So that's clear that such function is possible to call inside member function, inside extension function. But when you need to call such function, not inside the class or not inside an extension of the class, but just somewhere, you can use all these auxiliary functions like with. In this case, you also have words available in this context, and therefore this is available. This refers to words, and that's how the Kotlin compiler understands that it's possible now to call these member extension functions. Now let's implement the second function that should be operator function. And again, to a string, we have operator function unr plus. It's called unr plus, and we simply call record here, and we can now check that everything works as expected. That no, it won't work because I have this line commented. But now you see that these functions compiled and work.
So that's how you may define these member extension functions. And later we'll discuss in the next course, when we'll discuss how to write domain-specific languages in Kotlin. You'll see like more examples like this of defining member extension functions, of using them outside of the context. So this might be considered as kind of introduction to the topic when you see how you can define some special syntax for your class. And also this example illustrates that you can use auxiliary functions like with to work with member extension functions defined in your class.
Congratulations! You've finished Java for Kotlin Developers course. Now you can confidently use Kotlin for your daily tasks. We really hope that you enjoyed the course. The next course will cover more advanced Kotlin topics like DSLs, variants, refined generics, delegated properties, reflection, and so on. And there'll be the whole separate course covering coroutines. So stay tuned!